In 1859, a German chemist named Robert Bunsen noticed something peculiar. When different salts burned in his newly invented burner, each element painted the flame a different color, as if matter itself were speaking in light. This quiet observation, made in a Heidelberg laboratory as autumn deepened outside the windows, would eventually unravel one of nature's oldest secrets. Over the next 6 decades, scientists across Europe would learn to read these spectral lines like a celestial alphabet, discovering new elements, measuring the composition of distant stars, and finally, through the gentle persistence of Niels Bohr, glimpsing the hidden architecture of the atom itself. If these slow journeys through scientific history bring a kind of peace to restless evenings, the subscribe button will bring more of them to quiet nights ahead. The flame flickers in Bunsen's laboratory, the colors shift and glow, and the story can begin there. In the autumn of 1859, in the pleasant university town of Heidelberg, nestled along the banks of the river Neckar in the Grand Duchy of Baden, 2 professors began a collaboration that would quietly transform our understanding of matter itself, though neither man could have fully appreciated, in those early days of shared work and conversation, just how far-reaching their partnership would prove to be. Gustav Robert Kirchhoff, a physicist of 35 years who had arrived at Heidelberg only the previous year, and Robert Wilhelm Bunsen, a chemist of 48 who had been at the university since 1852, found themselves drawn together by a mutual curiosity about the behavior of light when it passed through flames containing various chemical substances. Their collaboration, which would unfold over the following years in a modest laboratory space that they came to share, represents one of those gentle accidents of scientific history where the right combination of skills, temperaments, and circumstances allowed for discoveries that neither man could have made alone. Robert Bunsen had already established himself as one of the foremost chemists in the German-speaking world by the time Kirchhoff joined the Heidelberg faculty, and his reputation rested on decades of careful experimental work that ranged from studies of arsenic compounds, which had cost him the sight in one eye and nearly his life on more than one occasion, to investigations of volcanic gases collected at considerable personal risk from active fumaroles in Iceland. He was known among his colleagues as a man of great practical ingenuity, someone who could design and build the apparatus needed to answer whatever question currently occupied his mind, and his laboratory was filled with instruments of his own devising, each one crafted to solve a particular problem that had presented itself during the course of his researches. Bunsen possessed that rare combination of theoretical understanding and manual dexterity that allowed him to move seamlessly between the conception of an experiment and its physical realization, and it was this practical genius that would prove essential to the work he undertook with Kirchhoff. Kirchhoff, for his part, brought a different but entirely complementary set of abilities to the partnership, for he was trained in the mathematical physics that had flourished in the German universities during the middle decades of the 19th century, and his mind moved naturally toward the formulation of general principles and laws that could unify disparate phenomena under a single theoretical framework. He had already made significant contributions to the understanding of electrical circuits, deriving the laws that still bear his name and that describe how current and voltage distribute themselves through networks of conductors, and he approached the study of light with the same instinct for finding underlying order amid apparent complexity. Where Bunsen might see a practical problem to be solved through clever apparatus and patient observation, Kirchhoff was inclined to ask what fundamental principles governed the behavior being observed, and this difference in perspective meant that each man could see aspects of their shared work that might have remained invisible to the other. The instrument that made their collaboration possible, and that deserves its own moment of quiet attention in this account, was a burner that Bunsen had developed some 4 years earlier, in 1855, while working on problems quite unrelated to spectroscopy. The burner that now bears his name, though he himself acknowledged that the basic principle had been employed by others before him, represented a significant improvement over the gas flames that chemists had previously used for heating and analysis, and its importance lay not in any dramatic increase in temperature but rather in the quality of the flame it produced. By allowing air to mix with the gas before combustion, through adjustable openings at the base of the burner tube, Bunsen created a flame that burned with very little luminosity of its own, a pale blue cone that gave off heat in abundance but contributed almost no interfering light to whatever substance was being heated within it. This non-luminous flame was essential for the spectral observations that Bunsen and Kirchhoff would soon undertake, for a bright yellow flame of the sort produced by ordinary candles or oil lamps would have overwhelmed the delicate colored lines emitted by chemical elements, making it impossible to distinguish one substance from another. The design of the Bunsen burner was characteristic of its inventor's approach to scientific problems, being simple in conception but precise in execution, with each element serving a clear purpose and nothing included merely for ornament or complexity. The adjustable air intake allowed the user to control the character of the flame, making it more or less luminous as the experimental requirements demanded, and the steady flow of gas through the vertical tube ensured that the flame remained constant over long periods of observation, neither flickering unpredictably nor changing in intensity as the work proceeded. It was, in short, a tool designed by someone who understood exactly what was needed and how to provide it with the minimum of fuss, and it served Bunsen and Kirchhoff admirably throughout their years of collaboration, heating countless samples of metallic salts and other compounds while contributing nothing of its own to the spectral patterns they sought to analyze. The laboratory space where Bunsen and Kirchhoff conducted their spectroscopic observations was not a grand or impressive chamber of the sort that one might imagine when thinking of revolutionary scientific work, but rather a modest room that had been deliberately modified to serve their particular needs. They had coated the walls with soot, that fine black carbon deposited by incompletely burning flames, in order to minimize the reflection of stray light that might have interfered with their delicate observations, and the resulting environment was one of almost complete darkness, broken only by the pale blue flame of the burner and the narrow beam of colored light that emerged from their spectroscope. In this blackened room, with the curtains drawn against any intrusion of daylight and the air carrying the faint smell of combustion products, the two professors would spend countless hours peering through their instruments at the thin bright lines that different elements produced when heated to incandescence, gradually building up the catalogue of spectral signatures that would form the foundation of a new analytical method. The spectroscope itself, the instrument through which they observed and measured the colored lines produced by heated substances, incorporated prisms obtained from Carl August von Steinheil, an optician working in Munich who had established a reputation for producing glass of exceptional quality and precision. These prisms, cut from carefully selected blocks of optical glass and polished to exacting standards, had the property of bending light by different amounts depending on its color, spreading out the constituent wavelengths of any beam that passed through them and revealing the detailed structure that would otherwise have been invisible to the eye. Steinheil's prisms were essential to the success of Bunsen and Kirchhoff's work, for inferior glass would have introduced distortions and aberrations that might have confused the spectral patterns they were trying to map, and the precision of their measurements depended directly on the quality of the optical components they employed. It is worth noting, in passing, how much of scientific progress depends on such collaborative networks, Where the skill of an optician in one city makes possible the discoveries of physicists and chemists in another, each contribution necessary but none sufficient on its own. The path to their great discovery was not without its difficulties and doubts, and it is recorded that Bunsen himself, despite his practical genius and his willingness to explore new methods of chemical analysis, was initially skeptical about whether the observation of spectral lines could ever provide reliable information about the composition of substances. He had seen how easily the bright yellow line of sodium, which appeared whenever even the smallest trace of that element was present in a flame, could contaminate observations and lead to false conclusions, and he worried that the method might prove too sensitive for practical use, detecting impurities so minute as to be chemically insignificant. It fell to Kirchhoff, with his physicist's instinct for underlying principles, to convince his colleague that this very sensitivity could be turned to advantage, that the ability to detect traces of elements in quantities far smaller than any chemical method could reveal was not a weakness but a strength, and that with proper care and systematic study, the spectral lines could indeed serve as reliable indicators of chemical identity. There is an anecdote preserved in the historical record, one of those small human details that reminds us that even the most important scientific work is conducted by ordinary people in ordinary circumstances, concerning an incident that occurred during the early stages of Bunsen and Kirchhoff's experiments. In the course of heating some substance or other, testing the response of their apparatus or perhaps simply demonstrating the method to a visitor, Bunsen managed to set fire to the curtains of the laboratory, an accident that must have caused some consternation at the time, but that serves now mainly to illustrate the informal and exploratory character of those early investigations. One imagines the two professors, the elder chemist and the younger physicist, dealing with the immediate crisis of smoldering fabric while perhaps exchanging rueful glances at the hazards of their chosen pursuit, and then returning, once the danger had passed, to the patient work of observation and measurement that would eventually yield such significant results. The burned curtains were replaced, the experiments continued, and the momentary excitement gave way once more to the quiet rhythms of scientific inquiry. The crucial insight that emerged from these long hours of observation in their darkened laboratory, the recognition that would prove most consequential for the future of chemistry and physics alike, was that each chemical element, when heated to the point where it emitted light, produced a characteristic pattern of spectral lines that was unique to that element and that remained constant regardless of how the element was combined with other substances. Sodium always produced the same bright yellow line, whether it was present as pure metal, as common salt, or as any of the countless other compounds in which it might be found, and the same principle held for every other element that Bunsen and Kirchhoff examined. This discovery, which they likened to a fingerprint or signature that allowed each element to be identified with certainty, transformed spectral observation from a curiosity into a powerful analytical tool, for it meant that the composition of any substance could in principle be determined simply by heating it and examining the light it emitted. The paper in which Bunsen and Kirchhoff announced their method to the scientific world appeared in October of 1859 in the Annalen der Physik, one of the leading journals for physical science in the German language, and it bore the straightforward title Chemical Analysis by Observation of Spectra. The paper was written in the careful, measured style that characterized serious scientific communication of the period, presenting the experimental findings in sufficient detail that other researchers could replicate the work and verify the conclusions for themselves, and it included descriptions of the spectral lines produced by various elements along with discussions of the conditions under which the observations had been made. The tone was confident but not boastful, claiming no more than the evidence warranted while making clear that the authors believed they had discovered something of genuine importance for the practice of chemical analysis. The implications of the fingerprint concept, as it came to be understood, extended far beyond the immediate practical applications that Bunsen and Kirchhoff had in mind when they began their work. If each element produced its own unique spectral signature, then it became possible not only to identify known substances but also to discover new ones. For any unfamiliar pattern of lines would indicate the presence of an element that had not yet been catalogued. Within the first few years following their initial publication, Bunsen and Kirchhoff used their spectroscopic method to identify two entirely new elements, Cesium and Rubidium, which they detected through their previously unknown spectral lines in samples of mineral water from the springs at Durkheim. The names they chose for these elements reflected the colors of the spectral lines by which they had been discovered, with cesium deriving from the Latin word for sky blue and rubidium from the Latin for deep red, and these naming choices served as a permanent reminder of the method that had brought them to light. The complementary nature of Bunsen and Kirchhoff's partnership was perhaps most evident in the way each man approached the theoretical questions raised by their experimental findings. Bunsen, true to his identity as an experimental chemist, was primarily concerned with the practical utility of the spectroscopic method, with establishing it as a reliable tool for chemical analysis that could be used by other researchers in their own laboratories, and he devoted considerable effort to refining the techniques and apparatus needed for accurate observations. Kirchhoff, meanwhile, was drawn to deeper questions about the nature of the spectral lines themselves, about why each element should produce light of particular colors and not others, and about the relationship between the emission of light by heated substances and the absorption of light by cooler ones. This division of labor, with Bunsen attending to the practical and Kirchhoff to the theoretical, allowed the two men to pursue their different interests while remaining united in their common project, and it ensured that the work they produced together was both experimentally sound and theoretically significant. The years following their initial publication saw Bunsen and Kirchhoff continue to refine and extend their methods, examining the spectra of more and more elements and building up an increasingly comprehensive catalogue of spectral signatures that could be used for chemical identification. They developed improved spectroscopes with greater resolving power, allowing them to distinguish between lines that had previously appeared to be single but that were in fact composed of multiple closely spaced components, and they established standard procedures for the preparation of samples and the calibration of instruments that helped to ensure consistency between different observations. The work was painstaking and often tedious, requiring long hours in the darkened laboratory and careful attention to countless small details. But neither man seemed to find this burdensome, for they were sustained by the knowledge that each new spectrum added to their growing collection brought them closer to a complete understanding of the spectral behavior of matter. The physical environment of their shared laboratory, that soot-blackened room where so much of this work was conducted, must have presented a striking contrast to the pleasant surroundings of Heidelberg itself, with its castle ruins overlooking the town and its forested hillsides rising along the valley of the Neckar. One imagines the two professors emerging from their darkened chamber after a day of observations, blinking perhaps in the afternoon light and carrying with them the faint smell of combustion products that would have permeated their clothing and hair, to walk through streets that knew nothing of spectral lines and absorption bands and the fingerprints of elements. The townspeople going about their daily business would have had no reason to suspect that anything of particular significance was occurring in the university buildings nearby, for scientific revolutions rarely announce themselves with fanfare, preferring instead to unfold quietly in laboratories and studies while the world outside continues on its accustomed course. The success of the Heidelberg partnership owed much to the particular circumstances that had brought Kirchhoff and Bunsen together. Circumstances that neither man had chosen or anticipated, but that proved fortuitous for the development of spectroscopic science. The University of Heidelberg in the 1850s was a place where serious research was valued and supported, where professors were given the time and resources to pursue their investigations without excessive interference from administrative concerns, and where the presence of talented colleagues in related fields created opportunities for fruitful collaboration. Kirchhoff's appointment to the physics chair had brought him into close contact with Bunsen, who was already well established in the chemistry department, and their shared interest in the behavior of light and matter had done the rest. Such meetings of minds and methods cannot be arranged or commanded, for they depend on accidents of timing and temperament that no administrator can control, but when they occur they can produce results that far exceed what either party could have achieved alone. As the collaboration matured and their methods became more widely known, Bunsen and Kirchhoff found themselves at the center of a growing community of researchers who were applying spectroscopic techniques to problems in chemistry, physics, and astronomy. Letters arrived from colleagues across Europe and beyond, asking for advice on apparatus and procedures, reporting new observations, and proposing extensions of the method to new domains. The two professors responded to these communications with the generosity that characterizes the scientific community at its best, sharing their knowledge freely and welcoming the contributions of others to the field they had helped to create. The fingerprint concept, once established, proved to be a gift that kept on giving, opening up avenues of investigation that Bunsen and Kirchhoff themselves had never imagined and that would continue to yield discoveries long after both men had passed from the scene. The work that began in that modest laboratory in Heidelberg in 1859, with a non-luminous flame and a set of Munich prisms and the patient observation of colored lines, would eventually lead to insights about the structure of atoms and the nature of matter that neither Kirchhoff nor Bunsen could have anticipated. But those developments lay in the future, and in the autumn of that year, as the two professors began their collaboration, they could not know where their inquiries would lead them, only that the spectral lines they observed seemed to hold some secret about the elements that composed the material world. It is enough, for now, to rest with them in their darkened room, watching the pale flame of the Bunsen burner and the bright lines of light that emerge from the spectroscope, and to appreciate the quiet satisfaction of work well begun, of questions carefully posed, and of a partnership that would prove equal to the task before it. In the quiet laboratories of Heidelberg, during the early months of 1860, Robert Bunsen and Gustav Kirchhoff found themselves engaged in a rather systematic examination of various mineral samples, applying their newly refined techniques of spectral analysis to whatever substances came within reach of their careful attention. The work proceeded slowly, as all good scientific work tends to do, with the two men spending long hours peering through the eyepiece of their spectroscope, recording the positions of colored lines with the patience that such observations demand, and gradually building up a catalogue of the characteristic signatures that different elements inscribe upon the spectrum when their vapors are heated in the colorless flame of Bunsen's improved burner. It was during this period of methodical investigation that they turned their attention to a sample of mineral water from the spa town of Durkheim, located not terribly far from Heidelberg in the Palatinate region, where the waters had long been valued for their supposed therapeutic properties, though the precise chemical composition of these waters remained, at that time, only incompletely understood. The mineral waters of Durkheim, like those of many spa towns throughout Europe, contained a complex mixture of dissolved salts and trace elements that had been leached from the surrounding rocks over countless years of slow geological processes. And Bunsen had obtained samples of this water with the intention of subjecting it to spectroscopic examination, curious to see what elements might reveal themselves through the telltale patterns of light that each produces when vaporized in a flame. When he first introduced a small quantity of the evaporated residue from this mineral water into the flame of his burner and observed the resulting light through the spectroscope, he noticed something rather unexpected, which was the presence of two bright blue lines in a region of the spectrum where no known element was understood to produce such emissions. These lines appeared at wavelengths that we would now express as approximately 455.5 nanometers and 459.3 nanometers. Though Bunsen and Kirchhoff would have recorded their positions using the somewhat different conventions of measurement that prevailed at that time. But regardless of the units employed, the essential observation remained the same, which was that these blue lines did not correspond to any element that had previously been catalogued in their growing collection of spectral signatures. The appearance of unknown spectral lines presented Bunsen and Kirchhoff with an intriguing possibility, namely that the mineral water from Durkheim might contain traces of an element that had never before been identified by chemists, an element so rare or so difficult to separate by conventional means that it had escaped detection despite the considerable efforts that had been devoted to analyzing mineral waters and other natural substances over the preceding decades. This was, of course, a hypothesis that required careful verification, for it would not do to announce the discovery of a new element based solely on the observation of unfamiliar spectral lines, which might conceivably have some other explanation, such as contamination of the sample or interference from compounds that somehow modified the emissions of known elements. And so Bunsen set about the laborious task of concentrating the substance responsible for these mysterious blue lines in quantity sufficient to permit more thorough investigation. The process of concentration that Bunsen undertook was one of those quietly heroic feats of experimental persistence that rarely receive the attention they deserve, for he found it necessary to evaporate truly enormous quantities of mineral water in order to obtain even small amounts of the residue containing the unknown element. Over the course of many months, Bunsen processed something approaching 44,000 liters of the Durkheim mineral water, allowing it to evaporate slowly and collecting the residues that remained, then subjecting these residues to various chemical separations intended to isolate and concentrate the component responsible for the blue spectral lines. 44,000 liters is, to give some sense of the scale involved, roughly the amount of water that might fill a modest swimming pool, and the work of evaporating such a quantity, even with the assistance of natural evaporation in suitable vessels, represents a commitment of time and labor that speaks to Bunsen's determination to pursue his observations to their logical conclusion, however tedious the intermediate steps might prove to be. As Bunsen worked through this process of concentration and purification, the blue spectral lines grew stronger and more distinct in his samples, confirming that he was indeed succeeding in isolating the substance responsible for them, and eventually he obtained a quantity of material sufficient to permit chemical analysis alongside the spectroscopic observations. The combined evidence from these investigations left little room for doubt that he had indeed identified a previously unknown element, one that belonged to the family of alkali metals alongside sodium, potassium, and lithium, but which possessed its own distinctive properties and its own unmistakable spectral signature. Bunsen named this new element cesium, drawing upon the Latin word cesius, which describes a particular shade of blue, the kind of blue one might see in a clear sky, and this name was chosen specifically to commemorate the striking blue spectral lines that had first revealed the element's existence to the careful observer peering through the spectroscope in the Heidelberg laboratory. The announcement of cesium's discovery was received with considerable interest by the scientific community, though it must be said that not all chemists were immediately convinced of the validity of spectroscopic methods as a means of identifying new elements. Among the skeptics was Friedrich Wöhler, a distinguished chemist whose earlier synthesis of urea had helped to establish the foundations of organic chemistry, and who maintained a preference for what he called wet chemical analysis, meaning the traditional methods of precipitation, crystallization, and gravimetric measurement that had served chemistry so well for so many years. Wöhler's reservations were not unreasonable, for the spectroscope was still a relatively new instrument in chemical practice, and its theoretical foundations remained somewhat uncertain, depending as they did on the assumption that each element produces a unique and unchanging pattern of spectral lines, an assumption that had not yet been tested under all conceivable conditions and which might, for all anyone knew at that time, proved to have exceptions or limitations that would undermine its reliability as a tool for elemental identification. Bunsen and Kirchhoff, however, were confident in their methods and their results, and they continued their spectroscopic investigations of various mineral samples throughout 1860 and into 1861. Systematically examining whatever substances came to their attention and recording the spectral signatures they observed. It was during this period that they turned their attention to samples of lepidolite, a lithium-bearing mica mineral that occurs in granitic pegmatites and which was of interest partly because of its lithium content and partly because it was known to contain various other elements in trace amounts that might repay spectroscopic investigation. When Bunsen examined the flame spectrum produced by samples of lepidolite, he observed, alongside the expected lines of lithium and other known elements, a pair of prominent red spectral lines in a region of the spectrum where no familiar element was known to emit light, and these red lines, appearing at wavelengths in the deep red portion of the visible spectrum, suggested the presence of yet another unknown element concealed within the mineral sample. The discovery of these red spectral lines in lepidolite came in 1861, following rather closely upon the discovery of cesium the previous year, and Bunsen again undertook the process of concentration and isolation necessary to confirm that the lines represented a genuinely new element rather than some artifact or misidentification. This time the work proceeded somewhat more quickly than it had with the Durkheim mineral water, partly because lepidolite is a solid mineral that can be processed more conveniently than large volumes of liquid, and partly because Bunsen had by now developed considerable expertise in the techniques required to isolate trace elements from complex mineral matrices. The chemical behavior of the new element proved to be similar to that of cesium and the other alkali metals, confirming its place in this family of elements, and Bunsen named it rubidium, from the Latin word rubidus, meaning deep red, in reference to the characteristic red lines that had first betrayed its presence to the spectroscope. The discoveries of cesium and rubidium within such a short span of time provided powerful validation of spectroscopic methods as a legitimate and valuable tool for chemical investigation. For here were two entirely new elements that had eluded detection by all the traditional methods of chemistry despite being present, albeit in small quantities, in substances that chemists had examined many times before. The mineral waters of Durkheim had been analyzed by competent chemists prior to Bunsen's work, and lepidolite had been subjected to chemical examination by numerous investigators interested in its lithium content and other properties. Yet none of these earlier studies had revealed the presence of cesium or rubidium, elements that had been hiding in plain sight, as it were, awaiting only the development of a sufficiently sensitive technique to bring them forth from obscurity. This demonstrated rather clearly that spectroscopy offered capabilities beyond those of traditional wet chemistry, particularly in the detection of elements present in very small concentrations. And the skeptics who had questioned the validity of spectroscopic identification found their objections increasingly difficult to maintain in the face of such concrete results. Gustav Kirchhoff, who served as Bunsen's close collaborator throughout these discoveries, played an essential role in the theoretical framework that made spectroscopic analysis possible. For it was Kirchhoff who had formulated the crucial principle that each element produces its own unique pattern of spectral lines, and who had demonstrated the connection between emission and absorption spectra that we touched upon in our earlier discussion. Without Kirchhoff's theoretical contributions, Bunsen's observations of colored lines in the spectroscope would have remained interesting curiosities without clear interpretation. But with the theoretical framework in place, these observations could be understood as definitive signatures of elemental identity, as reliable in their way as any fingerprint or other unique identifying mark. The partnership between Bunsen and Kirchhoff thus combined experimental skill and theoretical insight in a manner that proved extraordinarily productive, each man contributing abilities that complemented those of the other, and their joint work on spectral analysis stands as one of the more successful scientific collaborations of the 19th century. The practical implications of being able to detect elements through their spectral signatures extended well beyond the discovery of new elements, important though such discoveries were, for the technique also offered a means of detecting known elements with unprecedented sensitivity and in contexts where traditional methods might prove impractical or impossible. Bunsen demonstrated, for example, that spectroscopy could detect the presence of sodium in quantities far too small to be identified by any chemical test then available, and this sensitivity opened up possibilities for the analysis of rare minerals, meteorites, and other samples where only minute traces of certain elements might be present. The flame of Bunsen's burner, which had seemed at first to be merely a convenient tool for heating substances and vaporizing them for observation, proved to be a remarkably versatile excitation source that could coax luminous emissions from a wide variety of materials, each yielding its own characteristic spectral signature when viewed through the prism or diffraction grating of a properly constructed spectroscope. It is worth pausing for a moment to consider the broader significance of these discoveries in the context of the developing understanding of matter and its properties. For the detection of cesium and rubidium through spectroscopy raised questions that extended beyond the immediate practical applications of the technique. If each element produces its own unique pattern of spectral lines, as the evidence increasingly suggested, then there must be something about the internal structure of atoms that determines which wavelengths of light they are capable of emitting, and this in turn suggested that atoms might possess a more complex internal organization than the simple indivisible particles envisioned by the atomic theory in its earlier forms. These questions would not receive satisfactory answers until the 20th century, when the development of quantum theory finally provided a framework for understanding why atoms emit light at specific wavelengths rather than across a continuous range. But the observations made by Bunsen and Kirchhoff in those quiet Heidelberg laboratories helped to establish the empirical foundations upon which later theoretical advances would be built. The method by which Bunsen isolated his new elements deserves some further comment, for it illustrates the patience and methodical persistence that scientific investigation so often requires, even when the investigator has made an exciting preliminary observation that suggests the presence of something new and interesting. Having observed the blue lines of cesium in the Durkheim mineral water and the red lines of rubidium in lepidolite, Bunsen could not simply announce his discoveries and move on to other matters, but was obliged instead to undertake the laborious work of isolation and characterization that would transform his spectroscopic observations into properly established chemical facts. This meant evaporating enormous quantities of mineral water, separating the residues by precipitation and crystallization, testing the chemical properties of the concentrated materials, and gradually building up a body of evidence sufficient to convince even the most skeptical of his colleagues that the new elements were real and that spectroscopy was a valid method of discovery. The skepticism of chemists like Waller, though it may seem in retrospect to have been unnecessarily conservative, served an important function in the scientific process by ensuring that new methods and new claims were subjected to rigorous scrutiny before being accepted into the body of established knowledge. Wohlers' preference for wet chemical analysis reflected the accumulated experience of generations of chemists who had developed powerful and reliable techniques for identifying and quantifying the elements present in various substances, and it was not unreasonable for him to question whether a new technique based on the observation of colored light could really provide information as reliable as that obtained through careful chemical manipulation and gravimetric measurement. The burden of proof rested upon Bunsen and Kirchhoff to demonstrate that their spectroscopic methods were indeed trustworthy, and this they did through the careful documentation of their observations, the isolation of the new elements in quantities sufficient for chemical characterization, and the systematic comparison of spectroscopic results with those obtained by traditional methods wherever such comparison was possible. As the 1860s progressed, the validity of spectroscopic analysis became increasingly well established, and the technique found applications in an ever-widening range of scientific investigations. The discovery of cesium and rubidium had demonstrated that spectroscopy could reveal elements hidden in ordinary substances that had been examined many times before by conventional methods, and this suggested that other undiscovered elements might similarly be lurking undetected in minerals, ores, and other materials that merited spectroscopic examination. The search for new elements by spectroscopic means became a recognized field of investigation, and over the following decades, several more elements would be discovered through the characteristic spectral lines they produce, including thallium in 1861, indium in 1863, and eventually the noble gases helium, neon, argon, krypton, and xenon in the later decades of the century. The story of cesium and rubidium thus represents something of a turning point in the history of chemistry, marking the moment when spectroscopy established itself as a legitimate and powerful tool for elemental analysis and discovery. The blue lines that Bunsen observed in the Durkee mineral water and the red lines that appeared in the lepidolite samples were not merely pretty colored lights to be admired and then forgotten, but rather were the signatures of previously unknown elements, written in a language of wavelengths and frequencies that Bunsen and Kirchhoff had learned to read through their systematic investigations and careful theoretical analysis. The naming of these elements after colors, cesium for sky blue and rubidium for deep red, ensured that the spectroscopic origins of their discovery would remain part of their identity throughout all subsequent history, a permanent reminder of the role that light and color played in bringing these elements to the attention of the scientific world. In the gentle glow of a Bunsen flame, the alkali metals reveal themselves through their characteristic emissions: sodium with its bright yellow doublet, lithium with its crimson line, potassium with its violet emission, and now cesium and rubidium taking their places in the family with their blue and red signatures respectively. Each of these colors represents transitions of electrons between energy levels within the atoms, though Bunsen and Kirchhoff could not have known this at the time, working as they did before the discovery of the electron or the development of quantum theory. They knew only that each element produced its own pattern, as reliable and distinctive as a signature, and that this pattern could be used to identify the element's presence even in quantities too small for any other method of detection. This was knowledge enough to transform the practice of chemical analysis and to open new pathways for the discovery of elements that had previously escaped notice. In the early years of the 19th century, when natural philosophers were still piecing together the fundamental nature of light itself, a quiet observation was made that would eventually unlock the chemical secrets of the sun and stars. This observation concerned certain dark interruptions in the rainbow ribbon of sunlight, fine gaps where color seemed to be missing, and though it would take decades before these shadows were properly understood, their discovery marked the beginning of a profound journey toward comprehending the composition of objects impossibly distant from our earthly laboratories. The story begins not with the famous name most associated with these dark lines, but with an English physician and natural philosopher named William Hyde Wollaston, a man of considerable scientific accomplishment who, in the year 1802, noticed something peculiar when he allowed a narrow beam of sunlight to pass through a glass prism. Wollaston was examining the solar spectrum with careful attention, using a thin slit to admit the light rather than the round apertures that had been common in earlier experiments, and this methodological refinement allowed him to see details that had escaped previous observers. Where others had seen a continuous smear of color blending smoothly from red through orange and yellow and green to blue and violet, Wollaston perceived that this colored band was interrupted by several dark lines, narrow regions where the brightness of the spectrum seemed to fall away into shadow. He counted 7 of these dark divisions, positioned at various points across the spectrum, and he reported his observation to the Royal Society of London with the interpretation that seemed most natural to him at the time. Wollaston believed that these dark lines marked the true boundaries between the different colors, that they were somehow fundamental divisions separating one hue from the next in the same way that a fence might separate adjoining fields. This interpretation was reasonable given the state of knowledge in 1802, and it reflects how easy it is for even careful observers to fit unexpected phenomena into familiar frameworks. Wollaston did not pursue this observation further, did not measure the precise positions of these lines or attempt to explain their physical origin, and so his discovery remained a curious footnote, a detail noted but not understood. The dark lines waited in the spectrum, keeping their secrets for another dozen years, until a young German craftsman with extraordinary skill and patience would map them with unprecedented precision and thereby attach his name to them permanently, even though he too would fail to explain their true nature. This craftsman was Joseph von Fraunhofer, and his meticulous work at a glass-making establishment in Bavaria would transform a minor curiosity into one of the most important tools in the history of science. Joseph von Fraunhofer was born in 1800 and in the town of Straubing in Bavaria, the 11th child of a master glazier who died when Joseph was only 11 years old. The boy was apprenticed to a glassmaker and mirror manufacturer in Munich, where he endured harsh conditions and received little formal education, and his prospects seemed limited to a life of manual labor. However, fate intervened in a dramatic fashion when the building housing his master's workshop collapsed in 1801, trapping the young apprentice in the rubble. The rescue efforts attracted the attention of important figures, including the Elector of Bavaria himself, who took an interest in the surviving boy and provided him with money and patronage. This stroke of fortune allowed Fraunhofer to pursue his education and to develop his considerable talents for optical work, and by his early 20s he had joined the Optical Institute at Benedict Boyen, a former monastery in the Bavarian Alps that had been converted into a center for precision glassmaking and instrument manufacture. At Benedict Boyen, Fraunhofer found an environment perfectly suited to his gifts. The institute was dedicated to producing the finest optical glass in Europe, and Fraunhofer immersed himself in every aspect of the craft, from the chemistry of the glass melts to the mathematics of lens design to the practical techniques of grinding and polishing. He became exceptionally skilled at producing glass of remarkable purity and homogeneity, free from the bubbles and striations that plagued lesser manufacturers, and he developed new methods for creating prisms and lenses of unprecedented quality. It was this mastery of optical materials that enabled his spectroscopic discoveries, for the clarity of his prisms allowed him to see details in the spectrum that had been blurred and obscured in the instruments of his predecessors. Fraunhofer was not merely a craftsman, however, but a true experimental physicist who combined manual skill with theoretical understanding, and his investigation of the solar spectrum was motivated by practical concerns related to his work in optics. The immediate reason for Fraunhofer's spectroscopic studies was his need to measure the refractive properties of different types of glass with great accuracy. In order to design achromatic lenses that would bring all colors to the same focus and thereby eliminate the colored fringes that plagued simple lenses, it was necessary to know precisely how each type of glass bent light of different colors. For these measurements, Fraunhofer required standard reference points in the spectrum, fixed positions of known color that could be used to compare the behavior of different glass samples. The dark lines in the solar spectrum, once he had observed them, provided exactly such reference points, for they remained stationary even when the spectrum was spread more widely or compressed more narrowly by using prisms of different dispersive power. Their constancy made them ideal standards, reliable markers that could be used to calibrate optical instruments and to specify colors with scientific precision. In the year 1814, Fraunhofer began a systematic survey of these dark lines using equipment of his own design and manufacture. He set up a theodolite telescope, an instrument normally used for surveying and measuring angles with great precision, and fitted it with a prism of exceptional quality mounted before the objective lens. Sunlight was admitted through a narrow slit and passed through the prism, which spread it into a spectrum that could be examined through the telescope eyepiece at considerable magnification. The theodolite mounting allowed Fraunhofer to measure the angular positions of features in the spectrum with extraordinary accuracy, and he combined these measurements with detailed visual observations of the dark lines, noting their relative intensities, their widths, and their precise locations within the colored band. His prisms were superior to any that had been available to earlier investigators, and this optical quality, combined with his patient and methodical approach, revealed the spectrum in detail that no one had seen before. Where Wollaston had counted 7 dark lines, Fraunhofer ultimately mapped 574 distinct lines in the visible portion of the solar spectrum. Some of these were broad and prominent, easily visible even with modest equipment, while others were faint and narrow, requiring the finest optics and the most careful observation to detect. Fraunhofer assigned letters of the alphabet to the most conspicuous lines, beginning with the letter A for a prominent line in the deep red region of the spectrum and proceeding through B, C, D, E, F, G, H, and beyond into the violet. This labeling system proved so useful and became so widely adopted that it remains in use to this day, more than 2 centuries later, and when modern scientists refer to the sodium D lines or the hydrogen alpha line in the C position, they are using Fraunhofer's nomenclature. The lines themselves came to be known as Fraunhofer lines, a fitting tribute to the man who first charted their positions with scientific rigor, even though he could not explain their origin. Fraunhofer observed that the dark lines maintained exactly the same positions regardless of the direction from which the sunlight came, whether from the center of the solar disk or from its edges, and this suggested that they were somehow intrinsic to the sunlight itself rather than being produced by the Earth's atmosphere or by his optical apparatus. He also examined light from the Moon and planets and found the same lines, which made sense since moonlight and planetary light are merely reflected sunlight. When he turned his instruments to the stars, however, he discovered something remarkable. The spectra of bright stars such as Sirius and Castor showed dark lines, but these lines were arranged differently from those in the solar spectrum. The number and positions of the dark lines varied from star to star, suggesting that different stars possessed different chemical compositions or physical conditions. This was an astounding hint of what spectroscopy might reveal about the nature of celestial objects, though Fraunhofer himself did not live to see the full development of this insight. The reason for Fraunhofer's early death is a sobering reminder of the costs that scientific and industrial progress sometimes exact from those who labor to achieve them. Throughout his years at the glassworks, Fraunhofer was exposed to the fumes and vapors that accompanied the processes of glassmaking, including lead compounds and other toxic substances that were used as ingredients in optical glass and as materials in the polishing and grinding operations. These exposures damaged his lungs and undermined his health, and he developed tuberculosis, a disease that was already widespread in the 19th century but was certainly exacerbated by the irritation and injury caused by occupational exposures. Fraunhofer died in 1826 at the age of 39. His life cut short just as his reputation was reaching its peak and his instruments were being sought by observatories and laboratories across Europe. The epitaph on his grave reads simply that he brought the stars nearer, a poetic summary of his contributions to astronomy and optics, and his name lives on not only in the Fraunhofer lines but also in the Fraunhofer Institute, a major German research organization named in his honor. For more than 4 decades after Fraunhofer's death, the dark lines in the solar spectrum remained a mystery. Scientists knew they were there, could measure their positions with increasing precision, and used them as reference standards for optical work, but no one could explain why certain colors should be absent from sunlight. The breakthrough came in 1859, the same year that Charles Darwin published On the Origin of Species, when Gustav Kirchhoff, working with Robert Bunsen at the University of Heidelberg, demonstrated that the dark lines were caused by absorption. This discovery arose from their joint investigations of flame spectra, during which they had observed that the bright yellow line produced by sodium compounds corresponded exactly in position to the dark double line labeled D in the Fraunhofer spectrum. This coincidence seemed too precise to be accidental, and Kirchhoff devised an experiment to test whether there might be a connection between emission and absorption at the same wavelength. Kirchhoff's crucial experiment was elegantly simple in conception, though it required careful execution. He arranged for sunlight to pass through a flame containing sodium vapor before entering the spectroscope. If the sodium flame emitted yellow light at exactly the wavelength of the dark D line, one might expect that this emission would fill in the gap and brighten that region of the spectrum. Instead, Kirchhoff observed the opposite effect. The dark D line became even darker and more prominent when the sunlight passed through the sodium flame. The flame was absorbing light at exactly the same wavelength at which it was capable of emitting light, and this absorption was adding to whatever absorption had already occurred in the sun to produce the original dark line. This result was counterintuitive at first, for it seemed strange that a glowing flame should absorb rather than emit light. But Kirchhoff realized that the explanation lay in the temperature difference between the sodium flame and the solar surface. When Kirchhoff blocked the sunlight entirely and observed only the sodium flame, he saw the familiar bright emission lines in the yellow region of the spectrum. But when he combined the bright continuous light of the sun with the cooler sodium flame, the flame acted as an absorber rather than an emitter because it was cooler than the source of the continuous light. This led Kirchhoff to formulate a general principle: a substance that emits light of a particular wavelength when heated will absorb light of the same wavelength when it is cooler than the source of illumination. The dark lines in the solar spectrum, then, must be caused by cooler gases in the outer layers of the Sun's atmosphere absorbing light at specific wavelengths from the brighter, hotter layers beneath. Each dark line corresponded to a chemical element present in the solar atmosphere, and by matching the positions of the dark lines to the emission lines produced by elements in the laboratory, it became possible to determine what the Sun was made of without ever leaving the Earth. This was a profound achievement, for it meant that spectroscopy could serve as a tool for chemical analysis at any distance. The light from a star or nebula, analyzed through a spectroscope, would reveal the chemical elements present in that distant object just as clearly as if a sample had been brought into the laboratory. Kirchhoff and Bunsen quickly applied this principle to identify several elements in the solar atmosphere, including sodium, calcium, magnesium, iron, and chromium, and they noted the absence of certain elements that one might have expected to find. The technique could also be used in reverse, to discover new elements by observing emission lines that did not correspond to any known substance. And this approach led to the discovery of cesium and rubidium by Bunsen and Kirchhoff in 1860 and 1861 respectively. The era of spectroscopic analysis had begun, and within a few decades it would revolutionize both chemistry and astronomy. The understanding of the Fraunhofer lines that emerged from Kirchhoff's work tied together several previously separate strands of knowledge. The bright emission lines observed in flames and electric sparks were characteristic signatures of the chemical elements present in those sources. The dark absorption lines in the solar spectrum were the negative images of these same signatures, produced when light from a hotter source passed through cooler gases containing those elements. The exact correspondence between emission and absorption wavelengths was a fundamental property of matter, though the deeper reason for this correspondence, rooted in the quantum structure of atoms, would not be understood for another half-century. In the meantime, the empirical relationship was sufficient to launch the new science of astrophysics, the study of the physical and chemical properties of celestial objects through the analysis of their light. Fraunhofer's careful mapping of the solar spectrum had provided the foundation for all of this subsequent work. His letters for the prominent lines, his measurements of their positions, his observations that different stars showed different spectral patterns, all of these contributions remained valuable and relevant even after the physical explanation had been found. The young Bavarian craftsman who had been pulled from the rubble of a collapsed building and had risen to become the finest optical instrument maker of his age had left a legacy that extended far beyond his own lifetime and far beyond anything he could have imagined. The dark lines that bear his name continue to be studied and catalogued, with modern instruments revealing millions of distinct features in the solar spectrum, each one a message from the atoms and ions in the outer layers of our star. And the fundamental principle that Kirchhoff established, that emission and absorption occur at the same characteristic wavelengths, remains the cornerstone of spectroscopic analysis in laboratories and observatories around the world. The story of the Fraunhofer lines illustrates how scientific understanding often advances through a combination of careful observation, technological improvement, and theoretical insight. Wollaston saw the dark lines but misinterpreted them. Fraunhofer mapped them with unprecedented precision but could not explain their origin. Kirchhoff, building on the work of both predecessors and on his own studies with Bunsen, finally found the explanation that made sense of all the observations. Each contribution was necessary, and none alone was sufficient, and the full understanding emerged only from the accumulation of knowledge over more than 50 years. Such is often the way of science, a gradual and collective enterprise in which the insights of one generation become the starting points for the next, and in which patience and precision are rewarded in the end, even if the rewards come too late for some of the contributors to see them. Fraunhofer died too young, but his lines endure, dark markers in the rainbow of sunlight that tell us what the sun is made of, and that opened the door to understanding the chemistry of the cosmos. In the quiet months following the discovery of cesium and rubidium, Gustav Kirchhoff turned his attention away from the practical work of identifying new elements and toward something rather more abstract, though no less important. He wished to understand why the spectroscope worked at all, why certain substances emitted light at particular wavelengths while absorbing light at those very same wavelengths, and what fundamental principles govern the entire exchange of radiant energy between matter and the luminous vibrations that we perceive as light and heat. This contemplative turn, undertaken between 1859 and 1862, would yield 3 laws of spectroscopy that remain foundational to this day, and would open a door to theoretical questions about radiation that would occupy physicists for the next 4 decades, ultimately leading to discoveries that Kirchhoff himself could never have anticipated. The first of these laws concerns the simplest case one might imagine, that of a hot solid object or a gas compressed to sufficient density that its atoms or molecules interact frequently and intimately with one another. When such a body is heated until it glows, the light it produces, when passed through a prism or diffraction grating and spread into its component wavelengths, forms what Kirchhoff termed a continuous spectrum. This is to say that the resulting band of color contains every wavelength within the visible range, blending smoothly from deep reds through oranges and yellows into greens and blues and finally into the violet regions at the far end, with no gaps, no missing colors, and no discrete bright lines interrupting the gradual progression. The heated filament of a lamp, the glowing coals of a fire, the surface of molten iron in a crucible, and indeed the visible surface of the sun itself all produce continuous spectra of this general type, though the precise distribution of brightness across the different wavelengths varies according to the temperature of the source. A cooler glowing object appears predominantly red, while a hotter one shifts toward orange and yellow and eventually toward blue-white as its temperature increases. But in each case the spectrum remains continuous, without the distinctive gaps or bright lines that characterize other types of spectra. The second law addresses a different situation entirely, one in which a gas exists at low density and high temperature, with its constituent atoms or molecules sufficiently separated that they do not much interfere with one another's behavior. When such a rarefied hot gas is made to emit light, perhaps by passing an electrical discharge through it or by heating it in a flame, the resulting spectrum is not continuous at all but consists instead of discrete bright lines appearing at specific wavelengths against an otherwise dark background. These emission lines, as they came to be called, occur at positions characteristic of the particular element or compound producing them, and it was precisely this phenomenon that had allowed Kirchhoff and Bunsen to identify cesium and rubidium by the unique colored lines those elements produced when introduced into the flame of the spectroscope. Each each element possesses its own distinctive pattern of emission lines, a kind of luminous signature that remains constant regardless of how the element is heated or excited. And this consistency is what makes spectroscopic analysis so reliable and so useful for identifying the composition of substances both familiar and unknown. The third law completes the framework by describing what happens when a continuous spectrum, produced by a hot, dense source, passes through a cooler gas before reaching the observer. In this circumstance, the cooler gas absorbs light at precisely those wavelengths where it would emit light if it were itself hot enough to glow. The result is an absorption spectrum, which appears as a continuous band of color interrupted by dark lines at specific positions, each dark line corresponding to a wavelength that has been removed from the passing light by the intervening gas. This was exactly the phenomenon that Joseph von Fraunhofer had documented so carefully half a century earlier when he catalogued the dark lines in the solar spectrum, and Kirchhoff now understood that those lines were produced by cooler gases in the outer atmosphere of the Sun absorbing specific wavelengths from the continuous spectrum generated by the hotter solar surface beneath. The wavelengths at which a given element produces absorption lines are identical to the wavelengths at which that same element produces emission lines, a correspondence that is both remarkable and deeply significant, and which Kirchhoff set about demonstrating through careful experimentation and theoretical reasoning. These three laws, taken together, provided a comprehensive description of how matter and radiant energy interact under different conditions of temperature and density, and they gave investigators a reliable framework for interpreting the spectra of any source they might wish to study. But Kirchhoff was not content merely to catalogue these empirical regularities. He wished to understand them at a more fundamental level, to discover what underlying principles connected the ability of a substance to emit light with its ability to absorb light, and whether there existed some universal relationship governing this connection. His investigations along these lines led him to one of the most important theoretical insights of 19th-century physics, an insight that would prove essential to the eventual development of quantum theory several decades later. The central question Kirchhoff posed to himself was deceptively simple in its formulation. If a body at a given temperature both emits and absorbs radiant energy, what is the relationship between its emissive power, which measures how much energy it radiates at each wavelength, and its absorptive power, which measures what fraction of incident radiation at each wavelength it absorbs rather than reflects or transmits? Through a series of elegant thought experiments involving enclosed cavities and the exchange of radiation between different surfaces, Kirchhoff demonstrated that the ratio of emissive power to absorptive power must be the same for all bodies at the same temperature, regardless of their composition, their color, their texture, or any other particular property they might possess. This result is both profound and somewhat counterintuitive, for it tells us that a good absorber must also be a good emitter, and a poor absorber must be a poor emitter, with the balance between these two capacities governed by a universal function that depends only on the temperature and the wavelength of the radiation in question. To arrive at this conclusion, Kirchhoff imagined an enclosure whose walls were maintained at a uniform temperature throughout, with no sources of energy other than the thermal radiation exchanged between the surfaces. He considered what would happen if two different materials, possessing different emissive and absorptive properties, were placed within such an enclosure and allowed to come into thermal equilibrium with their surroundings. If the ratio of emissive to absorptive power were not the same for both materials, he reasoned, then one would emit more radiation than it absorbed while the other absorbed more than it emitted, and this imbalance would cause a net flow of energy from one body to the other. But such a flow would violate the laws of thermodynamics, for it would allow heat to pass spontaneously from a cooler body to a warmer one, or would enable the creation of perpetual motion through the conversion of thermal energy into organized work without any corresponding increase in entropy elsewhere. Since such violations are forbidden by the fundamental principles of thermodynamics, the ratio of emissive to absorptive power must indeed be identical for all materials at the same temperature, a conclusion now known as Kirchhoff's law of thermal radiation. This universal ratio, which Kirchhoff denoted with a function depending on wavelength and temperature, represents the emissive power of an ideal body that absorbs all radiation falling upon it, reflecting nothing and transmitting nothing. Such a body, which absorbs perfectly at all wavelengths, would appear completely black when cold, since it would reflect no light to the eye, and Kirchhoff therefore termed it a perfectly black body, or simply a black body. The radiation emitted by such an ideal absorber when heated to any given temperature would depend only on that temperature and on the wavelength in question, following a universal function that Kirchhoff recognized must exist even though he could not himself determine its precise mathematical form. The challenge of discovering this universal function, which describes how the intensity of black body radiation varies with wavelength and temperature, became one of the central problems of theoretical physics in the decades following Kirchhoff's work, attracting the attention of many of the finest minds in Europe and ultimately leading to revolutionary developments at the turn of the century. The concept of the perfectly black body, introduced by Kirchhoff in 1860, might seem at first an abstraction of limited practical relevance, since no real material absorbs all incident radiation with perfect completeness. But Kirchhoff showed that such an ideal absorber could be approximated with remarkable accuracy by a simple device, namely a cavity or enclosure with a small opening through which radiation could enter and exit. When radiation enters such a cavity through its small aperture, it reflects multiple times from the interior walls before eventually escaping, and with each reflection some fraction is absorbed. If the aperture is sufficiently small relative to the size of the cavity, radiation entering has very little chance of escaping again before being absorbed, and the opening therefore behaves very nearly as a perfect absorber. Conversely, when such a cavity is heated, the radiation emerging from the aperture is very nearly that of an ideal black body, depending only on the temperature and not on the particular material from which the cavity walls are constructed. This realization provided experimentalists with a practical means of producing and studying black body radiation, and such cavity radiators became essential tools in the precision measurements of thermal radiation that occupied physicists in the subsequent decades. The influence of Kirchhoff's work extended far beyond the immediate context of spectroscopy and the identification of elements. His demonstration that a universal function must govern black body radiation posed a challenge that attracted some of the most distinguished theoretical physicists of the era, each seeking to derive the form of this function from fundamental principles. In 1879, Joseph Stefan in Vienna showed experimentally that the total energy radiated by a black body increases very rapidly with temperature, being proportional to the fourth power of the absolute temperature. 5 years later, Ludwig Boltzmann provided a theoretical derivation of this result using thermodynamic arguments, establishing what is now called the Stefan-Boltzmann law and demonstrating the power of thermodynamic reasoning applied to problems of radiation. Wilhelm Wien in Berlin made further progress in the 1890s, deriving a displacement law that describes how the wavelength of maximum emission shifts toward shorter wavelengths as the temperature increases, and proposing a formula for the full distribution of black body radiation that agreed well with measurements at short wavelengths but failed at longer wavelengths in the infrared region. The ultimate resolution of this problem came in 1900, when Max Planck, also working in Berlin, discovered the correct formula for the black body spectrum by introducing the revolutionary hypothesis that energy is emitted and absorbed not continuously but in discrete units or quanta, with the size of each quantum proportional to the frequency of the radiation. This hypothesis, which Planck himself initially regarded as a mathematical device rather than a description of physical reality, marked the beginning of quantum theory and transformed our understanding of the interaction between matter and radiation at the most fundamental level. None of this could have occurred without Kirchhoff's foundational work, for it was Kirchhoff who first demonstrated that a universal function must exist, who introduced the concept of the black body, and who thereby defined the problem that Planck eventually solved through means that no one in the 19th century could have anticipated. Beyond its influence on the development of radiation theory, Kirchhoff's spectroscopic work achieved something of enormous significance for our understanding of the cosmos. By demonstrating that the absorption lines in the solar spectrum are produced by elements present in the Sun's atmosphere, and by showing that these elements produce exactly the same spectral signatures as samples of those elements studied in terrestrial laboratories, Kirchhoff established for the first time that the Sun and the Earth are composed of the same kinds of matter, governed by the same physical and chemical laws. This might seem obvious to us now, but in the middle of the 19th century it was far from certain. The Sun was unimaginably distant and inaccessible, its composition utterly unknown, and there was no a priori reason to assume that celestial bodies were made of the same substances as terrestrial rocks and metals. The spectroscope, wielded according to the laws that Kirchhoff had formulated, revealed that hydrogen, sodium, iron, calcium, magnesium, and many other familiar elements were present in the solar atmosphere, producing absorption lines at exactly the wavelengths where those elements absorb light in laboratory experiments. This unification of terrestrial and celestial chemistry was one of the great intellectual achievements of the 19th century, transforming astronomy from a science of positions and motions into a science capable of determining the physical composition and conditions of objects at any distance, provided only that their light could be collected and analyzed. The same methods that revealed the composition of the Sun could be applied to the stars, to nebulae, to comets, and eventually to galaxies beyond our own, extending human knowledge across distances so vast that no traveler could ever hope to cross them, yet accessible to the patient observer with a spectroscope and the understanding that Kirchhoff had provided. In this way, the quiet theoretical work of a German physicist in the early 1860s opened up the universe to chemical investigation, making it possible to know what the stars are made of without ever leaving the Earth. The three laws of spectroscopy, together with the deeper theoretical insights about radiation and absorption that accompanied them, represent Kirchhoff's lasting contribution to physics and astronomy. They remain as valid today as when he first formulated them, taught to students in introductory courses and applied routinely in research laboratories and observatories around the world. The gentle glow of heated objects, the bright lines of excited gases, the dark absorption features in stellar spectra, all continue to be understood through the framework that Kirchhoff established, a framework that has proven robust enough to accommodate the revolutionary developments of quantum mechanics while remaining accessible to anyone willing to learn its basic principles. As you rest and listen to these words, perhaps you might take some comfort in the thought that the light from distant stars, traveling for years or centuries or millennia before reaching your eyes, carries within it information about the very atoms from which those stars are made, information that becomes legible through the laws that Kirchhoff discovered in his quiet study more than 160 years ago. in the quiet of a London evening. In the year 1863, a man named William Huggins stood in his private observatory, which he had built upon the grounds of his home in Tulse Hill, a peaceful suburb to the south of the city, and he turned his telescope toward the stars with a new purpose, one that would forever change our understanding of the distant suns that pepper the night sky. Huggins was not, by training, a professional astronomer, but rather a gentleman of independent means who had sold his family's silk and linen business some years earlier in order to devote himself entirely to the study of the heavens. And on this particular evening, as on many evenings before and after, he was accompanied by a wedge of glass, a prism, which he had attached to his telescope in such a manner that the light from a star, instead of forming a simple point of brightness, would be spread out into a ribbon of color, a spectrum, much like the rainbow that forms when sunlight passes through a crystal decanter left upon a windowsill. The idea of examining starlight through a prism was not entirely new, for others had glimpsed the spectra of bright stars in years past. But what Huggins proposed to do, and what he would accomplish with remarkable success, was to compare the dark lines that appeared in these stellar spectra with the bright lines produced by chemical elements when heated in a laboratory flame, thereby identifying, for the very first time, the actual substances present in stars that lay at distances so vast that the human mind could scarcely comprehend them. This endeavor required not only astronomical skill but also chemical expertise, and so Huggins sought a collaborator, finding one in William Allen Miller, a professor of chemistry at King's College London, who was himself deeply interested in the application of spectroscopy to chemical analysis and who brought to their partnership a rigorous understanding of the spectral signatures that various elements produced when examined under controlled conditions. Together, Huggins and Miller set about the painstaking work of comparing stellar spectra with laboratory spectra, a process that required great patience and careful observation, for the light from even the brightest stars, when spread into a spectrum, becomes exceedingly faint, and the dark lines within that spectrum, the absorption lines that Fraunhofer had first catalogued in sunlight decades earlier, appear as mere whispers of darkness against an already dim background. They began with the star Aldebaran, that reddish beacon in the constellation of Taurus, and through many nights of careful measurement, they identified within its spectrum the characteristic lines of hydrogen, of sodium, of magnesium, and of iron, among other elements, demonstrating beyond reasonable doubt that this distant sun, separated from our own by a gulf of space that light itself takes decades to cross, was composed of the very same substances that could be found here upon the Earth. This was a finding of profound importance, for it suggested a unity of composition throughout the universe, a cosmic kinship between our small world and the countless stars that had seemed, until that moment, forever beyond the reach of human inquiry. The method that Huggins and Miller employed was straightforward in principle, though demanding in execution. They would first observe a star through the spectroscope, noting carefully the positions of the dark lines that crossed its spectrum, and then they would observe the spectrum produced by a particular element when heated in a flame or sparked between electrodes, comparing the positions of the bright emission lines thus produced with the dark absorption lines in the star. When a match was found, when the bright laboratory line fell precisely at the same position as a dark stellar line, they could conclude with confidence that the element in question was present in the atmosphere of the star, absorbing light at that particular wavelength as the stellar radiation passed through the cooler outer layers on its journey toward Earth. In this way, chemistry and astronomy, two sciences that had previously seemed quite separate in their concerns, were united in the new discipline that would come to be called astrophysics, the study of the physical and chemical nature of celestial bodies, and William Huggins, working quietly in his suburban observatory with his chemical colleague, became one of its founding practitioners. The collaboration between Huggins and Miller was highly productive, and their joint paper of 1863, presented to the Royal Society, announced their identification of several elements in the spectra of multiple stars, establishing the methodology that would be employed and refined by astronomers for generations to come. William Allen Miller brought to the partnership his expertise in chemical spectroscopy and his familiarity with the characteristic spectral signatures of numerous elements, while Huggins contributed his astronomical skill, his dedicated observatory, and his patient willingness to spend night after night at the eyepiece, slowly accumulating the observations upon which their conclusions rested. Miller had previously conducted extensive spectroscopic studies of chemical compounds and had written authoritatively on the subject, making him an ideal partner for this astronomical application of spectroscopic methods, and the two men worked together with a collegiality that served their shared scientific goals admirably. At roughly the same time, across the European continent in the city of Rome, another observer was turning his attention to the spectra of stars, approaching the subject with a slightly different purpose and achieving results that would prove equally significant in their own way. This observer was Angelo Secchi, a Jesuit priest and astronomer who directed the observatory at the Roman College, and who, from 1863 through 1868, undertook a comprehensive survey of stellar spectra, examining several thousand stars and grouping them into categories based upon the appearance of their spectral features. Secchi worked from the Vatican Observatory with dedication and systematic rigor, and through his observations he came to recognize that stars, despite their apparent individuality, could be sorted into a relatively small number of spectral types, each type characterized by particular patterns of absorption lines and by an overall color that reflected the temperature of the stellar surface. Secchi's classification scheme divided stars into 4 main types, later expanded to 5 with the addition of a class for certain unusual red stars. The first type comprised white and blue-white stars whose spectra were dominated by strong hydrogen lines, stars such as Sirius and Vega that shine with a brilliant clarity in the night sky. The second type included yellow stars like our own Sun, whose spectra displayed numerous fine lines corresponding to various metals, a dense forest of absorptions that spoke to the rich chemical complexity of their atmospheres. The third type encompassed orange and red stars with broad, dark bands in their spectra, bands that would later be understood to arise from molecules rather than individual atoms, indicating cooler stellar surfaces where atoms could combine into more complex structures. And the fourth type consisted of deep red stars with similar banding but shifted in its arrangement, stars that were cooler still and that represented, though this was not yet understood, a different chemical composition or a different stage of stellar evolution. This classification of stars into spectral types was an organizational achievement of considerable importance, for it imposed order upon what had seemed a bewildering variety, suggesting that underlying physical principles governed the appearances of stellar spectra and that by understanding those principles one might come to comprehend the nature of the stars themselves. Secchi observed tirelessly, cataloguing star after star, and his system of classification, though it would later be revised and refined as understanding deepened, laid the groundwork for all subsequent schemes of stellar taxonomy, including the Harvard classification system that would emerge toward the end of the 19th century and that remains, in modified form, in use to this day. The priest astronomer, working within the ancient walls of the Vatican, thus contributed fundamentally to the young science of astrophysics, demonstrating that spectroscopy could be used not only to identify elements in individual stars, but also to organize the stars themselves into meaningful categories that invited further investigation and explanation. Returning now to William Huggins in his Tulse Hill Observatory, we may follow him as he turned his spectroscope, in the year 1864, toward an object quite different from the point-like stars he had been examining, an object that appeared through the telescope not as a sharp dot of light but as a diffuse, glowing cloud, a nebula, specifically the Great Nebula in the constellation of Orion, that spectacular region of light and shadow visible to the unaided eye as a faint smudge below the three stars of Orion's belt. The nature of nebulae was at this time a subject of considerable uncertainty, for while some astronomers believed them to be vast collections of stars, clusters so distant that individual stellar points could not be resolved, others suggested that they might be clouds of luminous gas, extended bodies of an entirely different character from the stars that populated the sky around them. The question was not merely academic, for it touched upon fundamental issues of cosmic structure and the processes by which celestial bodies might form and evolve. When Huggins directed his spectroscope toward the Orion Nebula on that evening in 1864, he observed something that immediately settled the question for this particular object, and that something was profoundly revealing. Instead of the continuous spectrum crossed by dark absorption lines that characterized stellar light, the nebula produced a spectrum consisting of only a few bright emission lines, isolated bands of color against a dark background, with no continuous rainbow whatsoever. This was the signature of a glowing gas, a cloud of rarefied matter that emitted light at specific wavelengths determined by the atoms of which it was composed, rather than the dense, hot surface of a star that radiated light across the entire visible spectrum. Huggins had demonstrated, through the simple act of spreading the nebula's light with a prism, that the Orion Nebula was not a distant star cluster, not a congregation of unresolved suns, but a true cloud of gas, luminous and extended, floating in the depths of space. This discovery opened a new chapter in astronomical understanding, for it revealed that the universe contained, in addition to stars and planets, vast reservoirs of gaseous matter, clouds that glowed with their own light and that might, as some theorists had speculated, serve as the raw material from which new stars could form. The emission lines that Huggins observed in the nebula's spectrum included lines that could be matched to hydrogen, which was not surprising, but also a bright green line that corresponded to no element known in terrestrial laboratories, a mysterious emission that would puzzle astronomers for many decades and that would eventually be attributed not to a new element, as some proposed, but to a familiar element, oxygen, existing under conditions of extreme rarefaction that could not be reproduced on Earth, conditions that allowed forbidden atomic transitions to occur that would never be observed in the denser environments of laboratory experiments. 4 years later, in 1868, Huggins achieved another remarkable result, one that demonstrated a different application of spectroscopic methods and that would prove of immense value in understanding the motions of celestial bodies. By carefully measuring the positions of absorption lines in the spectrum of the star Sirius, the brightest star in the night sky, and comparing them to the positions of the same lines as produced by sources in his laboratory, Huggins detected a small but measurable shift, a displacement of the stellar lines toward the red end of the spectrum that indicated, according to the principle that Christian Doppler had described some decades earlier, that Sirius was moving away from the Earth. This was the first measurement of a star's radial velocity, its speed of approach or recession along the line of sight, And while the value that Huggins obtained was not precisely correct, limited as he was by the technology of his time, the method itself was sound and would be refined by later astronomers to yield ever more accurate determinations of stellar motions, motions that would eventually reveal the rotation of galaxies, the expansion of the universe, and a host of other cosmic phenomena. Throughout these years of productive observation and discovery, William Huggins did not work entirely alone, for alongside him, often uncredited and unacknowledged in the formal publications of the day, labored his wife, Margaret Lindsay Huggins, née Murray, a woman of considerable scientific ability and dedication who contributed substantially to the research conducted at the Tulse Hill Observatory. Margaret had been interested in astronomy and spectroscopy before her marriage to William in 1875, having educated herself in these subjects through reading and personal study, and after their union she became his constant collaborator, sharing in the nightly observations, assisting with the complex equipment, and participating in the analysis and interpretation of results. She was particularly skilled in the photographic techniques that became increasingly important in spectroscopic work as the century progressed, and her contributions extended to the writing and illustration of their published papers. Yet the conventions of the era ensured that her name appeared far less often than it deserved in the scientific record, a reflection of broader social attitudes toward women in science that would only slowly change in the decades to come. Margaret Lindsay Huggins possessed a genuine passion for the work she shared with her husband, and the letters and notebooks that survive from their collaboration reveal her as an engaged and thoughtful participant rather than merely an assistant who followed instructions. She maintained meticulous records, operated delicate instruments with skill, and contributed ideas to the research program that the couple pursued together for over 3 decades. In later years, William Huggins himself acknowledged her contributions more openly, and the couple's joint work on stellar spectroscopy was eventually published under both their names, a belated recognition of a partnership that had been genuinely collaborative from the start. The story of Margaret Lindsay Huggins serves as a reminder that the history of science, as recorded in formal publications and institutional records, does not always capture the full range of individuals who contributed to the advancement of knowledge, particularly when those individuals were women working in an era that did not readily grant them professional recognition. Across the Atlantic Ocean, in the city of New York, another observer was making significant contributions to the young field of spectroscopy, bringing to it both innovative equipment and a pioneering application of photography that would prove essential to the discipline's future development. This observer was Lewis Morris Rutherford, a lawyer by training who had retired from legal practice to pursue his interests in astronomy and physics, and who, beginning in 1862, devoted himself to the spectroscopic study of stars and other celestial objects from his private observatory on 2nd Avenue in Manhattan. Rutherford was particularly concerned with the design and construction of spectroscopic apparatus, and he developed equipment of exceptional quality, including diffraction gratings ruled with great precision that could spread light into spectra with sharpness and clarity superior to that achieved by many of his contemporaries. Rutherford recognized early the potential of photography for recording spectra, and he worked to adapt the photographic techniques of his day to the demanding requirements of astronomical spectroscopy, where the light to be recorded was often exceedingly faint and the exposure times correspondingly long. He photographed the spectra of the Sun, the Moon, and several bright stars, producing permanent records that could be examined at leisure in the daylight hours and measured with precision using micrometers and other instruments. These photographs allowed for more accurate determination of spectral line positions than visual observation alone could provide, and they freed the astronomer from the limitations of memory and real-time perception, creating an objective record that could be shared, compared, and re-examined as understanding deepened. Rutherford's stellar photographs from the 1860s were among the earliest attempts to apply photography systematically to spectroscopic research, and while the techniques would be greatly refined in the decades to come, he deserves recognition as a pioneer in a methodology that would transform the practice of astrophysics. In addition to his spectroscopic work, Rutherford also applied his photographic skills to the broader project of stellar cartography, producing photographs of star fields that could be measured to determine the precise positions of stars with an accuracy superior to traditional visual methods. He developed specialized telescope optics designed specifically for photographic work, recognizing that the requirements for photography differed from those for visual observation, and his innovations in this area influenced the design of astronomical instruments for years to come. Working largely in isolation from the European centers of astronomical research, Rutherford demonstrated that significant contributions to the science could be made from the New World, and his carefully crafted equipment, some of which remained in use long after his death, stood as testimony to the value of precision craftsmanship in scientific instrumentation. The years from 1859 to the late 1860s thus witnessed a remarkable expansion in the scope and ambition of spectroscopic astronomy, as observers in London, Rome, New York, and elsewhere directed their prisms and gratings toward the heavens and demonstrated that the light of stars and nebulae could reveal not only the presence of familiar chemical elements, but also the physical state of distant matter and the motions of celestial bodies through space. The work was painstaking and often tedious, requiring long hours at the telescope, careful maintenance of complex equipment, and the patient accumulation of observations that, individually, might seem unremarkable but that, taken together, built an ever clearer picture of the universe beyond our atmosphere. The observers themselves were a varied group, including professional scientists and dedicated amateurs, men and women, priests and lawyers, all united by their fascination with the information encoded in the colored light that reached the Earth after journeys of months or years or centuries through the emptiness of space. And so, as the century progressed toward its final decades, the foundations of astrophysical spectroscopy were firmly laid, ready to support the great edifice of stellar and nebula science that would rise upon them in the years to come. The instruments that allowed scientists to peer into the hidden nature of light evolved gradually, each generation of spectroscope building upon the insights and limitations of what came before, and the story of these instruments is itself a quiet narrative of patience and ingenuity, of glassmakers and metalworkers and astronomers all contributing their particular skills to the shared endeavor of understanding how matter and light converse with one another across the distances of space and the intimate proximities of the laboratory bench. In the beginning, which is to say in the years just before 1860, the spectroscope was a relatively simple arrangement, though simple here should not be taken to mean crude or ineffective, for even the earliest instruments were capable of revealing the distinct colored lines that would revolutionize our understanding of chemistry and physics, and the simplicity was rather a mark of elegance, of achieving much with carefully chosen components arranged in just the right configuration to separate white light into its constituent wavelengths and present them to the waiting eye of the observer. The original spectroscope designed by Robert Bunsen and Gustav Kirchhoff at Heidelberg consisted of three essential parts that would remain, in one form or another, at the heart of spectroscope design for many decades to come, and these were the collimator tube through which light entered the instrument, the prism that performed the actual work of dispersing the light into its spectrum, and the telescope through which the observer viewed the resulting ribbon of colors marked by bright or dark lines depending on whether one was examining an emission or absorption spectrum. The collimator tube was a modest cylinder, blackened on the inside to prevent stray reflections, with a narrow adjustable slit at its outer end through which light from the source under examination could enter, and at its inner end a lens that rendered the diverging rays parallel, for it was essential that the light striking the prism consisted of parallel rays if the resulting spectrum was to be sharp and well-defined rather than blurred and indistinct, and the width of the slit could be adjusted by means of a fine screw mechanism, narrower slits producing sharper spectral lines at the cost of admitting less light, a trade-off that the observer learned to balance according to the brightness of the source and the fineness of detail required. The prism itself sat upon a small rotating table at the center of the instrument, and in the original Kirchhoff and Bunsen design this was a single prism of flint glass, a type of glass chosen for its relatively high refractive index and its consequent ability to spread the spectrum over a wider angle than ordinary crown glass would permit, and the prism table could be rotated to bring different portions of the spectrum into the field of view of the telescope. Though in later and more sophisticated instruments this rotation would be calibrated and fitted with scales and verniers to allow precise measurement of the angular deviation corresponding to each wavelength. The telescope arm extended from the prism table at an angle determined by the refractive properties of the prism and the wavelength being observed, and through this telescope the observer gazed upon the spectrum, seeing the familiar progression from red through orange and yellow and green to blue and violet, and superimposed upon this continuous background, when examining heated gases or vapors, the bright-colored lines that announced the presence of particular elements: sodium with its distinctive yellow doublet, potassium with its lines in the red and violet, lithium with its crimson signature, and so on through the growing catalogue of elemental spectra. What made the Kirchhoff and Bunsen instrument particularly useful for analytical chemistry was the incorporation of a comparison prism, a small auxiliary prism positioned just in front of the slit in such a manner that the observer could view two spectra simultaneously, one above the other in the field of view, and this arrangement allowed the chemist to compare directly the spectrum of an unknown substance with the spectrum of a known reference material, aligning the two and noting which lines coincided and which did not. And this side-by-side comparison eliminated the uncertainties of memory and the difficulties of describing the precise position of a spectral line in words or numbers, for the eye could judge coincidence with great sensitivity, detecting mismatches that would have been difficult to quantify in any other way. The comparison prism was a small right-angled prism of glass, positioned so that light from a second source, typically a flame containing a known element, entered through its hypotenuse face and was reflected by total internal reflection at its rear face, emerging to pass through the upper portion of the collimator slit while light from the unknown source passed through the lower portion, and thus two spectra appeared in the eyepiece, neatly arranged for comparison. And this simple optical trick proved enormously valuable in the practical application of spectroscopy to chemical analysis, allowing rapid and reliable identification of elements in samples ranging from minerals to biological tissues to the waters of mineral springs. As spectroscopy developed and its applications multiplied, there arose a need for instruments of greater resolving power, capable of distinguishing spectral lines that lay very close together in wavelength, and this need drove the development of spectroscopes with multiple prisms arranged in series, each prism adding its dispersive effect to that of its predecessors, so that a train of 3 or 4 or even 5 prisms could spread the spectrum over a much greater angle than any single prism could achieve. And such instruments, though cumbersome and demanding in their adjustment, allowed observers to discern fine details of spectral structure that simpler instruments could not reveal. There was, however, an alternative path to high resolution that did not depend upon prisms at all, and this was the diffraction grating, a device that exploited the wave nature of light to produce spectra of exceptional purity and mathematical precision. And while diffraction gratings had been known since the early 19th century, it was not until the 1870s and 1880s that they became truly practical tools for precision spectroscopy. And the person most responsible for this development was Henry Augustus Rowland, a physicist at the Johns Hopkins University in Baltimore, whose work on ruling concave gratings transformed the field and made possible measurements of wavelength accurate to parts in a million. A diffraction grating consists of a surface upon which a great many parallel grooves have been ruled, closely and evenly spaced, and when light falls upon this ruled surface it is diffracted, each groove acting as a source of wavelets that interfere with one another, reinforcing at certain angles and cancelling at others, with the result that different wavelengths are sent off in slightly different directions, producing a spectrum. And the more grooves per unit length, the greater the angular separation between wavelengths and the higher the resolving power of the grating. But ruling such gratings with the necessary uniformity and straightness was a task of extraordinary difficulty, for any irregularity in the spacing or depth of the grooves would introduce false lines or ghosts into the spectrum, corrupting the very measurements the grating was meant to enable. Rowland addressed this challenge with characteristic thoroughness, designing and building a ruling engine of unprecedented precision at Johns Hopkins, a massive machine mounted on a brick pier sunk into the earth to isolate it from vibrations, with a diamond point that traced grooves across the surface of a metal blank advanced by a screw so accurate that its errors were measured in millionths of an inch. And with this engine Rowland ruled gratings of remarkable quality, eventually achieving densities of 14,000 lines per inch and higher. And the spectra produced by these gratings revealed details invisible to any prism spectroscope, including the fine structure of spectral lines and the subtle patterns that would later be explained by quantum theory. Rowland's particular innovation was the concave grating, in which the grooves were ruled not upon a flat surface but upon a concave mirror. And this arrangement offered the immense advantage of eliminating the need for separate collimating and focusing lenses, for the concave surface itself focused the diffracted light, and since the light did not pass through any glass, there was no absorption of ultraviolet or infrared wavelengths, making the concave grating ideal for exploring spectral regions invisible to the eye. And Rowland mounted his gratings in a configuration that came to be known as the Rowland circle, a geometrical arrangement in which both the grating and the photographic plate recording the spectrum lay on the circumference of a circle whose diameter equaled the radius of curvature of the grating. And by sliding the plate holder along this circle, different portions of the spectrum could be brought into focus. Photography had entered spectroscopy some years before Rowland's work on gratings, and the introduction of photographic recording represented another quiet revolution in the capabilities of spectroscopic instruments, for the photographic plate could accumulate light over long exposures, revealing faint lines invisible to the eye in real time, and it provided a permanent record that could be measured and remeasured at leisure, compared with other plates, published and shared among researchers, and examined with magnifying lenses or projection apparatus to extract the maximum information from each observation. Henry Draper, an American physician and astronomer working at his private observatory in Hastings-on-Hudson, New York, was among the pioneers of this technique, and in 1872 he succeeded in photographing the spectrum of the bright star Vega, capturing on a glass plate coated with wet collodion emulsion the pattern of absorption lines that revealed the chemical composition of that distant sun. And this achievement marked the beginning of astrophysical spectroscopy as a quantitative science. For now the spectra of stars could be studied with the same care and precision as spectra produced in the laboratory, and the photographic record made it possible to survey and classify the spectra of thousands of stars. Work that would eventually lead to our modern understanding of stellar evolution and the life cycles of suns. The sensitivity of photographic emulsions was initially quite limited, with early plates responding primarily to blue and violet light and recording red and yellow wavelengths only weakly or not at all. And this limitation meant that the photographic record of a spectrum was incomplete, biased toward the short wavelength end. And Hermann Karl Vogel, working at the Potsdam Astrophysical Observatory in Germany, devoted considerable effort to improving this situation, experimenting with dyes that could be added to photographic emulsions to extend their sensitivity toward longer wavelengths. And these orthochromatic and eventually panchromatic emulsions made possible the photographic recording of complete spectra from the near ultraviolet through the visible range and into the near infrared, greatly expanding the information that could be extracted from each exposure. Vogel's work at Potsdam was part of a broader effort to transform spectroscopy from an art practiced by skilled individuals into a systematic science with standardized methods and instruments. And this effort found commercial expression in the products of instrument makers such as Adam Hilger Limited of London, a company that came to dominate the market for high-quality spectroscopic apparatus in the late 19th and early 20th centuries, producing instruments of consistent quality that could be purchased and put to work without the years of experience in glass grinding and metalworking that had previously been necessary to construct a capable spectroscope. The Hilger spectroscopes came in many forms, from small direct vision instruments suitable for fieldwork to large laboratory spectrographs with automatic wavelength drives and precision measuring microscopes for reading photographic plates. And the availability of these commercial instruments democratized spectroscopy, making it accessible to university teaching laboratories and industrial quality control facilities, as well as the elite research institutes where the technique had originated. And generations of students learned the principles of atomic spectra by peering through Hilger instruments at the colored lines of hydrogen and sodium and mercury, watching the spectrum shift as they turned the calibrated drum that rotated the prism or grating. The direct vision spectroscope mentioned a moment ago deserves particular attention, for it represented an ingenious solution to the problem of portability and convenience. And the credit for this design belongs to Giovanni Battista Amici, an Italian optician and naturalist working in Florence, who conceived the idea of combining prisms of different glasses in such a way that their dispersive effects would add together while their deviating effects would cancel, so that the spectrum would be spread out in a fan of colors while the central ray passed straight through the system without being bent to one side. And this meant that one could look through the spectroscope directly at a light source, holding the instrument to the eye like a small telescope, and see the spectrum superimposed upon or adjacent to the image of the source itself. Amici's direct vision spectroscope used a train of prisms alternating between crown and flint glass, typically 3 or 5 prisms cemented together in a compact unit. And while the resolving power of such an instrument was modest compared to large laboratory spectroscopes with their collimators and telescope arms and finely adjusted slit mechanisms, the convenience was considerable, and the direct vision spectroscope found wide use among chemists testing for adulterants in food and drink, geologists examining minerals in the field, and astronomers making quick surveys of stellar spectra before committing to the long exposures required for photographic work. The development of spectroscope design was not a matter of sudden leaps and revolutionary inventions so much as a gradual accumulation of refinements, each improvement building upon those that came before, and the result by the end of the 19th century was a mature technology capable of measurements that would have seemed miraculous to Newton or even to Fraunhofer. Wavelengths determined to 6 or 7 significant figures. Spectral lines resolved that lay so close together their separation was measured in fractions of an angstrom. And photographic surveys of stellar spectra numbering in the hundreds of thousands, all made possible by the patient work of those who designed and built and improved the instruments through which light revealed its secrets. The arrangement of collimator tube and prism table and telescope arm, established by Kirchhoff and Bunsen in those early days at Heidelberg, remained the fundamental architecture of the dispersive spectroscope, varied and elaborated but never entirely abandoned, and even the diffraction grating instruments of the Rowland school retained the essential geometry of a source, a dispersing element, and a means of observation, whether eye or photographic plate or, in later years, electronic detector, and this continuity of design reflected the fundamental nature of the task, which was always to separate light by wavelength and to record or observe the result with the greatest possible precision and sensitivity. As you rest now, you might picture one of these instruments, a Hilger spectrograph perhaps, sitting on a laboratory bench in some quiet university building in the early years of the 20th century, its brass fittings gleaming softly in the gaslight, its prism of finest optical glass waiting to receive the light from a Bunsen burner flame into which a student has introduced a sample of some mineral brought back from a geological expedition. And as the flame burns steadily and the light passes through the slit and is rendered parallel by the collimator lens and falls upon the prism face and is bent and spread and bent again as it exits the glass and passes into the telescope where it comes to focus on the reticle, the student sees the familiar pattern of bright lines that spell out in the language of light the elemental composition of the unknown sample, a message written in wavelengths and colors. And the instrument that makes this reading possible is the product of all those decades of development, from Bunsen's first crude attempts to Kirchhoff's systematizing genius to Rowland's precision gratings to Hilger's commercial standardization, a quiet accumulation of human ingenuity in the service of understanding. And the spectra recorded by these instruments, whether on photographic plates or in the notebooks of observers who sketched what they saw through the eyepiece, would provide the data that theorists would puzzle over in the years to come. The regularities and patterns that seemed to cry out for explanation but resisted all attempts at understanding within the framework of classical physics, until at last Bohr and his contemporaries found the key in the quantum hypothesis. And the spectral lines that had been observed and catalogued and measured with such care by so many workers using instruments of ever-increasing sophistication finally yielded up their meaning. But that is a story for another time. And for now it is enough to appreciate the instruments themselves, the spectroscopes and spectrographs and spectrometers that made the whole enterprise possible, standing patient and precise in their laboratories and observatories, gathering light and sorting it by wavelength, revealing the hidden order of the atomic world one bright line at a time. And so we come now to a particularly soothing corner of our story, one that involves a quiet schoolteacher in Switzerland, a set of numbers that seemed almost musical in their regularity, and the gentle unraveling of a puzzle that had lingered at the edges of scientific understanding for some 2 decades. The year is 1885, and the city is Basel, that ancient and tranquil place where the Rhine bends slowly through its medieval heart, where church spires rise above terracotta rooftops, and where, in a modest school for girls, a mathematics teacher named Johann Jacob Balmer was about to achieve something quite remarkable, though he himself might not have fully grasped its significance at the time. Johann Jacob Balmer was not a young man burning with ambition, nor was he a figure moving through the distinguished corridors of university physics. He was 60 years old, white-bearded and gentle, a man who had spent his career teaching geometry and arithmetic to young women at a secondary school, explaining the properties of triangles and the behavior of quadratic equations with the patient repetition that such teaching requires. He had earned his doctorate many years earlier, in 1849, with a dissertation on cycloids, those lovely curves traced by points on rolling circles. But he had never worked in spectroscopy, had never peered through a prism at the colored bands of light that so fascinated the experimental physicists of his era, and had published nothing of particular note in the intervening 36 years. What Balmer did possess, however, was a deep and abiding love of numerical patterns, a fascination with the way that integers could dance together to produce harmonious relationships, and it was this somewhat abstract interest that would lead him, almost by accident, to one of the most important formulae in the history of atomic physics. He was, in a sense, a numerologist of the best kind, someone who believed that nature's secrets might reveal themselves through the careful study of ratios and proportions, and who had the mathematical training to pursue such intuitions with precision. The puzzle that captured Balmer's attention in his 60th year concerned the spectrum of hydrogen, that simplest of all elements, consisting as we now know of just one proton and one electron, though such knowledge lay far in the future. When hydrogen gas is heated or subjected to electrical discharge, it glows with a distinctive pinkish light, and when that light is passed through a spectrometer, it separates into a series of discrete colored lines rather than a continuous rainbow. There is a red line, quite prominent and easily visible, and then a blue-green line somewhat closer to the center of the visible spectrum, followed by a blue line and a violet line, each successive line growing fainter and each positioned at a very specific wavelength that could be measured with considerable accuracy. Anders Jonas Ångström, the Swedish physicist after whom the unit of length is named, had measured these wavelengths with exceptional precision in 1868, publishing values that would later prove accurate to within a few hundredths of a percent. The red line, which we now call hydrogen alpha, sits at a wavelength of 656.3 nanometers. The blue-green line, hydrogen beta, appears at 486.1 nanometers. The blue line, hydrogen gamma, registers at 434.0 nanometers. And the violet line, hydrogen delta, glows faintly at 410.2 nanometers. These numbers were known, recorded in tables, cited in papers, but for nearly 2 decades, no one had found any pattern connecting them, any formula that could predict their values from first principles or even from simple arithmetic relationships. It was this challenge that a colleague apparently mentioned to Balmer, perhaps over tea or during one of those leisurely conversations that academics enjoy, suggesting that here was a set of numbers that might appeal to his particular talents. And so Balmer, in his quiet study or perhaps at his desk at the girls' school between lessons on Euclidean geometry, began to play with these 4 wavelengths, seeking the hidden regularity that he believed must surely exist. What he discovered, after much patient calculation and trial of various numerical schemes, was breathtakingly simple. Each wavelength could be expressed as a constant, which he determined to be 364.56 nanometers, multiplied by a ratio of the form n squared divided by the quantity n squared minus 4, where n took on the integer values 3, 4, 5, and 6 for the 4 known visible lines. For the red line, n equals 3, and the formula gives 3 squared over 3 squared minus 4, which is 9 over 5, or 1.8, and when multiplied by the constant yields 656.2 nanometers, matching Angstrom's measurement almost exactly. For the blue-green line, n equals 4, giving 16/12, or 4/3, which produces 486.1 nanometers. For the blue line, n equals 5, giving 25/21, yielding 434.0 nanometers. And for the violet line, n equals 6, giving 36/32, or 9/8, producing 410.2 nanometers. The agreement was startling in its precision. Here was a simple algebraic expression, involving only integers and a single constant, that reproduced the measured wavelengths of hydrogen's visible spectrum to within the limits of experimental accuracy. Balmer published his discovery in June of 1885, in a paper presented to the Naturforschungsgesellschaft in Basel, that venerable scientific society where local scholars gathered to share their findings in an atmosphere of collegial respect. But Balmer did not stop with merely fitting the four known lines. He recognized that his formula, if it truly captured some fundamental truth about the hydrogen atom, should predict additional lines beyond those already measured. If n equals 7, the formula gives a wavelength of 397 nanometers, deep in the violet where the human eye struggles to perceive. If n equals 8, it predicts 389 nanometers. If n equals 9, 383 nanometers. And as n increases further, approaching infinity, the wavelengths converge toward a limiting value of 364.6 nanometers, where the lines would crowd together so closely as to become indistinguishable, forming what spectroscopists call a series limit. When astronomers and laboratory physicists examined hydrogen spectra more carefully, they found precisely what Balmer had predicted. The additional lines were there, exactly where his formula said they should be, growing fainter and more closely spaced as the wavelengths decreased toward the ultraviolet. By 1886, just a year after Balmer's publication, spectroscopists had confirmed lines up to n equals 11, and eventually the series would be traced even further, with Balmer's simple formula proving correct in every case. It is worth pausing here, in the gentle way that this narrative allows, to appreciate what Balmer had achieved and what remained mysterious about his achievement. He had found a pattern, a beautiful and precise mathematical relationship, but he had no theory to explain it. The formula worked, magnificently and undeniably, but it offered no insight into why hydrogen should emit light at these particular wavelengths rather than others, no mechanism by which the atom might produce such a regular sequence of spectral lines. The constant 364.56 nanometers had no physical interpretation that Balmer could provide. It was simply a number that made the formula fit the data. The integers 3, 4, 5, and 6 appeared as if by magic, with no explanation for their role in the atom's behavior. This situation, where an empirical formula succeeds brilliantly without any theoretical foundation, is a common and often fruitful one in the history of science. The formula becomes a challenge to theorists, a puzzle demanding explanation, and in seeking that explanation, deeper truths about nature are often revealed. Balmer's formula would have to wait nearly 3 decades for such an explanation, until a young Danish physicist named Niels Bohr would provide it in 1913, but that belongs to a later section of our story. 3 years after Balmer's discovery, in 1888, a Swedish physicist named Johannes Robert Rydberg undertook a systematic study of spectral series across many different elements, seeking to generalize Balmer's result and to express it in a more universal form. Rydberg, who was known to his friends as Jonna, worked at Lund University in southern Sweden, and he possessed both the mathematical skill and the patient temperament required for such a comprehensive survey. Rydberg recognized that Balmer's formula could be rewritten in terms of wave numbers rather than wavelengths. The wave number is simply the reciprocal of the wavelength, representing how many waves fit into a unit of length, and it has the convenient property that it is directly proportional to the frequency and energy of the light. When Balmer's formula is expressed in wave number form, it becomes remarkably elegant. The wave number of each line equals a constant, which we now call the Rydberg constant, multiplied by the quantity 1 over 4 minus 1 over n squared. The factor of 1 over 4 can itself be written as 1 over 2 squared, revealing the underlying symmetry more clearly. The wave number equals the Rydberg constant times the difference between 1 over 2 squared and 1 over n squared, where n takes the integer values 3, 4, 5, 6, and so on. This formulation suggests a natural generalization. Perhaps other series of hydrogen lines exist, corresponding to other values in place of the two, with the wave number given by the Rydberg constant times the difference between 1 over m squared and 1 over n squared, where m and n are both integers and n is always larger than m. Rydberg proposed exactly this generalization, suggesting that Balmer's visible series was just one member of a family of spectral series, each characterized by a different value of the lower integer m. For m equals 1, there should be a series in the ultraviolet, with wavelengths shorter than the violet light visible to human eyes. For m equals 3, 4, 5, and beyond, there should be series in the infrared, with wavelengths longer than the red light we can see. The Rydberg constant itself, that fundamental parameter governing all of hydrogen's spectral series, was determined to have a value of 1.097 times 10 to the 7th per meter, or approximately 10,970,000 inverse meters. This number, emerging purely from the analysis of spectral data, would later prove to be expressible in terms of more fundamental physical constants, the mass and charge of the electron, the speed of light, and Planck's constant. But in 1888, it stood alone as an empirical fact, another mysterious number awaiting theoretical explanation. The confirmation of Rydberg's predicted series came gradually over the following decades, as experimental techniques improved and spectroscopists extended their observations beyond the visible range. The ultraviolet series, with m equals 1, was discovered by Theodore Lyman at Harvard University in 1906. Lyman used a vacuum spectrograph to observe wavelengths below 200 nanometers, where ordinary air absorbs the radiation, and he found precisely the series of lines that Rydberg's formula predicted, with wavelengths of 122 nanometers for the first line, 103 nanometers for the second, and so on, converging toward a series limit at 91.2 nanometers. The infrared series with m equals 3 was discovered by Friedrich Parchen in 1908, using techniques sensitive to wavelengths around 1000 to 2000 nanometers, in the near-infrared region just beyond the red end of the visible spectrum. Parchen worked at the University of Tübingen in Germany, and his measurements confirmed yet another branch of the hydrogen spectrum, with lines at 1875 nanometers, 1282 nanometers, and continuing to shorter infrared wavelengths according to Rydberg's formula. Still further into the infrared, The series with m equals 4 was discovered by Frederick Sumner Brackett in 1922, with lines at 4052 nanometers and beyond, deep in the infrared where special detectors are required. The series with m equals 5, named after August Hermann Pfund, who found it in 1924, lies even further into the infrared, with its first line at 7458 nanometers. And series corresponding to still larger values of m have since been observed, each confirming Rydberg's generalization with remarkable precision. The existence of these multiple series, all governed by the same Rydberg constant and the same simple formula involving integer squared terms, deepened the puzzle rather than resolving it. Why should integers play such a fundamental role in the emission of light by atoms? What was the physical meaning of the quantum numbers m and n? Why did the wave number depend on the difference of inverse squares rather than some other mathematical combination? These questions would eventually lead to the quantum theory of the atom, to Bohr's model of 1913 with its discrete electron orbits, and ultimately to the full wave mechanics of Schrödinger and Heisenberg in the 1920s. But in the decades following Balmer's discovery, the formula and its generalizations stood as empirical facts, beautiful and mysterious, patterns in nature that invited explanation but did not compel any particular theoretical interpretation. It is pleasant to imagine Balmer himself, in his final years, learning of the confirmations of his predicted lines and perhaps hearing early discussions of Rydberg's work. He lived until 1898, passing away at the age of 73, having spent most of his life in the quiet routines of teaching mathematics to young women in Basel. He published a few more papers after his spectroscopy work, including some further investigations of numerical patterns, but none achieved the significance of his 1885 formula. His name would become permanently attached to the visible series of hydrogen lines, the Balmer series, a modest monument to an afternoon's inspiration in a schoolteacher's study. The Rydberg constant, that fundamental number connecting all of hydrogen's spectral series, would prove even more significant. When Bohr developed his model of the atom in 1913, one of his great triumphs was deriving the Rydberg constant from first principles, expressing it as a combination of the electron mass, the electron charge, Planck's constant, and the speed of light. The fact that this theoretical calculation matched the experimentally determined value was powerful evidence that Bohr's model, for all its eventual limitations, had captured something essential about atomic structure. But we are getting ahead of ourselves, drifting toward topics that belong to later sections of this narrative. For now, it is enough to rest in the gentle satisfaction of Balmer's discovery and Rydberg's generalization, to appreciate how 4 numbers in a table of wavelengths, measured with care by Swedish experimenters and studied with patience by a Swiss schoolteacher, revealed a pattern of such beautiful simplicity that it seemed to offer a glimpse into the fundamental architecture of matter. The hydrogen atom, that most basic of all atomic systems, had yielded its first secret, the secret of its light. The spectrum that had seemed merely a jumble of colored lines now showed an orderly structure, governed by integers and ratios in a way that hinted at deep principles yet to be uncovered. The formula worked perfectly and reliably, and the physics would eventually follow, in its own unhurried time. And so, with Balmer's numbers and Rydberg's constant settled comfortably into the scientific literature, with the Lyman series glowing in the ultraviolet and the Parchen series warming the infrared, we may let our thoughts drift gently, knowing that the hydrogen puzzle, though not yet solved, has at least been clearly stated, its patterns revealed, its regularities laid bare for the theorists who would come later to explain. The lines in the spectrum continue to shine, in laboratories and in stars, each photon following faithfully the formula that Balmer found, each wavelength confirming what a 60-year-old schoolteacher worked out at his desk in Basel, in the quiet hours between lessons on geometry and the peaceful evenings of a well-ordered life. In the quiet university city of Leiden, in the autumn of 1896, a young Dutch physicist named Peter Zeeman was working in a basement laboratory, surrounded by the heavy iron cores of electromagnets and the familiar orange glow of sodium flames. He was 31 years old at the time, having recently completed his doctoral studies under the guidance of the distinguished physicist Hendrik Antoon Lorentz, and he had become interested in a question that had lingered at the edges of optical research for several decades. The question was simple enough to state, though answering it had proved remarkably difficult, and it concerned whether the spectral lines produced by glowing substances might be affected in some way by the presence of strong magnetic fields. This was the sort of fundamental inquiry that appealed to Zeeman's methodical temperament, and he approached it with the patient determination that would characterize his entire scientific career, setting up his apparatus with great care and recording his observations with meticulous attention to detail. The idea that magnetism might influence the behavior of light was not entirely new, and indeed the great Michael Faraday had attempted similar experiments more than 3 decades earlier, in 1862, during the final years of his extraordinary scientific life. Faraday had long believed in a deep connection between light and electromagnetism, having already demonstrated that magnetic fields could rotate the plane of polarization of light passing through certain transparent materials, a phenomenon that came to bear his name. Encouraged by this discovery, he had sought to determine whether magnetic fields might also affect the light emitted by luminous gases, and he had placed various flame sources between the poles of the strongest permanent magnets available to him at the Royal Institution. He examined the spectral lines produced by these flames with considerable care, looking for any broadening or shifting or splitting that might indicate a magnetic influence, but his instruments revealed nothing that could be distinguished from experimental noise. The magnets he possessed were simply not powerful enough, and the spectroscopes of his era lacked the resolving power necessary to detect the very subtle changes that actually occur. Faraday recorded his negative results in his laboratory notebook, as was his careful habit, and the question remained open, waiting for future investigators with better equipment and more sensitive techniques. Zeeman was aware of Faraday's earlier attempts when he began his own experiments, and he understood that success would require both stronger magnetic fields and more precise methods of observation than had been available in 1862. For his magnetic field source, he employed a large Ruhmkorff electromagnet, which was a device named after the German instrument maker Heinrich Ruhmkorff and consisting of an iron core wrapped with many turns of copper wire through which a substantial electric current could be passed. These electromagnets were capable of producing magnetic fields far stronger than any permanent magnet, and by the 1890s they had become standard equipment in physics laboratories investigating the properties of matter and radiation. Zeeman positioned his sodium flame directly between the pole pieces of his Ruhmkorff electromagnet, arranging the apparatus so that he could observe the emitted light either along the direction of the magnetic field or perpendicular to it. For his spectroscopic analysis, he used a high-quality diffraction grating that could spread the light into its component wavelengths with sufficient resolution to detect very small changes in the positions or widths of spectral lines, and he took great pains to eliminate sources of vibration and thermal disturbance that might blur his observations. When Zeeman first energized his electromagnet and examined the bright yellow lines of sodium through his spectroscope, he noticed something that Faraday had searched for but never found. The characteristic sodium doublet. Those two closely spaced yellow lines that had been known to spectroscopists for decades appeared to broaden slightly when the magnetic field was applied. The broadening was subtle, barely perceptible at first glance, but it was reproducible and it varied in a systematic way with the strength of the applied field. As Zeeman continued his observations and refined his technique, he came to understand that what appeared as broadening was actually something more interesting, namely the splitting of each spectral line into multiple components that were too close together to be fully resolved by his initial measurements. With improved apparatus and stronger magnetic fields, the splitting became clearer, and Zeeman could see that a single spectral line was being divided into three separate lines when viewed perpendicular to the magnetic field direction, with the central component remaining at the original wavelength and the two outer components displaced symmetrically to slightly shorter and slightly longer wavelengths. The discovery was announced in a brief communication to the Royal Netherlands Academy of Arts and Sciences in October of 1896. And it immediately attracted the attention of theoretical physicists who recognized its profound implications. Chief among these was Hendrik Lorentz himself, Zeeman's former doctoral supervisor and one of the leading theoretical minds of the era. Lorentz had been developing a comprehensive theory of the interaction between matter and electromagnetic fields, building upon the foundational work of James Clerk Maxwell and extending it to describe the behavior of charged particles within atoms. According to Lorentz's theoretical framework, the light emitted by atoms was produced by the oscillation of electrically charged particles, and these oscillating charges would naturally be influenced by external magnetic fields in predictable ways. The magnetic force acting on a moving charge would modify the frequency of oscillation, and by carefully analyzing the mathematical consequences of this interaction, Lorentz was able to derive a theoretical prediction for the magnitude and pattern of the spectral line splitting that Zeeman had observed. Lorentz's theoretical explanation, which he developed with remarkable speed in the weeks following Zeeman's announcement, provided a beautiful connection between the observed spectral phenomena and the properties of the charged particles responsible for light emission. According to his analysis, the amount by which each spectral line was split depended on a single quantity, namely the ratio of the electric charge of the oscillating particle to its mass. This charge-to-mass ratio could be calculated directly from Zeeman's measurements of the line splitting and the known strength of the applied magnetic field, and when Lorentz performed this calculation, he obtained a value that was extraordinarily large compared to any previously known charged particle. The charge-to-mass ratio implied by the Zeeman effect was roughly 1,000 times greater than that of the hydrogen ion, which was the lightest charged particle known from electrochemistry, and this suggested that the particles responsible for light emission were either much more highly charged or much less massive than hydrogen atoms, or perhaps some combination of both possibilities. This theoretical prediction arrived at a particularly opportune moment in the history of physics, for just a year later, in 1897, the English physicist Joseph John Thomson at the Cavendish Laboratory in Cambridge would announce his discovery of cathode rays as streams of particles with precisely this anomalously large charge-to-mass ratio. Thomson's experiments on cathode rays and Lorentz's analysis of Zeeman's spectroscopic observations thus converged on the same remarkable conclusion, that there existed a particle of electricity far smaller than any atom, a fundamental constituent of matter that would come to be called the electron. The Zeeman effect therefore played a crucial role in establishing the existence of electrons and demonstrating their involvement in the production of light, providing independent evidence that complemented and reinforced the more direct investigations of cathode ray physics. The relationship between Zeeman and his supervisor Lorentz during this period of discovery was characterized by mutual respect and productive collaboration, though it is worth noting that not everyone in the Leiden physics community was initially supportive of Zeeman's line of investigation. The director of the Leiden Physics Laboratory was Heike Kamerlingh-Onnes, a formidable experimentalist who would later become famous for his pioneering work on low-temperature physics and the discovery of superconductivity. Kamerlingh-Onnes ran his laboratory with considerable discipline, and he initially expressed skepticism about the value of Zeeman's magnetic investigations, preferring that his researchers focus on the cryogenic studies that formed the laboratory's principal research program. According to some accounts, Zeeman's early experiments on the magnetic effect were conducted somewhat outside the official purview of the laboratory's activities, though the exact nature and extent of any tension between Zeeman and Kamerlingh-Onnes has been the subject of varying historical interpretations. What is clear is that once the importance of Zeeman's discovery became apparent, any initial reservations were set aside, and the work received full recognition both within Leiden and throughout the international physics community. The pattern of spectral line splitting that Zeeman initially observed, with each line dividing into three components of specific polarization characteristics, came to be known as the normal Zeeman effect, and it could be explained completely within the framework of classical electromagnetic theory as developed by Lorentz. When observed perpendicular to the magnetic field direction, the three components consisted of a central line at the original wavelength, polarized parallel to the field, flanked by two displaced lines polarized perpendicular to the field. When observed along the direction of the magnetic field, only the two outer components were visible, and these exhibited circular polarization in opposite senses. All of these features followed naturally from Lorentz's model of oscillating charged particles in a magnetic field, and the quantitative agreement between theory and observation was highly satisfying. However, as spectroscopists continued to investigate the Zeeman effect in various elements throughout the closing years of the 19th century and the opening years of the 20th, it became apparent that the simple triplet pattern was actually the exception rather than the rule. Many spectral lines, when subjected to magnetic fields, split into far more complex patterns involving 4, 6, or even more components with varying intensities and polarizations that could not be explained by the classical theory. This more complicated behavior came to be called the anomalous Zeeman effect, though in retrospect it was the normal effect that was anomalous in the sense of being unusually simple. The anomalous Zeeman effect presented a significant puzzle for theoretical physics, one that would not be satisfactorily resolved until the development of quantum mechanics and the discovery of electron spin in the 1920s. The complexity of these anomalous patterns provided important clues about the internal structure of atoms and the need for new physical concepts beyond classical electromagnetism, though working out the full explanation would require the efforts of many theoretical physicists over several decades. In recognition of their contributions to the understanding of electromagnetic phenomena, Peter Zeeman and Hendrik Lorentz were jointly awarded the Nobel Prize in Physics for the year 1902. The prize citation specifically mentioned their researches into the influence of magnetism upon radiation phenomena, acknowledging both the experimental discovery and the theoretical explanation as complementary achievements of comparable significance. Zeeman was only 37 years old at the time, making him one of the younger Nobel laureates in physics, and he would continue productive research for many more decades, eventually serving as director of the Zeeman laboratory in Amsterdam that was named in his honor. Lorentz, for his part, remained one of the most respected figures in theoretical physics throughout the early 20th century, serving as a kind of elder statesman and mentor to the younger generation of physicists who would develop quantum mechanics and relativity theory. The significance of the Zeeman effect for the understanding of atomic structure cannot be overstated, even though its full interpretation required theoretical tools that were not available in 1896. At the most basic level, it demonstrated conclusively that the light emitted by atoms was produced by the motion of electrically charged particles, confirming a hypothesis that had been speculative and confirming electrons as the carriers of atomic radiation. The precise measurements of spectral line splitting provided quantitative information about the charge-to-mass ratio of these particles, yielding values that agreed with independent measurements from cathode ray experiments, and thus establishing the electron as a well-defined physical entity with consistent properties. The existence of both normal and anomalous patterns indicated that the internal dynamics of atoms were more complex than simple classical models could accommodate, pointing toward the need for fundamentally new physical principles. For spectroscopy as a scientific discipline, the Zeeman effect also provided a powerful new analytical tool, allowing investigators to distinguish between different types of spectral lines and to gain information about atomic structure that was not accessible through ordinary spectroscopic measurements. The polarization characteristics of the various Zeeman components, and the way these components varied with viewing angle relative to the magnetic field, provided additional degrees of freedom for classifying and interpreting spectral data. This proved particularly valuable for untangling complex spectra containing many overlapping lines, and the study of Zeeman patterns became an important branch of spectroscopic research throughout the early 20th century. From the perspective of electromagnetic theory, the Zeeman effect also represented an important confirmation and extension of Maxwell's equations and their application to atomic phenomena. The success of Lorentz's theoretical explanation demonstrated that the classical framework of electromagnetism remained valid even at the atomic scale, at least for certain phenomena, and this provided confidence in extending electromagnetic concepts to ever smaller dimensions. Of course, the limitations of classical theory would become increasingly apparent as the anomalous Zeeman effect and other quantum phenomena demanded explanation. But in 1896 and the years immediately following, the Zeeman effect stood as a triumph of classical physics applied to atomic spectroscopy. The path from Faraday's unsuccessful attempts in 1862 to Zeeman's successful observations in 1896 illustrates several important aspects of scientific progress. Both investigators asked essentially the same question and employed similar experimental strategies. Yet Faraday failed where Zeeman succeeded, not because of any difference in skill or insight, but simply because the necessary technology had not yet been developed in Faraday's time. The powerful electromagnets that Zeeman employed, the high-resolution diffraction gratings that allowed him to detect subtle line splitting, and the accumulated understanding of spectroscopic technique that guided his experimental design were all products of the intervening decades of scientific and technical development. Faraday had the right idea but the wrong equipment, and history remembers Zeeman because he happened to work at a moment when the experimental tools had finally caught up with the theoretical questions. As you settle more deeply into your restful state, consider how the quiet basement laboratory in Leiden, with its humming electromagnets and flickering sodium flames, became the site of a discovery that helped reveal the electron and demonstrated the intimate connection between light and magnetism that Faraday had always believed must exist. The orange glow of sodium, so familiar and so seemingly simple, concealed within its spectral lines the subtle signatures of magnetic influence, waiting patiently for instruments sensitive enough to reveal them. And in the mathematical equations that Lorentz developed to explain Zeeman's observations, the electron first appeared as a theoretical necessity, a particle of definite charge and mass whose existence would soon be confirmed by many independent lines of evidence. These developments unfolded gradually, methodically, one careful measurement and one theoretical calculation at a time, in the manner of all lasting scientific achievements. And so we come now to the work of Henry Augustus Rowland, a quiet and determined physicist working in Baltimore, in the state of Maryland, whose patience and mechanical genius would transform the study of light itself, giving astronomers and chemists alike a tool of such extraordinary precision that it would remain unsurpassed for decades to come. His story is one of careful labor, of nights spent adjusting screws by fractions of a hair's breadth, of years devoted to the perfection of a single instrument, and of a resulting atlas that would map the composition of our nearest star with an accuracy that still commands respect more than a century after its completion. It is a gentle story, really, despite its grand implications. A story of one man's belief that pure knowledge, pursued for its own sake, holds a value beyond any immediate practical application, and that the careful measurement of nature's smallest details can reveal truths of cosmic significance. Henry Augustus Rowland was born in Pennsylvania in 1848, into a family of Protestant ministers. Though from an early age his interests turned not toward theology but toward the physical world and the elegant certainties of mathematics and experiment. He studied civil engineering at the Rensselaer Polytechnic Institute, and though he worked briefly as a surveyor, his heart belonged to physics, to the careful investigation of electromagnetic phenomena that had so captivated the scientific world in the wake of Faraday and Maxwell. His early papers on magnetic permeability caught the attention of James Clerk Maxwell himself, who arranged for their publication in the Philosophical magazine when American journals had shown little interest. This recognition from abroad was both a validation and a reminder of something that would trouble Rowland throughout his career, namely the relative indifference of American society toward pure scientific research, a preference for the practical and the profitable over the theoretical and the true. In 1876, Rowland was appointed the first professor of physics at the newly established Johns Hopkins University, an institution founded with the explicit intention of combining teaching with original research in the German manner. And it was there, in Baltimore, that he would spend the remainder of his working life. The university provided him with resources and, more importantly, with the freedom to pursue fundamental questions without constant pressure to demonstrate immediate utility. Rowland took full advantage of this liberty, establishing a laboratory that would become renowned for its combination of theoretical sophistication and mechanical precision, a place where the most delicate instruments were designed, built, and operated in service of answering nature's subtlest questions. The challenge that would occupy the central years of his career concerned the diffraction grating, that deceptively simple device consisting of many fine parallel lines ruled on a reflective or transparent surface, which separates light into its component wavelengths through the phenomenon of interference. The principle had been understood since the work of Fraunhofer earlier in the century, and gratings had proven invaluable for spectroscopy, for the analysis of light emitted or absorbed by various substances. But the gratings available in Rowland's time were limited in their resolving power, which is to say their ability to distinguish between wavelengths very close together. And this limitation arose from the difficulty of ruling sufficiently fine and regular lines over a sufficiently large area. Every tiny irregularity in the spacing of the lines produced errors and ghosts in the resulting spectrum. false lines, or distortions that complicated the already intricate business of interpretation. Rowland understood that the path to better gratings lay through better ruling engines, the mechanical devices used to cut the lines, and so he set about designing and constructing a ruling engine of unprecedented accuracy. This was not a task of months but of years, a slow and painstaking process of eliminating sources of error one by one, of understanding how temperature changes caused metal to expand and contract, how vibrations from distant streets or railways could disturb the cutting point, how the very act of measurement could introduce uncertainties if not performed with sufficient care. He worked with screws ground to tolerances that pushed the limits of what contemporary metrology could verify, with diamond cutting points mounted in holders designed to maintain perfect constancy of pressure, with frames and beds machined from carefully selected materials and allowed to settle and stabilize before final adjustment. The work took 5 years, from 1877 to 1882, 5 years of refinement and modification and testing, of ruling gratings and examining their spectra and noting where imperfections remained, then returning to the engine to identify and correct the source of each flaw. Rowland's laboratory notebooks from this period record a mind utterly absorbed in the details of mechanical perfection, in the question of how to make a screw advance by exactly the same amount with each turn, how to guide a carriage along a path that deviates from straightness by no more than a few millionths of an inch, how to keep a diamond point sharp enough and steady enough to cut 20,000 lines across each inch of metal without wavering or skipping or dulling. It was work that required not only theoretical understanding but also the practical skills of a master craftsman, and Rowland possessed both in full measure. By 1882, the ruling engine was complete, capable of producing gratings with up to 20,000 lines per inch, a density far exceeding anything previously achieved, and with a regularity that eliminated most of the troublesome ghosts and distortions that had plagued earlier instruments. But Rowland had also introduced another innovation, equally important, which was the ruling of these lines not on flat surfaces but on concave mirrors. A concave grating combines in a single optical element the functions of both diffraction and focusing, eliminating the need for separate lenses or mirrors to form the spectrum into a sharp image, and thus avoiding the chromatic aberrations and light losses that such additional elements inevitably introduce. The concave grating was simpler to use, more efficient, and capable of greater resolving power than any flat grating of comparable size, and its introduction transformed spectroscopic practice in observatories and laboratories around the world. Rowland did not hoard his invention but made gratings available to other researchers at reasonable cost, and the instruments that emerged from his Baltimore laboratory found their way to scientific institutions across America and Europe, each one a precision tool that enabled new discoveries and more accurate measurements. But the finest gratings, the largest and most perfect, Rowland reserved for a project of his own, the comprehensive mapping of the solar spectrum, that intricate pattern of bright continuous background crossed by thousands of dark absorption lines that had first been noted by Wollaston and catalogued by Fraunhofer, and which held the key to understanding not only the composition of the Sun but the fundamental nature of matter itself. The project began in earnest in 1888 and would continue for nearly a decade, a sustained effort involving Rowland and several assistants who devoted themselves to the systematic photography and measurement of every discernible feature in the visible solar spectrum. The work proceeded wavelength by wavelength, region by region, with large concave gratings producing spectra of unprecedented dispersion and clarity, spreading the colors of sunlight across photographic plates where each dark line stood distinct from its neighbors, no longer blurred or merged but sharp and individual, available for precise measurement. Rowland developed techniques for calibrating the wavelength scale to accuracies of 1 part in a million, for identifying the systematic errors introduced by temperature variation and atmospheric refraction, for cross-checking measurements made on different days and under different conditions to ensure consistency and reliability. The result of this labor was the photographic map of the normal solar spectrum, published in 9 volumes between 1895 and 1897, a monumental work containing detailed photographs and tables documenting over 20,000 Fraunhofer lines across the visible spectrum. Each line was assigned a precise wavelength, accurate to 1,000th of an angstrom, that tiny unit of length equal to 1/10,000,000th of a meter, itself named for the Swedish physicist whose earlier solar atlas Rowland's work now decisively superseded. The atlas was not merely a catalogue but a reference standard, a foundation upon which all subsequent spectroscopic work could build, confident that wavelengths cited by Rowland could be trusted to an accuracy unmatched by any previous compilation. Within this forest of lines, Rowland and his team identified the spectroscopic signatures of 39 terrestrial elements, their presence in the solar atmosphere revealed by the precise coincidence between dark lines in the solar spectrum and bright lines produced by the same elements when heated to incandescence in the laboratory. Here was iron, its complex pattern of hundreds of lines unmistakable once the wavelengths were known with sufficient precision. Here was calcium, and sodium, and hydrogen, and magnesium, and nickel, and chromium, and a host of other familiar substances, all present in the outer layers of a star 93 million miles distant, their identities as certain as if samples had been collected and analyzed in Baltimore. The solar spectrum was no longer merely a curiosity but a chemical inventory, a census of elemental abundances that would inform theories of stellar structure and evolution for generations to come. Rowland's work established not only a catalogue of solar lines but an international system of wavelength standards, a common reference frame that enabled researchers in different countries and different laboratories to compare their measurements with confidence. Before Rowland, spectroscopic wavelengths were often reported using arbitrary or inconsistent scales, making it difficult to know whether a line measured in Berlin corresponded to one measured in Paris or Cambridge. After Rowland, there was a single authoritative system, anchored in his carefully calibrated solar measurements, to which all others could refer. This standardization may seem a modest achievement compared to the drama of discovering new elements or formulating new theories, but it was in its way just as important, providing the common language without which scientific communication and cumulative progress would have been greatly impeded. There is a small and charming footnote to Rowland's spectroscopic work, a demonstration of both his technical virtuosity and his sense of scientific play. In 1882, he produced what might be called a spectroscopic self-portrait, ruling his own signature, the name Rowland, directly onto a diffraction grating in such a way that when light was passed through the grating and dispersed into a spectrum, the name appeared written across the colored bands. It was a curiosity, a piece of scientific whimsy, but it demonstrated with elegant economy the principle by which gratings work and the precision with which Rowland's engines could place lines in predetermined positions. The signature remains one of the more unusual items in the history of physics, a calling card written in diffracted light. Beyond his laboratory achievements, Rowland was also a forceful advocate for the place of pure science in American intellectual life, at a time when the prevailing culture favored practical invention and commercial application over theoretical inquiry. His address to the American Association for the Advancement of Science in 1883, titled A Plea for Pure Science, remains a significant document in the history of American science policy, a passionate argument for the intrinsic value of knowledge pursued without regard to immediate utility. Rowland observed that American society celebrated its inventors and entrepreneurs but showed comparative indifference to its researchers and theorists, and he warned that this imbalance would ultimately impoverish the nation's scientific culture and limit its capacity for future innovation. Pure science, he argued, was the wellspring from which applied science drew its inspiration and its tools, and a society that neglected the former while celebrating the latter was like a farmer who consumed his seed corn, enjoying a temporary abundance while ensuring future scarcity. The address was not without controversy, as some heard in it an implied criticism of American values and priorities, but Rowland was unrepentant. He believed that the pursuit of truth about the natural world was among the highest of human activities, worthy of support and respect regardless of whether it led to patentable inventions or commercial profits. His own career embodied this belief, for the ruling engine and the solar atlas brought him scientific fame but little financial reward, and he spent his later years in declining health, his laboratory struggling for funding even as the gratings it produced were transforming spectroscopy worldwide. He died in 1901, at the age of 52, leaving behind not only his instruments and his publications but a model of scientific dedication that would inspire those who came after. The photographic map of the normal solar spectrum remained the standard reference for solar spectroscopy for many decades, consulted by astronomers and physicists seeking reliable wavelength data for their own investigations. Even as new techniques emerged and new atlases were compiled, Rowland's work retained its authority, a testament to the care and precision that had gone into its making. The 20,000 lines he measured, the 39 elements he identified, the wavelength standards he established, all of these became part of the permanent foundation of astrophysics, taken for granted by later generations who might not always remember the years of patient labor that had produced them. In the larger story of atomic spectroscopy, Rowland's contribution occupies a crucial middle position, coming after Kirchhoff and Bunsen had established the basic principles of spectral analysis, but before Bohr and others would explain why atoms emit and absorb light at their characteristic wavelengths. Rowland did not theorize about the internal structure of atoms or the quantum nature of radiation. Such questions lay beyond the scope of his enterprise, which was fundamentally one of measurement and cataloging. But by providing data of unprecedented accuracy and completeness, he gave the theorists who followed a firm empirical foundation upon which to build. When physicists sought to explain the regular patterns in hydrogen spectrum or the complex structures of heavier elements, they turned to wavelength tables ultimately traceable to Rowland's laboratory, confident that the numbers they were trying to explain were correct to within a few parts per million. And so the ruling engine in Baltimore, turning through the night as its diamond point traced line after line across the curved surface of a specular mirror, was in its quiet way preparing the ground for the quantum revolution to come. The light from the sun, captured on photographic plates and measured with obsessive care, held clues to the nature of matter that would take another generation to decode. Rowland himself would not live to see Bohr's atomic model or the triumph of quantum mechanics, but his work made those achievements possible, or at least made them testable against observation of the required precision. Science proceeds by such accumulations, each careful researcher adding something to the common store of knowledge, trusting that others will find uses for measurements whose significance may not yet be clear. For now, as you settle deeper into rest, you might picture that Baltimore laboratory in the 1880s and 90s, quiet except for the soft mechanical sounds of the ruling engine, the occasional note in a logbook, the patient adjustment of a screw or a prism. The sun's light, ancient and distant, is being parsed into its components, its secrets catalogued and numbered, its composition revealed through the dark lines that cross its spectrum like a fingerprint. 20,000 lines, each one a signature of a particular element, each one measured to a precision that seems almost miraculous given the tools available. And from this labor, a map emerges, not of geography but of chemistry, not of the Earth but of the star that makes life on Earth possible. It is a gentle form of exploration, requiring no voyages and risking no lives, only patience and skill and the conviction that careful measurement is worth the years it demands. Sleep now, if you like, while Rowland's engine continues its work in imagination, line by line, hour by hour, building a portrait of the sun one wavelength at a time. As spectroscopy matured beyond its early experimental phases, it began to find its way into the practical world of industry and commerce, moving gradually from the quiet laboratories of university professors into the bustling environments of steelworks and mining operations, forensic investigations, and agricultural research stations. This transition occurred with a certain inevitability, for once it became clear that the spectroscope could identify elements with such remarkable precision, practical minds began to consider how this capability might be applied to the everyday problems of manufacturing and quality control. The movement of spectroscopy into industrial settings represents one of those quiet revolutions in scientific practice, the kind that rarely captures public attention but which nonetheless transforms the material conditions of modern life in profound and lasting ways. The metallurgical industries were among the first to recognize the potential value of spectroscopic analysis, and by the early 1870s, forward-thinking steelmakers had begun to investigate how the spectroscope might assist in the production of consistent, high-quality metal. The challenge facing steel manufacturers during this period was considerable, for the properties of steel depend critically upon its composition, and even small variations in the amounts of carbon, phosphorus, sulfur, or other elements can dramatically alter the strength, brittleness, and workability of the final product. Traditional methods of chemical analysis, while accurate, were time-consuming affairs that could take hours or even days to complete, during which time an entire batch of steel might be produced with unknown characteristics. The spectroscope offered the tantalizing possibility of much faster analysis, potentially allowing steelmakers to monitor and adjust their processes in something approaching real time. The Bessemer process, which had revolutionized steel production since its introduction in the 1850s, proved particularly amenable to spectroscopic monitoring. In this process, air is blown through molten pig iron to oxidize and remove impurities, with the carbon content decreasing as the blow progresses. Determining when sufficient carbon had been removed to produce steel of the desired composition was a matter of considerable skill, and experienced operators had developed various empirical methods involving the appearance of the flame and the behavior of the molten metal. However, these methods were imprecise, and the results could vary significantly depending upon the judgment of individual workers. Spectroscopic observation of the flame emerging from the converter offered a more objective approach, for the intensity of the carbon spectral lines could be monitored throughout the process, providing a direct indication of the carbon content remaining in the melt. As the carbon was oxidized and carried away, its characteristic spectral signature would diminish in brightness, allowing the operator to determine with reasonable accuracy when the blow should be terminated. The implementation of this technique required the development of spectroscopes robust enough to withstand the harsh conditions of the steelworks, where heat, dust, and vibration presented challenges quite unlike those encountered in the genteel environment of a university laboratory. Various designs emerged to meet these requirements, with instruments featuring protective housings and adjustable mountings that allowed them to be positioned at safe distances from the converter while still maintaining a clear line of sight to the flame. The training of workers to use these instruments competently represented an additional challenge, for the interpretation of spectra required a certain level of skill and experience, and not every steelworker possessed the temperament or inclination for such precise observational work. Nevertheless, those works that successfully adopted spectroscopic methods generally found that the improved consistency of their products more than justified the investment in equipment and training. Beyond the Bessemer process, spectroscopic analysis found applications throughout the metallurgical industries in the detection and quantification of trace impurities in alloys. The railway industry, which was expanding rapidly during this period and which depended utterly upon the reliability of its rails, wheels, and axles, had a particular interest in ensuring the quality of the steel it purchased. A rail that appeared perfectly sound but which contained excessive amounts of phosphorus might become brittle in cold weather and fracture catastrophically under load, with potentially devastating consequences for passengers and crew. Spectroscopic testing offered a means of screening incoming materials and verifying that they met the required specifications, though it should be noted that the technique was generally used as a supplement to, rather than a replacement for, traditional wet chemical analysis during this early period. The shipbuilding industry faced similar concerns regarding the quality of the steel plate used in hull construction, and here too spectroscopic methods found application in quality control. The great ocean-going vessels of the late 19th century represented enormous investments of capital, and the failure of a single plate due to undetected impurities could result in disaster. Naval authorities in several countries took a particular interest in spectroscopic testing, for the performance of warships in combat depended critically upon the quality of their armor and structural components. The British Admiralty, ever conscious of maintaining the superiority of the Royal Navy, encouraged research into improved methods of materials testing, and spectroscopy gradually became part of the standard toolkit employed in naval dockyards and the facilities of their suppliers. While these industrial applications were developing, spectroscopy was also finding its way into the quite different realm of forensic investigation. The detection of poisons had long presented challenges for investigators and courts alike, for many toxic substances could be administered in quantities too small to detect by ordinary means, and the symptoms they produced often resembled those of natural illness. The development of increasingly sensitive chemical tests during the early 19th century had improved the situation somewhat, but there remained substances that were difficult to identify with certainty using conventional methods. Spectroscopy offered new possibilities in this regard, for the characteristic spectral signatures of various elements could serve as unambiguous evidence of their presence, even in very small quantities. The application of spectroscopic methods to the detection of arsenic in suspected poisoning cases attracted considerable attention from the late 1860s onward. Arsenic had long been the poisoner's substance of choice, being readily available, relatively tasteless when properly administered, and capable of producing symptoms that could easily be mistaken for natural gastrointestinal illness. The Marsh test, developed some decades earlier, provided a reliable means of detecting arsenic through wet chemistry, But spectroscopic analysis offered a complementary approach that could in some circumstances provide additional confirmation of the presence of this deadly element. When arsenic compounds were introduced into a flame or electrical discharge, they produced characteristic spectral lines that could be identified with the spectroscope, providing evidence that was both highly specific and visually compelling when presented in court. The exact circumstances and cases in which spectroscopic evidence was first admitted in legal proceedings varied somewhat from jurisdiction to jurisdiction, and the acceptance of such technical evidence by judges and juries was not always straightforward. Expert witnesses were required to explain the principles of spectroscopy to laypeople who had never encountered such apparatus before, and the defense might always argue that the instruments had been improperly used or the results incorrectly interpreted. Nevertheless, spectroscopic evidence gradually gained acceptance as courts became more familiar with the technique, and by the final decades of the 19th century it had become an established part of the forensic toolkit in cases involving suspected poisoning or the adulteration of foodstuffs with harmful substances. The potential of spectroscopy for work outside the fixed laboratory setting led to the development of portable instruments suitable for use in the field. The United States Geological Survey, which was engaged in the systematic mapping and assessment of the nation's mineral resources, took a particular interest in portable spectroscopes that could be carried into remote areas by geologists conducting surveys. When a geologist encountered a mineral outcrop in some distant canyon or mountainside, it was often impractical to collect samples and transport them back to a distant laboratory for analysis, particularly when the initial question was simply whether the deposit warranted further investigation. A portable spectroscope allowed preliminary identification of minerals in the field, helping geologists to make more informed decisions about where to focus their detailed studies. The design of these field instruments required compromises between portability and optical performance, for the prisms and lenses of a high-quality laboratory spectroscope were heavy and fragile, ill-suited to being carried on horseback through rough country. Various manufacturers developed compact designs featuring smaller optical components housed in rugged cases, and while these instruments could not match the resolving power of their laboratory counterparts, they were adequate for many practical purposes. The flame sources used in the field were necessarily simpler than the elaborate gas burners available in well-equipped laboratories, with alcohol lamps and blowpipe flames serving in many situations. Despite these limitations, field spectroscopy proved valuable in mineral exploration, and the technique was gradually adopted by geological surveys in several countries as they worked to catalogue the Earth's resources. Agricultural applications of spectroscopy developed somewhat later than industrial uses, but by the 1880s and 90s, researchers in Germany and elsewhere were investigating how spectroscopic methods might be applied to the analysis of soils and plant materials. The fertility of agricultural land depends upon the presence of various essential elements, including nitrogen, phosphorus, and potassium, as well as trace amounts of other substances. And understanding the composition of a particular soil could help farmers to determine what fertilizers might be beneficially applied. Traditional methods of soil analysis were laborious and expensive, placing them beyond the reach of most ordinary farmers. But there was hope that spectroscopic techniques might eventually provide faster and more economical alternatives. The German agricultural research stations, which had been established to support the scientific improvement of farming practices, took a particular interest in these possibilities. The systematic study of plant nutrition and soil chemistry that these institutions undertook naturally led to interest in improved methods of chemical analysis, and spectroscopy offered potential advantages in terms of speed and the ability to detect multiple elements simultaneously. While the practical application of spectroscopy to routine agricultural analysis remained limited during this period, the research conducted at these stations laid foundations that would later be built upon as the techniques matured and became more accessible. The pharmaceutical industry represented another area in which spectroscopic methods found valuable applications, particularly in the authentication and quality control of chemical compounds. The purity of medicinal substances was a matter of considerable importance, for impurities might render a medicine ineffective or even dangerous, and unscrupulous suppliers had been known to adulterate their products with cheaper substitutes. Spectroscopic analysis could reveal the presence of unexpected elements in a pharmaceutical preparation, alerting manufacturers and pharmacists to potential problems with their supplies. The characteristic spectra of various compounds also provided a means of confirming the identity of substances, complementing other methods of chemical identification. As these various applications developed, commercial laboratories began to emerge, offering spectroscopic analysis as a service to clients who lacked the equipment or expertise to perform such tests themselves. William Crookes, who had made significant contributions to spectroscopic research in his own right, established a laboratory in London that undertook analytical work for a variety of clients. Such commercial enterprises filled an important niche, for while the largest industrial concerns might justify the expense of maintaining their own spectroscopic facilities, smaller firms often found it more economical to send samples to a specialist laboratory when analysis was required. The growth of these commercial services helped to spread the benefits of spectroscopic analysis more widely through the economy, making the technique accessible to clients who could not otherwise have afforded the necessary investment in instruments and trained personnel. The economic impact of spectroscopy upon the German optical and chemical industries proved particularly significant. 4 German firms were well positioned to take advantage of the growing demand for spectroscopic apparatus and the chemicals used in analytical work. The city of Jena, in particular, became a center of excellence for the manufacture of precision optical instruments, with the firms of Carl Zeiss and the Schott Glassworks achieving international reputations for the quality of their products. Zeiss had established his workshop in the 1840s, initially producing microscopes, but the firm gradually expanded its range to include spectroscopes and other precision instruments as demand grew during the latter half of the century. The relationship between Zeiss and the glassmaker Otto Schott proved particularly fruitful for the development of spectroscopic apparatus. The quality of a spectroscope depends critically upon the optical properties of its prisms and lenses, which in turn depend upon the quality of the glass from which they are made. Schott devoted considerable effort to the systematic improvement of optical glass, developing new compositions with precisely controlled refractive indices and dispersion characteristics. The glasses produced by the Schott works in Jena were eagerly sought by instrument makers throughout Europe and beyond, and the technical superiority of German optical glass helped to establish the dominance of German manufacturers in the market for precision scientific instruments. The physicist Ernst Abbe, who had developed theoretical treatments of optical systems that guided the design of improved instruments, played a crucial role in the success of the Jena firms. His collaboration with Zeiss and Schott brought together theoretical understanding and practical craftsmanship in a manner that proved enormously productive, and the instruments produced as a result of this collaboration set standards against which other manufacturers were measured. The integration of scientific research with manufacturing enterprise that characterized the Jena firms became a model that others sought to emulate. And the economic success of these enterprises demonstrated the practical value of investment in scientific and technical education. The German chemical industry similarly benefited from the growth of spectroscopy, for the demand for pure chemicals suitable for use as spectroscopic standards and reagents created new markets for producers who could guarantee the quality of their products. The great chemical firms that had grown wealthy from the production of synthetic dyes found new opportunities in the supply of laboratory chemicals, and the rigorous quality control that spectroscopic methods made possible helped to ensure that German chemical products maintained their reputation for reliability. The interconnections between different sectors of the German economy, from glass manufacturing to chemical production to instrument making, created a mutually reinforcing system that supported continued growth and innovation. The training of personnel to operate spectroscopic equipment and interpret results represented another area in which Germany established an early lead. The German technical universities and polytechnic institutes incorporated spectroscopy into their curricula, producing graduates who were familiar with the technique and capable of applying it in industrial settings. The systematic approach to technical education that characterized the German system proved well suited to the needs of industries increasingly dependent upon scientific methods of quality control and analysis. Firms that wished to implement spectroscopic testing could draw upon a pool of trained personnel, making adoption of the technique more straightforward than in countries where such training was less readily available. By the turn of the 20th century, spectroscopy had become thoroughly integrated into industrial practice across a wide range of sectors, from steel production to pharmaceutical manufacturing to geological exploration. The technique that had begun as a tool of pure scientific research, aimed at understanding the fundamental nature of matter and the composition of distant stars, had proved itself equally valuable in the mundane but essential work of ensuring the quality and consistency of manufactured goods. This movement from laboratory to factory floor represents one of the characteristic patterns of scientific development, in which advances in fundamental understanding eventually find practical applications that transform industry and daily life in ways their original discoverers could scarcely have anticipated. The story of spectroscopist's industrial adoption also illustrates the importance of the supporting infrastructure that makes scientific techniques practically useful, from the manufacture of precision instruments to the training of skilled workers to the establishment of commercial services for those lacking in-house capabilities. A scientific technique, however powerful in principle, remains of limited practical value until this broader ecosystem develops to support its widespread use. The growth of this ecosystem around spectroscopy during the latter half of the 19th century transformed what had been an exotic laboratory curiosity into a routine tool of industry and commerce, and the economic impact of this transformation was felt across the industrialized world, though nowhere more strongly than in the German states that had positioned themselves so effectively to supply the apparatus, chemicals, and trained personnel upon which the technique depended. In the city of Würzburg, in the south of Germany, there stood a university that had been teaching students for more than 300 years, and within its Physics Institute, in the autumn of 1895, a professor named Wilhelm Conrad Röntgen was conducting experiments with cathode ray tubes, those curious glass vessels from which most of the air had been pumped away and through which electrical discharges could be made to pass. Röntgen was 50 years old at the time, a careful and methodical researcher with a full beard and a reputation for preferring solitary work in his laboratory to the social gatherings that many of his colleagues enjoyed. He had been investigating the phenomena that occurred when cathode rays struck the glass walls of these evacuated tubes, following up on work that other physicists had been doing in laboratories across Europe. And on the 8th of November, in the early evening, he noticed something that he could not immediately explain. He had covered his cathode ray tube with black cardboard, you see, to block out the visible light that such tubes sometimes produced, and he had darkened his laboratory so that he might better observe the faint glows and fluorescences that were the subject of his investigations. The room was quite dark, and the covered tube should not have been emitting any light that could reach beyond its cardboard shielding, and yet Röntgen noticed that a screen coated with barium platinocyanide, which happened to be lying on a bench some distance away, was glowing with a faint greenish light. This was peculiar, because cathode rays themselves could not travel more than a few centimeters through air, and the screen was much farther away than that. Something was leaving the tube, passing through the black cardboard, traveling through the air of the laboratory, and causing the fluorescent screen to glow, and Röntgen did not know what that something might be. What followed was a period of investigation that Röntgen conducted in near total secrecy, scarcely emerging from his laboratory for the next 6 weeks, taking his meals there rather than at home, and sleeping on a cot when he slept at all. His wife Anna Bertha grew concerned about his health and his state of mind, but Röntgen was not ready to share what he was finding, not even with her, because the phenomena he was observing were so strange and so unexpected that he wanted to be certain of his results before he spoke to anyone about them. He was, by all accounts, a man who dreaded making mistakes in public, and he could not yet explain what he was seeing. During those 6 weeks, Röntgen discovered that these mysterious rays, whatever they were, could pass through many solid objects that would stop ordinary light. They passed through paper and wood and cloth with ease. They passed through thin sheets of metal, though thicker metal plates would stop them. They passed through the soft tissues of the human body, and here was the most remarkable thing of all, while being stopped or at least greatly absorbed by bones and dense materials. When Röntgen held his hand between the source of the rays and a photographic plate, and then developed that plate, he could see the shadows of his own bones, the skeleton of his living hand rendered visible through his flesh. Because he did not know what these rays were, and because the letter X is often used in mathematics to denote an unknown quantity, Röntgen called them X-rays, and that name has remained in common use ever since, though in Germany they are sometimes called Röntgen rays in honor of their discoverer. He continued his investigations methodically, determining that the rays traveled in straight lines like light, that they could not be reflected by mirrors or refracted by lenses in the way that ordinary light could be, and that they caused certain fluorescent materials to glow while leaving others unaffected. On the 22nd of December, 1895, Röntgen asked his wife to come to his laboratory, and there he made a radiograph of her hand, positioning it on a photographic plate while the X-rays passed through her flesh to darken the plate around the bones. The exposure took about 15 minutes, during which Anna Bertha had to hold quite still, and when the image was developed it showed her finger bones with stark clarity, along with the shadow of the wedding ring she wore. She is said to have found the image unsettling, this glimpse of her own skeleton, and to have remarked that she felt she was looking at her own death, though whether she used precisely those words we cannot be certain. That image, the radiograph of Anna Bertha Röntgen's hand, became one of the most famous scientific photographs ever made. On the 28th of December, Röntgen submitted his findings to the Physical Medical Society of Würzburg, and on the 5th of January 1896, the news of his discovery reached the general press, whereupon it spread around the world with remarkable speed for that era before radio and before the widespread use of telephones. Within weeks, Scientists in laboratories across Europe and America were reproducing his experiments, and within months, physicians were beginning to use X-rays to examine broken bones and locate foreign objects within the body. The medical applications were so immediately apparent and so obviously valuable that X-ray equipment was being manufactured and sold before anyone had properly understood what X-rays actually were. This question of the nature of X-rays would take many years to resolve, and the uncertainty surrounding it would lead to some of the most important developments in the early 20th century understanding of both atoms and radiation. Were X-rays a form of electromagnetic radiation, like light and the invisible ultraviolet and infrared rays, or were they something else entirely? Perhaps streams of particles like the cathode rays that produced them. The fact that X-rays could not be reflected or refracted in the usual ways suggested to some physicists that they might not be waves at all, while others proposed that they were simply electromagnetic waves of extremely short wavelength, too short to interact with ordinary optical materials. One of the physicists who contributed most to understanding the interaction between X-rays and matter was Charles Glover Barkla, who was born in Widnes in Lancashire in 1877 and who conducted much of his important research at the University of Liverpool and later at the University of Edinburgh. Barkla was interested in what happened when X-rays struck various substances, and in 1906, he made a discovery that would prove to be of fundamental importance for the understanding of atomic structure. He found that when X-rays hit a sample of a particular chemical element, that element would emit secondary X-rays of its own, and that these secondary X-rays had wavelengths that were characteristic of the element in question. This meant that each element, when stimulated by X-rays, gave off its own particular kind of X-ray radiation, just as each element, when heated in a flame, gave off its own particular colors of visible light. Barkla called these characteristic X-rays, and he identified two distinct series of them, which he labeled the K series and the L series, using letters from the middle of the alphabet in case additional series should be discovered at higher or lower energies, as indeed they later were. This discovery demonstrated that atoms had internal structure of some kind, that there were different parts or layers within the atom that could be excited by radiation and that would emit radiation of specific wavelengths in response. For his discovery of the characteristic X-rays of the elements, Barkla was awarded the Nobel Prize in Physics in 1917, though the award ceremony was delayed until 1918 because of the ongoing First World War. The significance of his work lay in demonstrating that X-ray spectroscopy could be used, like optical spectroscopy before it, to identify and study the elements, and indeed X-ray spectroscopy would prove to be an even more powerful tool in some respects, because the characteristic X-rays of an element are largely unaffected by the chemical compounds in which that element might be found, whereas optical spectra can vary considerably depending on how atoms are bonded to one another. While Barkla was conducting his research, a vigorous debate was underway about whether X-rays were waves or particles, and one of the most prominent advocates for the particle interpretation was William Henry Bragg, who was born in Wigton in Cumberland in 1862 and who spent many years as a professor in Australia before returning to England. Bragg observed that X-rays seemed to transfer their energy to matter in discrete packets rather than continuously, which suggested to him that they might be corpuscular in nature, and he developed a theory in which X-rays were neutral particles, rather like pairs of positive and negative charges traveling together. This interpretation was opposed by those who, like Barkla, believed that X-rays were electromagnetic waves, and the disagreement between Bragg and Barkla became somewhat heated at times, though it remained within the bounds of scientific discourse. The question was not finally resolved until 1912, when Max von Laue, a German physicist working in Munich, devised an experiment that would prove conclusively whether X-rays were waves or not. Von Laue reasoned that if X-rays were electromagnetic waves of very short wavelength, then they ought to show the phenomenon of diffraction, which is the bending and interference of waves when they pass through narrow openings or around small obstacles. The difficulty was that the wavelengths of X-rays, if they were waves at all, would be so short that ordinary diffraction gratings, with their lines ruled at spacings of a few thousandths of a millimeter, would be far too coarse to produce any observable effect. What von Laue realized, with considerable insight, was that the regular arrangement of atoms within a crystal might serve as a natural diffraction grating for X-rays, because the spacing between atoms in a crystal is of the same order of magnitude as the wavelengths that X-rays were thought to have. If X-rays were passed through a crystal, and if they were indeed waves, then the regularly spaced layers of atoms should cause them to diffract and interfere, producing a pattern of spots on a photographic plate placed behind the crystal. The experiment was carried out in April of 1912 by two of von Laue's colleagues, Walter Friedrich and Paul Knipping, using a crystal of copper sulfate and a beam of X-rays. When the photographic plate was developed, it showed exactly the pattern of spots that von Laue had predicted, arranged in a symmetrical pattern that reflected the internal structure of the crystal. This was definitive proof that X-rays were waves, and specifically that they were electromagnetic waves with wavelengths of about 1/10,000th of a millionth of a meter, far shorter than visible light or even ultraviolet radiation. Von Laue was awarded the Nobel Prize in Physics in 1914 for this discovery, and the technique of X-ray diffraction that he had invented would become one of the most powerful methods available for studying the structure of matter at the atomic level. It would eventually be used to determine the structures of countless crystals, minerals, metals, and biological molecules, including, many decades later, the structure of DNA itself. But that story belongs to a later time, and we need not follow it further here. What is worth noting, for our present purposes, is that the resolution of the wave-particle debate for X-rays did not mean that William Henry Bragg had been entirely wrong in his thinking. The observations that had led him to favor a corpuscular interpretation were real, and they pointed toward something important about the nature of radiation that the purely wave picture could not explain. When X-rays interacted with matter, they did seem to behave in some ways as if they were particles, transferring their energy in discrete units rather than continuously. This puzzle would not be fully resolved until the development of quantum mechanics in the 1920s, which showed that radiation has both wave-like and particle-like properties, and that the two descriptions are complementary rather than contradictory. William Henry Bragg himself went on to make fundamental contributions to X-ray science, working together with his son William Lawrence Bragg to develop the mathematical laws governing X-ray diffraction in crystals and to pioneer the technique of X-ray crystallography. For this work, the father and son shared the Nobel Prize in Physics in 1915, making them the only father-son pair to have shared a Nobel Prize. The younger Bragg, who was only 25 years old at the time, remains the youngest person ever to have received a Nobel Prize in Physics. The medical applications of X-rays, meanwhile, had proceeded at a pace that far outstripped the scientific understanding of what X-rays actually were. Within months of Röntgen's announcement, hospitals and physicians' offices around the world were acquiring X-ray equipment and using it to examine patients. Broken bones could be visualized without surgery. Bullets and other foreign objects could be located within the body, and conditions of the lungs and other internal organs could be observed in ways that had never before been possible. The value of this new technology was so obvious and so immediate that it was adopted with an enthusiasm that, in retrospect, was perhaps somewhat reckless. For it was not yet understood, in those early years, that X-rays could cause harm as well as benefit. The radiation that passed so easily through soft tissue was not entirely without effect, and prolonged or repeated exposure to X-rays could damage living cells, causing burns to the skin, hair loss, and more serious injuries that might not become apparent until years later. Many of the early pioneers of X-ray technology suffered grievously from radiation injuries, losing fingers, hands, and sometimes their lives to cancers and other conditions caused by their repeated exposure to the rays they were using. The safety precautions that are now standard in any facility where X-rays are used were developed only gradually, as the dangers became apparent through hard experience. Röntgen himself was awarded the very first Nobel Prize in Physics, in 1901, in recognition of the extraordinary services he had rendered by the discovery of the remarkable rays subsequently named after him. He accepted the prize with characteristic modesty, declining to give a lecture at the award ceremony, and he donated the prize money to his university. He never patented his discovery or sought to profit from it commercially, believing that scientific discoveries should be freely available for the benefit of all humanity. He continued to work at Würzburg and later at Munich until his retirement, and he died in 1923, having lived long enough to see his rays transform both physics and medicine in ways he could scarcely have imagined on that November evening when he first noticed the faint glow of a fluorescent screen in his darkened laboratory. The discovery of X-rays and the subsequent development of X-ray spectroscopy added a new dimension to the study of atomic structure, complementing and extending the information that could be obtained from optical spectroscopy. The characteristic X-rays that Balmer discovered came from the inner parts of atoms, from electrons that were held more tightly than the outer electrons responsible for visible light emission, and they provided evidence about the deeper structure of the atom that optical spectroscopy could not reach. In the years that followed, X-ray spectroscopy would be used to probe the arrangement of electrons within atoms, to verify and refine atomic models, and to establish relationships between atomic structure and the position of elements in the periodic table. But those developments would require the new quantum theory of the atom that Niels Bohr would propose in 1913, and they form part of a later chapter in this story of how scientists came to understand the nature of light and matter and the intimate connection between them. In the closing years of the 19th century, as spectroscopists continued their patient work of cataloguing the characteristic lines of known elements, a series of discoveries would reveal an entirely new category of substances, glowing with energies that no one had previously suspected existed. These radioactive materials, as they would come to be called, presented both remarkable opportunities and considerable challenges for spectroscopic analysis, and the story of their identification represents one of the more quietly dramatic chapters in the history of chemistry and physics, though we shall tell it here in the gentle manner befitting an evening's contemplation, without undue excitement or hurry. The discovery that set this chapter in motion occurred in Paris, at the Muséum National d'Histoire Naturelle, where Henri Becquerel held a professorial position that had been occupied by both his father and his grandfather before him, this being a family with a long tradition of investigating the phenomena of phosphorescence and fluorescence, those curious behaviors by which certain materials absorb light and then re-emit it over time. In early 1896, Becquerel was investigating whether phosphorescent materials might emit X-rays, those remarkable penetrating rays that Wilhelm Röntgen had announced to the world just weeks before, and his experimental approach involved wrapping photographic plates in black paper, placing phosphorescent crystals upon them, exposing the arrangement to sunlight to activate the phosphorescence, and then developing the plates to see whether any radiation had penetrated the paper to create an image. The crystals Becquerel chose for these experiments were uranium salts, specifically potassium uranyl sulfate, which his father had studied and which were known to exhibit particularly strong phosphorescence when stimulated by light. On the 26th and 27th of February 1896, Becquerel prepared his experiment as usual but found that the Parisian skies remained overcast, and so he placed the wrapped photographic plate with its uranium salt crystal in a drawer to await better weather, intending to expose it to strong sunlight when conditions improved. When he developed this plate on the 1st of March, perhaps merely to confirm that it remained usable, he found to his considerable surprise that it bore a strong image of the uranium crystal, despite never having been exposed to sunlight at all. This accidental discovery revealed that the uranium salt was emitting some form of radiation continuously and spontaneously, without any need for prior stimulation by light, and this radiation was capable of penetrating the black paper to affect the photographic emulsion beneath. Becquerel continued his investigations throughout 1896, demonstrating that this radiation could ionize gases and that it was emitted by all uranium compounds regardless of their chemical form, and indeed by metallic uranium itself, which suggested that the radiation was a property of the uranium element rather than of any particular compound or crystal structure. This was something genuinely new in the natural world, a form of energy emission that seemed to arise from within the atom itself, and it would soon attract the attention of researchers across Europe who sensed that here was a phenomenon worthy of sustained investigation. Among those drawn to investigate Becquerel's rays was a young Polish scientist named Maria Sklodowska, who had come to Paris to study physics and mathematics at the Sorbonne and who had married the French physicist Pierre Curie in 1895. For her doctoral research, Marie Curie, as she became known, chose to investigate the uranium rays systematically, and she began by developing quantitative methods to measure the intensity of the radiation using sensitive electrometers that Pierre and his brother Jacques had developed for studying piezoelectricity. Her approach was characteristically methodical, testing not only uranium compounds but a wide variety of other minerals and substances to determine which, if any, exhibited similar radiation. In the course of this survey, Marie Curie made a discovery that would reshape her research entirely. She found that the mineral pitchblende, a uranium-bearing or also known as uraninite, emitted radiation more intense than could be accounted for by its uranium content alone. This observation suggested that pitchblende must contain some other substance, present in quantities too small to have been detected by ordinary chemical analysis, that was itself radioactive and perhaps more intensely so than uranium. Pierre Curie, recognizing the significance of his wife's finding, set aside his own research on crystallography and magnetism to join her in the search for this unknown radioactive substance, and together they began the laborious process of chemically separating pitchblende into its constituent fractions, testing each fraction for its radioactive intensity. The work was arduous in the extreme, requiring the processing of large quantities of pitchblende residues in a converted shed that served as their laboratory, a space that was poorly heated in winter and stifling in summer, with no proper ventilation and only the most basic equipment. The chemical separations followed classical analytical procedures, dissolving the ore in acids, precipitating various fractions with different reagents, filtering and washing and drying, and at each stage measuring the radioactivity of the products to determine which fraction carried the unknown active substance. By July 1898, the Curies had isolated a fraction that was several hundred times more radioactive than uranium and that followed bismuth in its chemical behavior, and they announced the probable presence of a new element, which Marie named polonium in honor of her native Poland, a country that at that time existed only as a partition among neighboring empires. But the story did not end with polonium, for the Curies found that even after removing the bismuth fraction, the remaining material from their separations still exhibited intense radioactivity, particularly in those fractions that followed barium in their chemical behavior. Continuing their separations through the autumn of 1898, concentrating the barium fraction and repeatedly recrystallizing its chloride salts, they found the radioactivity becoming more and more concentrated, and by December they were confident that they had evidence of yet another new element, one that they named radium for its intense radiating properties. It was here that spectroscopy played its crucial confirmatory role, for while radioactivity measurements could demonstrate the presence of an unusually active substance, they could not by themselves prove that this substance was a genuinely new element rather than a peculiar form of a known one. The Curies collaborated with the spectroscopist Eugene de Marquet, who examined the barium chloride fractions using spark spectroscopy and found, in addition to the well-known spectral lines of barium, a new line that grew stronger as the radioactivity of the sample increased. This line, which appeared in the ultraviolet region of the spectrum at a wavelength that would later be measured as approximately 381.47 nanometers, did not correspond to any known element and provided the spectroscopic fingerprint that confirmed radium as a distinct elemental species. As the Curies continued their purification work over the following years, processing literally tons of pitchblende residues to obtain weighable quantities of radium compounds, de Marquet continued his spectroscopic examinations, eventually identifying a series of characteristic radium lines that formed a distinctive pattern quite unlike that of barium or any other element. The most prominent lines appeared at wavelengths of 468.23, 482.59, and 381.47 nanometers, among others, creating a spectral signature that allowed radium to be identified even in minute quantities and that provided confirmation of its elemental status independent of its radioactive properties. By 1902, Marie Curie had isolated approximately 1/10 of a gram of radium chloride from several tons of pitchblende residues, a quantity sufficient to determine the atomic weight of radium spectroscopically and chemically, and this painstaking work would contribute to her being awarded the Nobel Prize in Physics in 1903, shared with Pierre and with Becquerel, and later the Nobel Prize in Chemistry in 1911 for her discoveries of radium and polonium. While the Curies were conducting their heroic labors in Paris, other researchers were also investigating radioactive phenomena using spectroscopic and chemical methods. In Germany, Friedrich Giesel, a chemist working at the quinine factory of Butchler and Company in Braunschweig, had independently begun purifying radium from pitchblende residues, and by 1899 he had obtained preparations of considerable purity. Giesel's work was conducted in an industrial rather than academic setting, and he approached the problem with a practical efficiency that allowed him to produce radium samples that were widely distributed to researchers across Europe and beyond. His spectroscopic examinations confirmed the characteristic lines that de Marquet had identified, and his preparations became important tools for the study of radioactivity in laboratories that lacked the resources to purify the element themselves. The spectroscopic study of radioactive materials presented particular challenges that distinguished it from the analysis of ordinary substances. The quantities available were often extraordinarily small, sometimes mere fractions of a milligram, and this required spectroscopists to work at the very limits of their instrument sensitivity. The spark and arc methods that worked well for larger samples had to be adapted for microchemical quantities, using carefully designed electrodes and optimized discharge conditions to produce spectra bright enough to photograph and measure. Moreover, the radioactive materials were often mixed with much larger quantities of chemically similar elements from which they had been incompletely separated, and the spectroscopist had to distinguish the faint lines of the new element from the stronger lines of its companions, a task requiring careful attention to relative intensities and precise wavelength measurements. Another layer of complexity arose from the phenomenon that would eventually be recognized as radioactive decay and transformation. In 1900, William Crookes, the same William Crookes who had developed the vacuum tube and identified the element thallium decades earlier, made a puzzling observation while working with uranium compounds at his London laboratory. He found that he could chemically separate from uranium a substance that carried most of the radioactivity, leaving behind uranium that was nearly inactive. This highly active substance, which he called uranium X, exhibited spectroscopic properties different from those of uranium itself, and yet over time the separated uranium regained its radioactivity while the uranium X lost its activity. This suggested that uranium was continuously producing uranium X, which was in turn transforming into something else, a cycle of production and decay that maintained an equilibrium activity in ordinary uranium samples. The spectroscopic differences between uranium and uranium X were subtle but detectable, and they pointed toward a remarkable conclusion that would take several more years to fully articulate, namely that atoms were not permanent and immutable but could transform from one element into another through radioactive processes. Crookes' observations were confirmed and extended by other researchers, and the spectroscopic identification of different radioactive substances within mixtures became an important tool for tracing these transformations. At McGill University in Montreal, Ernest Rutherford, a New Zealander who had studied under J.J. Thomson at Cambridge before taking up a professorship in Canada, was investigating the radiations emitted by thorium, another radioactive element that had been discovered to share uranium's property of spontaneous emission. Working with the chemist Frederick Soddy, Rutherford found in 1902 that thorium continuously produced a radioactive gas that could be collected and studied independently. This gas, which they called thorium emanation and which would later be identified as an isotope of the element radon, exhibited its own characteristic spectral properties when examined under suitable conditions. The spectroscopy of gaseous radioactive substances presented its own particular challenges, for these gases were present in extremely small quantities and decayed rapidly, sometimes with half-lives measured in seconds or minutes. Researchers had to work quickly to collect the gas and introduce it into discharge tubes where it could be excited to emit light, and then photograph the spectrum before the sample had decayed away. Despite these difficulties, the characteristic spectrum of radon and its decay products could be recorded, providing further evidence that the radioactive transformations were producing genuinely different elemental species rather than merely different chemical states of the original element. Rutherford and Soddy's work led them to propose, in 1902 and 1903, a theory of radioactive transformation that was revolutionary in its implications, suggesting that radioactive atoms were spontaneously breaking apart, emitting particles and energy, and transforming into atoms of different elements. This theory, which explained the observations of Crookes and many others, implied that the ancient dream of transmutation was occurring naturally in radioactive materials, though not in a form that the alchemists would have found useful. Spectroscopy provided crucial evidence for these transformations, demonstrating that the products of radioactive decay had spectral signatures corresponding to known elements or to new elements that could be characterized by their unique spectral lines. Another element whose discovery relied in part on spectroscopic methods was actinium, identified by André-Louis Debierne in Paris in 1899. Debierne, who had studied under the organic chemist Charles Friedel and who became a close associate of the Curies, was examining the pitchblende residues from which radium had been extracted, searching for additional radioactive substances. He found a radioactive material that exhibited chemical behavior similar to titanium and tantalum, and that could be partially separated from the thorium also present in the residues. The spectroscopic identification of actinium was complicated by the difficulty of obtaining it in sufficient purity, for it proved even more challenging to separate than radium, and its characteristic spectral lines were difficult to distinguish from those of accompanying elements. The story of actinium's discovery and characterization extended over many years, with different researchers sometimes disagreeing about its chemical properties and even its existence as a distinct element. Giesel in Germany found a substance he called imanium, which exhibited properties similar to Debierne's actinium, and for some time there was debate about whether these were the same or different elements. Spectroscopic measurements eventually helped to resolve these questions, though the full characterization of actinium and its place in the periodic table would not be firmly established until later decades. Throughout this period, from Becquerel's initial discovery in 1896 through the early years of the 20th century, spectroscopy served both as a tool for identifying new radioactive elements and as a source of questions about the nature of matter itself. The spectral lines of radium and other radioactive substances followed the same general patterns as those of ordinary elements, with sharp, well-defined lines at characteristic wavelengths, and this suggested that radioactive atoms possessed the same kind of electronic structure as stable atoms. The light emitted by radium in a discharge tube was produced by the same mechanisms that produced the light of sodium or calcium or any other element, namely the excitation and subsequent relaxation of electrons in the atom's outer regions. Yet the radioactivity itself, the spontaneous emission of energetic particles and rays from within the atom, pointed to processes occurring at a deeper level, in a region of the atom that spectroscopy could not directly probe. The reconciliation of these two aspects of atomic behavior, the familiar spectroscopic properties and the strange radioactive transformations, would require new theoretical frameworks that were only beginning to emerge in the first decade of the 20th century. The work of understanding how atoms could be stable enough to exhibit sharp spectral lines yet unstable enough to undergo radioactive decay would occupy physicists for many years to come. As the laboratories of Europe accumulated knowledge of radioactive substances and their properties, the characteristic spectral lines of radium in particular became familiar markers, as recognizable to experienced spectroscopists as the yellow lines of sodium or the red line of hydrogen. The ability to identify radium by its spectrum, even in very small quantities, proved valuable not only for pure research but also for practical purposes, as radium found applications in medicine and industry, and the need arose to verify the purity and quantity of radium preparations. Spectroscopy thus served its traditional role of elemental identification while also contributing to a broader revolution in the understanding of matter and energy. The discoveries of the radioactive elements demonstrated once again the power of spectroscopy as a tool for identifying new forms of matter, just as it had served Bunsen and Kirchhoff in their identification of cesium and rubidium decades before. The characteristic pattern of spectral lines remained the most definitive criterion for recognizing a new element, more reliable than chemical behavior alone. For chemical properties could sometimes be ambiguous, while spectral lines were precise and unmistakable. In the strange new world of radioactivity, where substances transformed into one another and emitted invisible rays of unprecedented penetrating power, the familiar light of spectral analysis provided a steady guide, connecting the remarkable new phenomena to the established framework of elemental chemistry and preparing the way for the atomic theories that would emerge in the years to come. In the city of Cambridge, in the east of England, there stands a building of modest brick and practical design, a place where the fundamental nature of matter would slowly reveal itself across decades of careful work. The Cavendish Laboratory, named in honor of the reclusive 18th-century scientist Henry Cavendish, had opened its doors in 1874, and by the closing years of the 19th century it had become one of the most significant centers of experimental physics in the world. Here, in rooms filled with glass apparatus and galvanometers, with vacuum pumps and induction coils, a young director named Joseph John Thomson was pursuing questions about the basic constituents of electricity and matter, questions that would eventually reshape humanity's understanding of the atom itself, though the path forward would prove far more winding and uncertain than anyone could have anticipated in those early years of investigation. Thomson had assumed the directorship of the Cavendish Laboratory in 1884, when he was only 27 years old, a remarkably young age for such a prestigious appointment, though his mathematical abilities and his capacity for guiding experimental work had already demonstrated themselves with sufficient clarity that the selection committee felt confident in their choice. Under his careful stewardship, the laboratory developed a distinctive atmosphere of collaborative inquiry, where theoreticians and experimentalists worked alongside one another, where apparatus was shared and ideas circulated freely through the corridors and workrooms. Thomson himself possessed a curious combination of mathematical sophistication and experimental intuition, able to derive equations with precision while also possessing an almost tactile sense for the behavior of electrical discharges and the peculiarities of cathode rays, those mysterious emanations that emerged from the negative electrode when electrical current passed through evacuated glass tubes. The question of cathode rays had occupied physicists for several decades by the time Thomson turned his sustained attention to the problem in the 1890s. German researchers had tended to favor the view that these rays represented some form of disturbance in the luminiferous ether, a kind of wave phenomenon analogous to light, while British physicists had generally inclined toward the interpretation that the rays consisted of streams of charged particles, tiny corpuscles of matter carrying electrical charge through the vacuum. Thomson's experiments, conducted with meticulous care using improved vacuum apparatus, would eventually settle this dispute in favor of the particle interpretation, though the full implications of his findings would take years to unfold and would create as many puzzles as they resolved. In 1897, Thomson performed a series of measurements that would prove decisive, determining with reasonable precision both the velocity of cathode ray particles and the ratio of their electrical charge to their mass. This ratio, expressed in the notation of the period, appeared extraordinarily large compared to the corresponding value for hydrogen ions in electrolysis, suggesting one of two possibilities. Either these cathode ray corpuscles carried an enormously greater charge than hydrogen ions, or alternatively they possessed a far smaller mass. Thomson concluded, correctly as it would transpire, that the latter interpretation was correct, that these particles were far smaller than even the lightest atom, possessing perhaps 1,000th the mass of a hydrogen atom. He had identified a subatomic particle, a constituent of matter smaller than atoms themselves, and he called these particles corpuscles, though the scientific community would eventually settle upon the term electrons, a word that had been coined some years earlier by the Irish physicist George Johnston Stoney to denote the fundamental unit of electrical charge. The discovery of the electron created an immediate and pressing theoretical difficulty. If atoms contained these tiny negatively charged corpuscles, and if atoms in their normal state were electrically neutral, then positive charge must exist somewhere within the atomic structure to balance the negative charge of the electrons. But where was this positive charge located? And how was it distributed? And what kept the electrons in place rather than flying off due to their mutual repulsion? These questions occupied Thomson and his colleagues for years, and in 1904 he proposed a model of atomic structure that attempted to address them in a coherent fashion, a model that would come to be known, somewhat whimsically, as the Plum pudding model, though Thomson himself never used this particular culinary metaphor in his scientific publications. In Thomson's conception, the atom consisted of a sphere of uniform positive charge, rather like a smooth and featureless pudding, within which the negatively charged electrons were embedded like raisins or currants distributed through the matrix. The positive charge was imagined to be spread continuously throughout the atomic volume, providing a kind of electrical scaffolding that held the electrons in place through electrostatic attraction. Thomson calculated that the electrons would arrange themselves in specific configurations within this positive sphere, forming rings or shells of particular sizes depending on the total number of electrons present, and he hoped that these configurations might explain the periodic properties of the chemical elements, the way that certain elements displayed similar behaviors at regular intervals as one progressed through the list of atomic weights. The model possessed a certain elegant simplicity, and Thomson was able to derive several interesting predictions from its mathematical structure. He worked out the conditions under which arrangements of electrons would be stable, the patterns they would naturally assume under the competing influences of their mutual repulsion and their attraction toward the surrounding positive charge. And these calculations occupied many pages of detailed analysis in his papers and lectures. The electrons, he proposed, could vibrate around their equilibrium positions when the atom was disturbed, oscillating back and forth like tiny pendulums embedded in the positive medium, and these vibrations would presumably be connected somehow to the emission of light, since oscillating charges were known to radiate electromagnetic waves according to Maxwell's equations. Here, then, was where the spectral lines entered the picture, those precise and characteristic frequencies that Bunsen and Kirchhoff had catalogued, that Balmer had fitted to his numerical formula, that represented perhaps the most detailed fingerprint that atoms offered to scientific investigation. If Thomson's model was correct, then the vibration frequencies of electrons within the plum pudding atom ought to correspond to the observed spectral lines, and the patterns of those lines ought to emerge naturally from the mathematics of electron arrangements and oscillation modes. Thomson and his students devoted considerable effort to these calculations, working through the mechanical and electromagnetic theory with great care, hoping to derive the Balmer formula or at least something resembling it from first principles. The results, unfortunately, were disappointing in ways that proved difficult to remedy. The mathematics of electron vibrations in a continuous positive medium yielded predictions quite different from what was actually observed. Most troublingly, The Plum pudding model tended to predict continuous ranges of possible vibration frequencies rather than the sharply discrete lines that spectroscopes revealed with such clarity. When you calculate the normal modes of oscillation for electrons arranged in rings within a uniform positive sphere, you obtain frequency spectra that bear little resemblance to the elegant arithmetic progressions that Balmer had discovered in hydrogen, or to the orderly patterns that other researchers were beginning to identify in helium and the alkali metals. The model could be adjusted and refined. Additional assumptions could be introduced. But the fundamental character of the predicted spectra remained stubbornly wrong in ways that suggested some deeper conceptual difficulty rather than merely incomplete calculation. Thomson's model was not the only attempt during this period to imagine the internal structure of atoms. Lord Kelvin, that grand figure of Victorian physics who had contributed so much to thermodynamics and electromagnetism and the laying of the Atlantic telegraph cable, had proposed his own atomic model based on the mathematics of vortex rings in fluid mechanics. Kelvin imagined atoms as knotted vortices in the ether, stable configurations of swirling fluid motion that might explain the permanence and individuality of different atomic species. Different elements would correspond to different knot types, and the complexity of their spectra might reflect the vibrational modes of these topological structures. The vortex atom model possessed a certain mathematical elegance, and it attracted the attention of some talented mathematicians who explored the properties of knotted curves with great sophistication. But like Thomson's plum pudding, it failed to make contact with the actual numerical regularities that spectroscopists had discovered. The Balmer formula remained unexplained, a numerical fact without a physical foundation. In Japan, a physicist named Hantaro Nagaka was contemplating a rather different approach to atomic structure, one that would prove in some respects more prescient than the models favored by his European contemporaries, though it too would ultimately fail to resolve the spectral puzzle. Nagaka had studied in Europe and was familiar with the latest developments in electromagnetic theory and the recent discoveries concerning electrons and radioactivity. In 1904, the same year that Thomson published his detailed account of the plum pudding model, Nagaka presented to the Tokyo Mathematical and Physical Society his conception of what he called a Saturnian atom, taking his inspiration from the ringed planet and the mathematical analysis that Maxwell had performed decades earlier on the stability of Saturn's rings. In Nagaka's model, published later that year in the Philosophical magazine where it would reach the attention of European physicists, the atom consisted of a massive central body carrying positive charge, around which electrons orbited in one or more circular rings, much as the particles constituting Saturn's rings orbit around the planet's enormous bulk. This arrangement was strikingly different from Thomson's conception, placing the positive charge at a concentrated center rather than spreading it throughout the atomic volume, and it anticipated in its general form the model that Ernest Rutherford would propose several years later on the basis of his famous scattering experiments. Nagaka worked out some of the mechanical properties of his orbital system, considering the conditions under which the electron rings would remain stable against small perturbations, and he attempted to connect the orbital frequencies to spectral emission. But the Saturnian model encountered its own severe difficulties rooted in the classical theory of electromagnetism that Nagaka, like all physicists of his time, accepted as fundamentally correct. According to Maxwell's equations, an accelerating electric charge must radiate electromagnetic energy, must continuously emit waves as it changes velocity. An electron moving in a circular orbit is constantly accelerating, constantly changing direction even if its speed remains uniform, and therefore it should continuously radiate energy according to classical electromagnetic theory. This radiation would carry energy away from the orbital system. And as the electron lost energy, it would spiral inward toward the central positive charge, moving faster and faster, radiating at higher and higher frequencies, until within a tiny fraction of a second it would collapse into the center and the atom would cease to exist. The classical electromagnetic theory that explained so much of light and radio waves and all manner of phenomena seemed to forbid the very existence of stable planetary atoms. Nagaka was aware of this difficulty, and he attempted to argue that under certain conditions the radiation might be suppressed or the instability might develop very slowly. But these arguments were not convincing to most physicists who considered the matter carefully. The Saturnian model remained an interesting speculation, noted in the literature and occasionally referenced, but it did not displace the plum pudding model from its position as the most widely discussed conception of atomic structure in the years immediately following 1904. Meanwhile, Thomson continued refining his estimates of how many electrons an atom might contain. His early calculations, based on various lines of evidence including the scattering of light by gases and the absorption of cathode rays passing through matter, suggested that atoms might contain very large numbers of electrons, perhaps 1,000 or more for the heavier elements, roughly proportional to the atomic weight. This estimate would later prove to be far too high, as more refined measurements and theoretical considerations would eventually establish that the number of electrons in a neutral atom equals the atomic number, the element's position in the periodic table, giving hydrogen just 1 electron and gold 79, rather than the hundreds or thousands that Thomson had initially supposed. But in the early years of the 20th century, these matters remained uncertain, and the large electron numbers were incorporated into Thomson's attempts to model atomic structure and spectral behavior. The research culture at the Cavendish laboratory during these years was one of patient accumulation, of careful measurement and gradual theoretical development. Thomson directed a growing stream of research students from Britain and from around the world, guiding their experimental projects, suggesting theoretical approaches, fostering an atmosphere of rigorous but collegial inquiry. The laboratory possessed excellent apparatus for its time, vacuum systems capable of achieving high degrees of evacuation, sensitive electroscopes and galvanometers, spectroscopic equipment for analyzing light, and the technical skill to construct and modify instruments as research demands required. Yet even with these resources and this intellectual environment, the fundamental puzzle of spectral lines resisted solution. The difficulty was not merely technical but conceptual. All of the atomic models proposed during this period, whether Thomson's plum pudding or Kelvin's vortex rings or Nagaka's Saturnian system, were constructed using the physics of the 19th century, using classical mechanics and classical electromagnetism, using the assumption that energy could vary continuously and that the ordinary laws of motion applied to particles of all sizes from planets to electrons. Within this framework, the sharp discrete lines of atomic spectra seemed almost paradoxical, a phenomenon that classical physics could describe empirically but could not derive from first principles. The Balmer formula, with its integers and its curious Rydberg constant, remained a numerical recipe without a theoretical foundation, an island of precise quantitative knowledge surrounded by conceptual uncertainty. Some physicists began to suspect, as the first decade of the 20th century progressed, that entirely new principles might be required, that the familiar laws which worked so well for macroscopic objects might need modification at the atomic scale. The quantum hypothesis that Max Planck had introduced in 1900 to explain the spectrum of thermal radiation, and that Albert Einstein had extended in 1905 to explain the photoelectric effect, suggested that energy might be fundamentally granular at the microscopic level, that it might come in discrete packets or quanta rather than being infinitely divisible. But how these quantum ideas might connect to atomic structure and spectral emission remained obscure for several years, a tantalizing hint rather than a clear solution. For now, as we rest here in these early years of atomic speculation, the electron has been discovered and its properties measured. The atom has been revealed to possess internal structure rather than being truly indivisible as its name suggested. But the precise arrangement of that structure and its connection to the patterns of light remain wrapped in uncertainty. Thomson's Plum pudding model sits at the center of discussion, challenged by its failures with spectral predictions but not yet displaced by any more successful alternative. Nagaka's Saturnian atom waits in the literature, its orbital conception perhaps closer to what will eventually emerge, but burdened by classical electromagnetic theory's prohibition against stable orbits. And in laboratories across Europe and beyond, spectroscopists continue their patient cataloguing of lines and wavelengths, accumulating the precise numerical data that any successful atomic theory must eventually explain. The story will continue, as scientific stories always do, with new experiments and new ideas gradually clarifying what now seems murky, but that continuation can wait for another time. For now, there is comfort in knowing that even the most fundamental questions are approached through patient work, through careful measurement, through the slow accumulation of understanding that characterizes science at its most genuine. The electrons embedded in their positive matrix, vibrating at frequencies that somehow produce the lines that spectroscopes reveal, represent a moment of partial knowledge, of physics in transition, and there is a quietness in contemplating such moments, a recognition that understanding comes gradually and that uncertainty is simply part of the process. The Plum pudding model, for all its limitations, was a serious attempt to make sense of new discoveries, and the physicists who developed and debated it were engaged in the patient work of trying to understand the material world at its most fundamental level, a task that continues to this day and that perhaps never fully concludes. In the years following the discovery of radioactivity, the laboratory at Manchester University became a place of quiet but persistent investigation, where the fundamental structure of matter was slowly, carefully, being revealed through experiments that required great patience and meticulous attention to detail. It was here, between the years 1909 and 1911, that Ernest Rutherford, along with his colleagues Hans Geiger and a young undergraduate named Ernest Marston, would conduct a series of experiments that would fundamentally alter our understanding of the atom, though the significance of what they observed would take some time to fully appreciate, and the path from experimental observation to theoretical interpretation would prove to be neither straightforward nor immediate. Ernest Rutherford had arrived at Manchester in 1907, having already established himself as one of the foremost investigators of radioactive phenomena through his earlier work at McGill University in Montreal. He was a large man with a booming voice and tremendous energy, though when engaged in careful experimental work he could demonstrate remarkable patience and attention to the smallest details. The laboratory he inherited at Manchester was well equipped for the study of radioactive emissions, and Rutherford set about gathering a talented group of researchers who shared his interest in understanding the nature of the particles emitted by radioactive substances and how these particles might be used as probes to investigate the structure of matter itself. The particles that would prove most useful for this investigation were what Rutherford called alpha particles, which he had identified during his earlier work as being identical to helium atoms carrying a positive electrical charge, having been stripped of their electrons during the process of radioactive emission. These alpha particles were ejected from radioactive substances at tremendous velocities, traveling at speeds of roughly 15,000 miles per second, and they carried sufficient energy to produce tiny flashes of light when they struck screens coated with zinc sulfide, a phenomenon that allowed individual particles to be detected and counted. It was this ability to detect single particles, one flash at a time, that made the scattering experiments possible, though the counting itself was tremendously tedious work that strained the eyes and tested the patience of even the most dedicated observer. The experimental apparatus used in these investigations was elegantly simple in conception, though demanding in execution. The source of alpha particles was typically what was called radium emanation, which we now know as the radioactive gas radon, collected from radium samples and sealed within small glass tubes. This emanation provided a concentrated and reasonably stable source of alpha particles that could be directed toward the target material. The particles would emerge from a small opening in a lead container and travel toward a thin metal foil, passing through it or being deflected by interactions with the atoms of the foil. A zinc sulfide screen positioned at various angles around the foil would register the arrival of alpha particles as tiny scintillations, brief sparkles of light that could be observed through a low-power microscope in a completely darkened room by an observer whose eyes had been allowed to adapt to the darkness for some considerable time beforehand. Hans Geiger, who was Rutherford's principal assistant in these matters, had been studying the scattering of alpha particles for some years, carefully measuring the small angles through which most particles were deflected as they passed through thin metal foils. This scattering was expected behavior, as the prevailing model of atomic structure at the time, proposed by J.G. Thomson and often referred to as the Plum pudding model, suggested that the positive charge of an atom was spread throughout its volume like a diffuse cloud, with the much smaller electrons embedded within it like plums in a pudding or raisins in a cake. Such a diffuse distribution of charge would produce only gentle deflections of the fast-moving alpha particles, and indeed this is what Geiger observed in the vast majority of cases, with most particles passing through the foil with only minor changes to their direction of travel. It was in 1909 that Rutherford suggested to Geiger that his undergraduate student Ernest Marston might undertake an investigation into whether any alpha particles were scattered through very large angles, perhaps even bouncing backward from the foil rather than passing through it. This was considered something of a long shot, as the prevailing theory gave no reason to expect such behavior, but Rutherford was known for his thorough approach to experimental investigation and his willingness to test ideas that might seem unlikely. And so Marston, working under Geiger's supervision, set about the painstaking task of looking for alpha particles that had been deflected through angles greater than 90 degrees. Effectively bouncing back toward the source from which they had come. The experiment required the zinc sulfide screen to be positioned on the same side of the gold foil as the alpha particle source, so that only particles that had been reflected backward would be detected. The gold foil was chosen because gold can be beaten into extraordinarily thin sheets, only a few hundred atoms thick, and because its high atomic weight was expected to produce stronger scattering effects than lighter elements. Marston would sit in the darkened room, his eyes fully adapted to the absence of light, counting the tiny flashes that appeared on the screen, one by one, hour after hour, keeping careful records of everything he observed. What Marston found was both unexpected and puzzling. although the vast majority of alpha particles passed through the foil with only slight deflections. As expected, a small but definite number were scattered through very large angles, and some came almost straight back toward the source. The fraction was small. Approximately 1 particle in 8,000 experienced this dramatic backward scattering when directed at gold foil, but the effect was unmistakable and reproducible. Here was something that the Thomson model of the atom could not readily explain. For a diffuse distribution of positive charge should not be capable of producing such violent deflections of particles traveling at such tremendous velocities. Rutherford's later description of his reaction to this discovery has become one of the most quoted passages in the history of physics. He compared the observation to firing a 15-inch artillery shell at a piece of tissue paper and having it bounce back and hit you. The 15-inch shell was a reference to the largest naval guns of the era, weapons capable of hurling projectiles weighing nearly a ton, and the comparison conveyed his astonishment that something as massive and fast-moving as an alpha particle could be turned completely around by an encounter with a thin metal foil. Something within the atom must be capable of exerting a tremendously strong repulsive force on the alpha particle, strong enough to reverse its direction of motion entirely, and this something must be quite different from the diffuse cloud of positive charge envisioned by Thomson. Yet the path from this experimental observation to the theoretical interpretation that we now consider correct was not immediate, and Rutherford spent considerable time, approximately 2 years in fact, considering various possible explanations for what had been observed. He explored whether multiple small deflections might somehow combine to produce the occasional large deflection, a possibility that mathematical analysis showed to be inadequate to explain the observed frequency of backward scattering. He considered whether the alpha particles might be interacting with the electrons within the atom, but the electron was known to be far too light to deflect the much heavier alpha particle through such large angles. He pondered whether the effect might be due to some property of the surface of the foil rather than the atoms within it, but this too failed to account for the observations. During this period of contemplation and analysis, Rutherford drew upon the mathematical abilities of several colleagues to help work through the theoretical implications of various atomic models. Among those who contributed to this mathematical analysis was the Japanese physicist Kinoshita Torihiko, who was working at Manchester during this period and who helped to develop some of the detailed calculations needed to compare theoretical predictions with experimental observations. The mathematics involved was not particularly advanced by the standards of theoretical physics, being largely a matter of applying the well-understood principles of electrostatic forces and classical mechanics, but the careful working through of the calculations for various possible atomic structures was essential to determining which model could account for the experimental results. It was in 1911, approximately 2 years after Marston's initial observations, that Rutherford published his revolutionary paper proposing what has come to be known as the nuclear model of the atom. In this model, Rutherford suggested that the positive charge of an atom, along with most of its mass, was concentrated in a very small central region, which he called the nucleus, rather than being spread throughout the volume of the atom as Thomson had proposed. The electrons, carrying negative charge, would occupy the much larger volume surrounding this tiny nucleus, and it was the concentrated positive charge of the nucleus that was responsible for the occasional dramatic deflection of alpha particles. When an alpha particle happened to approach very close to a nucleus, the intense electrostatic repulsion between the positive charges of the alpha particle and the nucleus would be sufficient to reverse the particle's direction of motion, sending it bouncing back the way it had come. The mathematics of this model proved to be in excellent agreement with the experimental observations. Rutherford was able to calculate exactly what fraction of alpha particles should be scattered through various angles if the positive charge were concentrated in a tiny nucleus, and these calculations matched the experimental data with remarkable precision. The nucleus, according to Rutherford's analysis, must have a radius of approximately 10 to the power of -14 meters. Roughly 10,000 times smaller than the atom as a whole. The atom, in this view, was mostly empty space, with the tiny nucleus at its center and the electrons somehow distributed throughout the vast empty volume surrounding it. This model was tremendously successful in explaining the scattering experiments, but it immediately created a profound crisis for atomic physics and for the understanding of atomic spectra that had been gradually developing since the time of Kirchhoff and Bunsen. The difficulty was fundamental and seemingly insoluble within the framework of classical physics. If the electrons were distributed throughout the volume of the atom surrounding the nucleus, they must somehow be held there against the attractive electrostatic force pulling them toward the oppositely charged nucleus. The obvious solution, by analogy with the planets orbiting the Sun, would be to have the electrons orbiting the nucleus, with their centripetal acceleration providing the force needed to maintain them in curved paths rather than falling into the center. However, there was a fatal problem with this picture. According to the well-established laws of classical electromagnetism, developed by Maxwell and thoroughly confirmed by experiment, an accelerating electric charge must continuously radiate electromagnetic energy. An electron traveling in a circular orbit around a nucleus is constantly accelerating, as it is continuously changing direction even if its speed remains constant, and therefore it should be continuously emitting electromagnetic radiation. This radiation would carry away energy from the electron, and as the electron lost energy it would spiral inward toward the nucleus, emitting radiation of increasingly higher frequency as the orbital radius decreased. The entire process should take only a tiny fraction of a second, perhaps 100 millionth of a second or so, after which the electron would have collapsed into the nucleus and the atom would cease to exist. This was clearly not what happened in nature. Atoms were known to be stable, persisting indefinitely without collapsing, and they emitted light only under certain circumstances and then only at specific discrete wavelengths, not in the continuous sweep of frequencies that a spiraling electron would produce. The beautiful spectral lines that had been studied and catalogued for half a century, the regularities discovered by Balmer and Heidelberg, the precise wavelengths that served as fingerprints for each element, all of this seemed completely incompatible with a model in which electrons orbited a central nucleus according to the laws of classical physics. The Rutherford model thus presented physicists with a stark choice. Either the experimental evidence pointing to a nuclear atom was somehow mistaken, which seemed unlikely given its clarity and reproducibility, or the laws of classical physics, which had served so magnificently for so many purposes, were somehow not applicable to the interior of the atom. The evidence for the nuclear atom was too strong to dismiss, and so it gradually became apparent that some new physics would be required to understand how electrons could stably occupy regions around an atomic nucleus without continuously radiating their energy away. This crisis in atomic physics, created by the success of Rutherford's scattering experiments, was the immediate background against which the next great advance in understanding atomic spectra would occur. The spectroscopic regularities discovered by Balmer, Heidelberg, and others remained unexplained, tantalizing hints of an underlying order that classical physics could not account for. The photon hypothesis of Einstein suggested that light came in discrete packets of energy, but how this related to the structure of atoms remained unclear. The nuclear model of Rutherford showed that atoms had a concentrated positive core with electrons somehow surrounding it. But the dynamics of this arrangement were utterly mysterious within the classical framework. The stage was thus set for a synthesis, a bringing together of the quantum ideas that had been tentatively introduced by Planck and Einstein with the nuclear atomic model established by Rutherford's scattering experiments. This synthesis would finally explain the long mysterious spectral lines and would establish the foundation for our modern understanding of atomic structure. But that development, which would come from a young Danish physicist named Niels Bohr who arrived at Manchester to work with Rutherford in 1912, would require yet another bold departure from classical thinking. Another willingness to accept that the microscopic world operated according to principles quite different from those governing the behavior of everyday objects. For now, as we rest with the knowledge of Rutherford's nuclear atom, we can appreciate both the elegance of the experimental work that revealed this structure and the profound difficulties it created for theoretical understanding. The scattering of alpha particles, counted one flash at a time in darkened rooms by patient observers, had revealed that the atom was mostly empty space with a tiny, dense, positively charged nucleus at its heart. The precise arrangement of the electrons around this nucleus, and how this arrangement could give rise to the beautiful discrete spectra that had been observed and catalogued for so many years, remained for the moment a puzzle, awaiting the next gentle step forward in human understanding. In the year 1912, a young Danish physicist named Niels Bohr arrived in England, carrying with him a doctoral thesis on the electron theory of metals and a quiet determination to understand the fundamental structure of matter. He was 26 years old, soft-spoken in manner, and possessed of a gentle persistence that would serve him well in the years to come. His first destination was the Cavendish Laboratory at Cambridge, where the great J.G. Thomson presided over what was then considered the foremost center for experimental physics in the world. Thomson had discovered the electron some 15 years earlier, and his laboratory attracted young researchers from across Europe and beyond, all hoping to learn from the master and to contribute their own small pieces to the growing edifice of atomic physics. Bohr had translated his thesis into English himself, a laborious process that resulted in prose that was sometimes difficult to follow, and he had brought it with him in the hope that Thomson might read it and offer guidance on its ideas. The months at Cambridge proved, however, to be rather less fruitful than Bohr had anticipated, and this period remains one of the quieter disappointments in his early career. Thomson was busy with his own research and with the administration of a large laboratory, and he showed little interest in reading the young Dane's theoretical work on electrons in metals. The thesis sat unread, and Bohr found himself somewhat adrift, attending lectures and working on experiments but never quite finding the intellectual engagement he sought. He improved his English, which had been somewhat uncertain upon his arrival, and he took up football with the laboratory's team, finding in this physical activity a pleasant diversion from his frustrations. But the deep questions about atomic structure that occupied his thoughts found little resonance in the Cavendish's predominantly experimental atmosphere, and by the end of 1911, Bohr was ready for a change of scene and a new direction. That change came in the form of an invitation to visit Manchester, where Ernest Rutherford had established his own remarkable laboratory and where the nuclear model of the atom had recently been born. Bohr had met Rutherford briefly during a visit to Cambridge, and something in the New Zealander's direct manner and physical intuition appealed to the young theorist. In March of 1912, Bohr made the journey north to Manchester, and within a short time he knew that he had found his intellectual home. Rutherford's laboratory was smaller than the Cavendish, less formal in its hierarchy, and animated by a spirit of bold inquiry that suited Bohr's temperament perfectly. The nuclear atom, with its tiny dense center and its orbiting electrons, presented exactly the kind of fundamental problem that Bohr wished to address, and he threw himself into the work with renewed energy and purpose. The difficulty with Rutherford's atomic model, as we have gently discussed in earlier passages, was that it could not explain why atoms were stable at all. According to classical electromagnetic theory, an electron circling a nucleus should continuously radiate energy, spiraling inward until it crashed into the center of the atom in a tiny fraction of a second. This clearly did not happen, as the world around us consisted of stable atoms that persisted indefinitely, but no one knew quite how to resolve the contradiction. Bohr pondered this problem during his months in Manchester, turning it over in his mind with that patient, almost meditative quality of thought that characterized his approach to physics. He recognized that classical physics was somehow inadequate to the task, and his thoughts turned increasingly to the quantum ideas that Max Planck had introduced in 1900 and that Einstein had developed in his work on light and on the specific heats of solids. During this period, Bohr also became aware of the work of John William Nicholson, an English mathematical physicist who had published several papers attempting to explain spectral lines using quantum concepts. Nicholson had proposed that the angular momentum of electrons in atoms might be related to Planck's constant, and although his specific models of atomic structure were rather different from what Bohr would eventually develop, the general idea of connecting quantum mechanics to the motion of electrons within atoms left a definite impression on the young Dane. Nicholson's work was complicated and in some ways speculative, involving atoms in stellar atmospheres and hypothetical elements that did not exist on Earth. But the mathematical techniques he employed and the fundamental insight that angular momentum might be quantized in some manner provided a useful stepping stone for Bohr's own developing ideas. Science progresses in this way, with each researcher building upon the work of those who came before, sometimes in directions that the original authors never anticipated. Bohr returned to Copenhagen in the summer of 1912. His head full of ideas about atomic structure but without yet having found the key that would unlock the puzzle. He became engaged to Margrethe Norland, and the happiness of this period in his personal life provided a gentle counterpoint to the intense intellectual struggles that occupied his working hours. He continued to think about electrons and their orbits, about the quantum and its implications, about the stability of atoms and the mystery of their spectra. The pieces of the puzzle were all before him, but they had not yet fallen into place, and for several months he worked without the flash of insight that would eventually come. That illuminating moment arrived in early 1913, and it came through a conversation with a young spectroscopist named Hans Marius Hansen. The two men had known each other since their student days in Copenhagen, and Hansen was familiar with the empirical regularities that had been discovered in atomic spectra over the preceding decades. During their conversation, Hansen mentioned the Balmer formula, that elegant mathematical expression that Johannes Balmer had published nearly 30 years earlier to describe the wavelengths of the visible lines in the hydrogen spectrum. Bohr had not been particularly focused on spectroscopy up to this point, his attention having been directed more toward the general problem of atomic stability. But when Hansen explained Balmer's formula to him, something remarkable happened. The connection between the quantum theory he had been developing and the observed spectral lines of hydrogen became suddenly and beautifully clear. Bohr himself later described this moment of recognition by saying that as soon as he saw Balmer's formula, everything became clear. The empirical regularity that Balmer had discovered decades earlier now revealed itself as a direct consequence of the quantum structure of the atom. What Bohr realized, in that moment of clarity, was that the Balmer formula could be derived from first principles if one assumed that electrons in atoms could only occupy certain specific orbits, and that light was emitted or absorbed only when electrons jumped between these orbits. The energy of the emitted light corresponded exactly to the difference in energy between the initial and final orbits, and the specific wavelengths observed in the hydrogen spectrum were simply a reflection of the specific energy levels available to the electron in a hydrogen atom. This insight unified the quantum theory of radiation with the nuclear model of the atom and with the accumulated spectroscopic observations of half a century. It was, by any measure, a profound moment in the history of physics, though Bohr himself approached it with his characteristic modesty and his determination to work out all the details with proper mathematical rigor. In the months that followed, Bohr worked intensively to develop his theory into a complete and coherent framework. The result was a trilogy of papers, each quite long and densely argued, which he submitted to the Philosophical magazine in the summer of 1913. The papers appeared in the July, September, and November issues of that year, under the general title On the Constitution of Atoms and Molecules, and they represent one of the foundational documents of 20th century physics. The writing was careful and thorough, building the argument step by step from basic principles, and though the prose was sometimes difficult to follow, the underlying ideas were revolutionary in their scope and implications. The first of Bohr's postulates addressed the paradox of atomic stability that had plagued Rutherford's nuclear model. Bohr simply declared that electrons in certain special orbits, which he called stationary states, do not radiate energy, despite what classical electromagnetic theory might predict. This was a bold departure from established physics, an assertion that the classical laws which worked so well for large-scale phenomena simply did not apply to the tiny world of the atom. Bohr did not attempt to explain why electrons in stationary states should be exempt from the requirement to radiate. He simply postulated it as a fundamental fact about the quantum world. This willingness to accept the quantum as a basic feature of reality, rather than trying to derive it from classical principles, was characteristic of Bohr's approach and would become even more pronounced in his later philosophical writings about the nature of physics. The second postulate concerned the emission and absorption of light. Bohr proposed that radiation is emitted or absorbed only when an electron makes a transition from one stationary state to another. The frequency of the emitted light is determined by the energy difference between the two states. According to the relation that Planck and Einstein had introduced, the energy of the light quantum equals Planck's constant multiplied by the frequency. This postulate connected the quantum theory of radiation directly to the structure of atoms and explained why atomic spectra consisted of discrete lines rather than continuous bands of color. Each spectral line corresponded to a specific transition between two energy levels, and the pattern of lines in the spectrum was a direct map of the energy level structure of the atom. The third postulate provided the mathematical rule for determining which orbits were allowed. Bohr proposed that the angular momentum of an electron in a stationary state must be an integer multiple of Planck's constant divided by 2 pi. This quantity, which is sometimes written as h bar, represents the fundamental unit of angular momentum in the quantum world, and Bohr's postulate restricted the electron to orbits whose angular momentum was exactly 1, or 2, or 3, or some other whole number times this basic unit. This quantization of angular momentum was the key that connected the abstract quantum theory to the specific numerical values observed in atomic spectra. With these three postulates in hand, Bohr was able to derive a formula for the wavelengths of light emitted by hydrogen atoms, and this formula turned out to be identical to the empirical Balmer formula that had been known for nearly 3 decades. Moreover, Bohr's derivation expressed the Rydberg constant, that mysterious numerical factor that appeared in the Balmer formula and in all the other series formulas for hydrogen, in terms of fundamental physical constants: the mass of the electron, the charge of the electron, Planck's constant, and the speed of light. When Bohr calculated the value of the Rydberg constant from these fundamental quantities, the result agreed remarkably well with the experimental value that had been determined from spectroscopic measurements. This was a stunning theoretical triumph, for it showed that the regularities observed in atomic spectra were not merely empirical patterns but were direct consequences of the fundamental quantum structure of matter. The derivation itself, which Bohr presented in careful mathematical detail, involved calculating the energy of an electron in a circular orbit around the hydrogen nucleus, using the familiar laws of electrostatics and mechanics, but with the additional constraint that the angular momentum must be quantized. The result was that the energy of the electron depended on the square of an integer, the quantum number n, in a specific way that could be calculated from first principles. When an electron jumped from an orbit with a higher quantum number to one with a lower quantum number, it emitted a photon whose energy corresponded to the difference between the two energy levels, and the wavelength of this photon could be calculated from the Planck-Einstein relation. The formula that emerged from this calculation was precisely the Balmer formula, with the Rydberg constant expressed in terms of fundamental constants rather than being merely an empirical fitting parameter. The agreement between theory and experiment was close but not perfect, as experimental precision had improved considerably since Balmer's time, and there were small discrepancies that could not be explained by Bohr's simple circular orbit model. Some of these discrepancies would later be resolved by Arnold Sommerfeld's extension of the Bohr theory to include elliptical orbits and relativistic corrections. But even in its original form, Bohr's theory represented an enormous advance in our understanding of atomic structure. For the first time, the spectral lines of an element could be predicted from first principles rather than simply catalogued and fitted to empirical formulas. The reception of Bohr's theory among established physicists was, perhaps predictably, rather mixed, and some of the most distinguished figures in the field expressed considerable skepticism. Lord Rayleigh, who had made fundamental contributions to the physics of waves and radiation over a career spanning more than half a century, was particularly cool in his assessment. At 70 years of age, Rayleigh had seen many theories come and go, and he found Bohr's willingness to abandon classical electromagnetic theory within the atom to be troubling rather than liberating. The postulate that electrons in stationary states simply do not radiate, despite having the acceleration that classical theory would require for radiation, seemed to Rayleigh more like a suspension of physical law than an explanation of atomic behavior. He was not alone in this assessment, and several other physicists of his generation found Bohr's approach too radical a departure from the established framework of classical physics. Other responses were more nuanced, combining appreciation for Bohr's achievement with reservations about the theoretical foundations. The theory was clearly successful in reproducing the hydrogen spectrum, and the derivation of the Rydberg constant from fundamental quantities was impressive by any standard, but the postulates themselves seemed arbitrary and disconnected from any deeper physical principle. Why should angular momentum be quantized in units of Planck's constant divided by 2 pi? Why should electrons in certain orbits be exempt from the classical requirement to radiate? These questions would occupy physicists for more than a decade, until the development of quantum mechanics in the 1920s provided a more fundamental framework within which Bohr's postulates could be understood and from which they could, in some sense, be derived. Einstein, characteristically, recognized both the power and the limitations of Bohr's approach. He appreciated the way that Bohr had connected the quantum theory of radiation to the structure of atoms, and he saw the derivation of the Rydberg constant as a significant achievement. But he also worried about the logical status of the theory, about the way it combined classical mechanics with quantum postulates in a manner that seemed inconsistent and ad hoc. The electron in a stationary state was described using classical equations of motion, but the transitions between states involved quantum ideas that had no classical analog. This hybrid character of the theory troubled Einstein, as it troubled many others, though it would be some years before a more coherent framework emerged. For Bohr himself, the 1913 papers were just the beginning of a long engagement with atomic physics that would span the rest of his career. He returned to Manchester briefly after the papers were published, and Rutherford received the work with his characteristic blend of enthusiasm and skepticism. Rutherford appreciated the experimental success of the theory, its ability to explain and predict spectroscopic observations, but he too had reservations about the theoretical foundations. In one often quoted remark, he noted that the theory worked well enough for hydrogen but that it was not clear how it could be extended to more complex atoms. This would indeed prove to be one of the limitations of Bohr's original model, which required extensive modification and extension before it could be applied to the spectra of elements heavier than hydrogen. The years immediately following 1913 saw rapid development and extension of Bohr's ideas by physicists around the world. The theory was applied to ionized helium, which has only one electron and thus resembles hydrogen in its basic structure, and the agreement with experiment was again remarkably good. Attempts to extend the theory to neutral helium and to heavier elements met with partial success and partial failure, revealing both the power and the limitations of the original framework. The field of atomic spectroscopy, which had accumulated vast amounts of empirical data over the preceding half-century, now had a theoretical framework within which to interpret that data, and the interaction between theory and experiment became increasingly productive and sophisticated. Here, perhaps, we might pause in our narrative and allow ourselves a moment of quiet reflection on what Bohr achieved in that remarkable year of 1913. He had taken the nuclear model of the atom, which Rutherford had proposed just 2 years earlier, and combined it with the quantum ideas of Planck and Einstein to create a new picture of atomic structure. In this picture, electrons circled the nucleus in specific allowed orbits, emitting or absorbing light only when they jumped between these orbits. The wavelengths of the emitted light were determined by the energy differences between the orbits, and the allowed orbits were determined by the quantization of angular momentum. The theory was not complete, and it raised as many questions as it answered, but it represented a decisive step forward in our understanding of the atom and of the quantum world that governs its behavior. The spectral lines that had fascinated and puzzled generations of spectroscopists were now understood, at least in principle, as windows into the internal structure of atoms, as signatures of the quantum jumps that electrons make as they move between allowed energy states. In the gentle unfolding of scientific understanding, there come moments when a single series of experiments can illuminate what had previously remained shrouded in uncertainty, and the work of Henry Gwyn Jeffreys Moseley, conducted in the laboratories of Manchester between 1913 and 1914, represents precisely such a clarifying moment in the history of atomic spectroscopy. Moseley was a young man of considerable talent and quiet determination. Born in 1887 into a family with deep roots in the natural sciences, his father having been a professor of anatomy and physiology, and his grandfather having accompanied the voyage of the HMS Beagle as a naturalist and shell collector. There was, it seems, something in the very fabric of the Moseley family that inclined its members toward careful observation and systematic inquiry, and Henry embodied these qualities with a particular intensity that would prove both remarkable and, in its ultimate expression, tragically brief. Moseley had arrived at Manchester to work under Ernest Rutherford, that formidable figure from New Zealand whose nuclear model of the atom had so recently transformed our understanding of atomic structure, and in this environment of intellectual ferment and experimental rigor, the young researcher found himself drawn to a question that had long troubled those who studied the periodic table of the elements. The table, as arranged by Dmitri Mendeleev and others, ordered the elements primarily according to their atomic weights, the mass of their atoms relative to hydrogen, and while this arrangement had proven remarkably successful in grouping elements with similar chemical properties, there remained troubling anomalies that suggested atomic weight alone could not be the fundamental ordering principle. The element tellurium, for instance, possessed a greater atomic weight than iodine, yet its chemical properties clearly indicated it should precede iodine in the table, and similarly cobalt weighed more than nickel while obviously belonging before it in the sequence of elements. These inversions had puzzled chemists for decades, suggesting that some deeper property, some more fundamental characteristic than mere atomic weight, must determine an element's true position in the grand ordering of matter. The theoretical groundwork for understanding this deeper property had been laid, in part, by the work of a Dutch amateur physicist named Antonius van den Broek, who had proposed in 1911 that the nuclear charge of an atom, the positive charge carried by its nucleus, might increase by 1 unit from one element to the next, and that this nuclear charge, rather than atomic weight, might serve as the true ordering principle of the periodic table. Rutherford himself had been receptive to this idea, though direct experimental confirmation remained elusive, and it was into this context of theoretical suggestion and experimental uncertainty that Moseley directed his considerable abilities. The tool that Moseley would employ in his investigations was the X-ray, that penetrating form of radiation discovered by Wilhelm Röntgen in 1895, and specifically the characteristic X-rays that different elements produce when bombarded with high-energy electrons. When energetic electrons strike an element, they can knock electrons from the innermost shells of that element's atoms, and when outer electrons fall inward to fill these vacancies, they release energy in the form of X-rays with frequencies characteristic of that particular element. These characteristic X-rays had been observed and studied by Charles Barkla, who had identified distinct series of X-ray emissions which he designated the K-series and L-series. But the precise relationship between these X-ray frequencies and the fundamental properties of atoms remained unclear. Moseley's experimental approach combined elegance with systematic thoroughness in a manner that exemplified the best traditions of physical measurement. He constructed an apparatus in which samples of different elements could be bombarded with cathode rays, the resulting X-rays then passing through a thin window to strike a crystal of potassium ferrocyanide, which served as a diffraction grating according to the principles that Max von Laue and the Braggs had recently established. The crystal would diffract the X-rays at angles dependent upon their wavelengths, and by recording these diffracted rays on photographic plates, Moseley could determine with considerable precision the frequencies of the characteristic X-rays emitted by each element. The apparatus required constant attention and careful adjustment. The work was painstaking and often continued late into the night, but Moseley possessed the patient temperament and steady hands that such delicate measurements demanded. In this work, Moseley was assisted by his colleague Charles Galton Darwin, a physicist whose name carried echoes of his illustrious grandfather, the naturalist Charles Darwin, though the younger Darwin had directed his considerable intellect toward the abstractions of theoretical physics rather than the observation of finches and barnacles. Darwin had developed mathematical treatments of X-ray diffraction and scattering that proved invaluable in interpreting the experimental results, and the collaboration between the two young scientists represented a fruitful combination of experimental skill and theoretical insight. Together they refined the techniques and analyzed the patterns of X-ray emission, though it was Moseley who conceived the central experimental program and who would draw from it the conclusions that would reshape our understanding of atomic identity. Beginning with aluminium and proceeding methodically through the elements, Moseley measured the characteristic X-ray frequencies of one substance after another, including calcium and titanium and vanadium, chromium and manganese and iron, cobalt and nickel and copper and zinc, and as he extended his measurements to heavier elements, he found that he could eventually trace the pattern through silver and gold and numerous elements in between. The photographic plates accumulated, each bearing the distinctive marks of X-rays diffracted at specific angles, each revealing the characteristic frequencies of a particular element. And as Moseley examined these accumulating data, a pattern of striking simplicity began to emerge from the complexity of his measurements. What Moseley discovered was a relationship of elegant mathematical form, a relationship that would come to bear his name and that would provide the definitive answer to the question of atomic ordering. When he plotted the square root of the characteristic X-ray frequencies against the position of each element in the periodic table, the points fell upon a straight line with remarkable precision, and this linear relationship suggested that the frequency of an element's characteristic X-rays was proportional to the square of some integer associated with that element. This integer, Moseley recognized, corresponded to what he termed the atomic number, the position of the element in the periodic sequence, and his measurements provided direct experimental evidence that this atomic number represented the positive charge on the atomic nucleus, measured in units of the electron charge. The mathematical expression of this relationship, which we now call Moseley's law, stated that the frequency of the characteristic K-alpha X-ray line of an element was proportional to the square of a quantity equal to the atomic number minus a small constant, this constant representing the shielding effect of inner electrons. The law held with such precision across the entire range of elements that Moseley examined, from the lightest to the heaviest, that there could be no doubt of its fundamental validity. And in establishing this relationship, Moseley had provided the experimental foundation for a complete reordering of our understanding of elemental identity. The implications of Moseley's law were profound and far-reaching, extending well beyond the resolution of those troublesome inversions that had puzzled chemists for so long. The cobalt-nickel inversion was now explained with perfect clarity. For while cobalt possessed a slightly greater atomic weight than nickel, Moseley's measurements showed unambiguously that cobalt had an atomic number of 27 while nickel had an atomic number of 28, placing them in their proper chemical order regardless of their atomic masses. Similarly, tellurium with its atomic number of 52 properly preceded iodine with its atomic number of 53. Even though tellurium's atoms were heavier, and the argon-potassium pair showed the same pattern, with argon at 18 preceding potassium at 19 despite argon's greater atomic weight. The atomic number, not the atomic weight, was revealed as the true determinant of chemical identity and periodic position. But perhaps equally significant was what Moseley's systematic measurements revealed about the gaps in the periodic table. Those positions where no known element resided but where his linear relationship predicted an element should exist. His straight-line plot of X-ray frequencies against atomic number showed unmistakably that elements were missing at atomic numbers 43, 61, 72, and 75, for at these positions there appeared no data points, no characteristic X-ray frequencies, despite the clear prediction of his law that elements with these atomic numbers must exist. Moseley had thus provided not merely a reordering of known elements but a definitive map of the undiscovered, a guide for future researchers who would eventually fill these gaps with elements now known as technetium, promethium, hafnium, and rhenium. The discovery of these missing elements would unfold over the subsequent decades, each confirming the validity of Moseley's predictions with gratifying precision. Hafnium, element 72, would be discovered in 1923 by Dirk Coster and George de Hevesy in Copenhagen, using X-ray spectroscopic methods directly descended from Moseley's techniques. Rhenium, element 75, would follow in 1925, discovered by Walter Noddack, Ida Tack, and Otto Berg in Berlin, again with X-ray spectroscopy playing a crucial role in its identification. Technetium, element 43, proved more elusive because it possesses no stable isotopes, and was first produced artificially in 1937 by Emilio Segre and Carlo Perrier, while promethium, element 61, similarly radioactive and unstable, was not isolated until 1945. In each case, the existence of the element and its proper position in the periodic table had been foretold by the elegant straight line of Moseley's graph, drawn decades before the elements themselves were found. The importance of Moseley's work extended into the very foundations of atomic theory, for his demonstration that atomic number corresponded to nuclear charge provided crucial support for the developing quantum mechanical understanding of atomic structure. Niels Bohr's atomic model, published in the same year that Moseley began his X-ray studies, had proposed that electrons occupied discrete energy levels around the nucleus, and Moseley's measurements of inner shell X-ray transitions provided direct experimental confirmation of these energy levels and their dependence upon nuclear charge. The synthesis of Bohr's theoretical framework with Moseley's experimental results created a coherent picture of atomic structure in which the nuclear charge, the atomic number, determined both the number of electrons surrounding the nucleus and the energy levels available to those electrons, thereby explaining both the X-ray spectra that Moseley measured and the optical spectra that spectroscopists had studied for decades. The techniques that Moseley developed and refined during his brief period of intensive research would become standard methods in the identification and analysis of elements, forming the foundation of what would eventually be known as X-ray fluorescence spectroscopy. The combination of electron bombardment to produce characteristic X-rays, crystal diffraction to separate X-rays by wavelength, and photographic or other detection methods to record the results would prove applicable to an enormous range of analytical problems, from the identification of unknown minerals to the detection of trace elements in biological samples. Moseley had not merely answered a fundamental question about atomic identity, but had provided a powerful practical tool for the investigation of matter in all its forms. Yet even as we consider the magnitude of Moseley's scientific achievements, we must also reckon with the terrible brevity of the life in which they were accomplished. 4. Henry Moseley was killed at Gallipoli on the 10th of August, 1915. At the age of 27, his promising career extinguished by a Turkish bullet during the disastrous Dardanelles campaign of the First World War. He had enlisted in the Royal Engineers despite offers of safer positions that would have allowed him to continue his research. Feeling that his duty to his country demanded active service, and he served as a telecommunications officer during the amphibious assault on the Ottoman Empire. The circumstances of his death were tragically commonplace amid the carnage of that war. A young man struck down in the midst of a military operation that would ultimately fail in all its objectives. But the loss to science was anything but commonplace. Ernest Rutherford, who had supervised Moseley's work at Manchester and who understood perhaps better than anyone the magnitude of his abilities, spoke of Moseley's death as the greatest single scientific loss of the entire war, a judgment that reflected not only personal grief for a fallen colleague but also a clear-eyed assessment of what Moseley might have achieved had he been allowed to continue his researches. Other scientists of the time shared this assessment, recognizing that Moseley's combination of experimental skill, theoretical insight, and systematic determination marked him as one of the most promising physicists of his generation. A young man who at 27 had already made contributions of lasting importance and who might well have made many more in the decades that should have followed. The shock of Moseley's death, and the recognition of what had been lost, contributed to changes in how nations would subsequently treat their scientific personnel during wartime, with governments becoming more careful to shield researchers of exceptional ability from the dangers of combat. The principle that scientific talent represented a national resource too valuable to be expended carelessly in military operations gained acceptance in the years following the First World War, and by the time of the Second World War most combatant nations had established mechanisms for identifying and protecting scientists whose skills might prove more valuable in laboratories than on battlefields. This policy change came too late to save Moseley himself, but it represented a recognition, born of bitter experience, that the advancement of human knowledge depends upon the preservation of those rare individuals capable of pushing forward the boundaries of understanding. In the quiet aftermath of war, as the scientific community resumed its work and took stock of what had been lost, Moseley's contribution stood as a monument to what a brilliant mind could achieve in a few short years of concentrated effort. His papers, published in the Philosophical magazine in 1913 and 1914, remained standard references for decades. His law became a fundamental tool of atomic physics, and his predictions of undiscovered elements were vindicated one by one as the periodic table was gradually completed. The atomic number, which Moseley had established as the true ordering principle of the elements, became the foundation upon which all subsequent understanding of atomic structure would be built, and his experimental techniques evolved into analytical methods that continue to serve science and industry to this day. As we contemplate the trajectory of atomic spectroscopy from its origins in the colored flames of Bunsen's laboratory to the X-ray diffraction patterns of Moseley's photographic plates, we can see a continuous thread of inquiry, each generation of researchers building upon the discoveries of those who came before, each new technique revealing deeper layers of atomic structure. The visible spectra that Bunsen and Kirchhoff had observed represented transitions of outer electrons, relatively easily disturbed by chemical combination and thermal excitation, while the X-ray spectra that Moseley measured arose from the innermost electrons, those bound most tightly to the nucleus and most directly sensitive to the nuclear charge. Both types of spectra, visible and X-ray, found their explanation in the quantum mechanical picture of atomic structure that Bohr and others were developing during these same years, a picture in which electrons occupied discrete energy states and emitted or absorbed radiation in precise quanta as they moved between these states. The synthesis of spectroscopy and atomic theory, to which Moseley contributed so significantly, represented one of the great achievements of early 20th century physics, transforming the periodic table from an empirical arrangement of observed regularities into a logical consequence of atomic structure and quantum mechanics. Each element found its place in the periodic sequence because of the number of protons in its nucleus and the corresponding number of electrons that surrounded that nucleus in its neutral state. And the chemical properties that determined periodic groupings arose from the arrangements of these electrons in their quantum mechanical energy levels. What had been mysterious became comprehensible. What had been empirical became theoretical. And the humble spectroscope, whether observing visible light or X-rays, provided the experimental key to this transformation. The story of Henry Moseley, brief and brilliant and ultimately tragic, reminds us that scientific progress depends not only upon ideas and instruments but upon the individual human beings who conceive the experiments and interpret the results, and that these individuals, for all their intellectual gifts, remain subject to the same contingencies of fate that govern all human lives. The atomic number that bears witness to Moseley's insight will endure as long as our understanding of atoms endures, a fitting memorial to a young man who might have achieved so much more, but whose actual achievements, compressed into those few productive years before the war, would have been sufficient legacy for a much longer life. And so we come now to another thread in this tapestry of discovery, a parallel line of inquiry that was unfolding in the laboratories of Germany during those same years when Niels Bohr was working out his atomic theory in Copenhagen and Manchester. This is the story of electric fields and their influence upon the light that atoms emit, a phenomenon that would come to be known as the Stark effect, after the German physicist Johannes Stark, who first observed it clearly in the autumn of 1913. The discovery would arrive at a remarkably fortuitous moment in the history of physics, just months after Bohr had published his revolutionary papers on the hydrogen atom, and it would provide an independent confirmation of quantum ideas that seemed almost too perfectly timed to be coincidental. Yet science often unfolds in this manner, with different researchers working along separate paths that converge unexpectedly, each illuminating the work of the other in ways that neither could have anticipated at the outset. Johannes Stark was born in 1874 in the town of Kirchhoff, in Bavaria, and he had pursued his education through the German university system with a particular interest in the behavior of electrically charged particles and the light they produced. By 1913, he had established himself as a capable experimental physicist at the Rheinisch-Westfälische Technische Hochschule in Aachen, an institution we know today as RWTH Aachen, one of the leading technical universities in Germany. Stark had been working for some years on the properties of canal rays, which were streams of positive ions that could be produced in discharge tubes and made to travel at considerable speeds through evacuated glass vessels. These canal rays had first been identified in 1886 by the physicist Eugen Goldstein, who had noticed streams of luminous particles passing through channels, or canals, drilled in the cathode of a discharge tube, traveling in the opposite direction to the more familiar cathode rays. The canal rays were positive ions, atoms that had lost one or more electrons and thus carried a positive electrical charge, and they could be accelerated to high velocities by the electric fields within the discharge apparatus. Stark had already made significant contributions to the study of canal rays, including observations of the Doppler effect in the light they emitted, which allowed him to measure their velocities with considerable precision. He understood that these fast-moving ions represented a useful tool for probing the properties of atomic light emission under various conditions. In particular, Stark became interested in the question of whether an external electric field might influence the spectral lines produced by these ions, in a manner analogous to the way that Zeeman had shown magnetic fields could split spectral lines back in 1896. This was not an entirely new idea, and other researchers had attempted similar experiments before Stark, but they had encountered significant difficulties that had prevented them from obtaining clear results. Among those who had searched for an electric analogue of the Zeeman effect was the German physicist Waldemar Voigt, who had conducted experiments in the 1890s and early 1900s without success. Voigt was a respected theoretician and experimentalist who had made important contributions to the understanding of crystal optics and other areas of physics, but his attempts to observe the splitting of spectral lines in electric fields had yielded only negative results. The fundamental problem was one of field strength, for the electric fields that could be generated in the laboratory using the techniques available at the time were simply not strong enough to produce observable effects on atomic spectra. The influence of an electric field on the energy levels of an atom is considerably weaker than the influence of a magnetic field of comparable magnitude, and this meant that experimenters needed to achieve field strengths that were extraordinarily difficult to produce and maintain. Stark approached this problem with a clever experimental strategy that took advantage of the properties of canal rays themselves. He reasoned that if he could not bring a sufficiently strong electric field to stationary atoms, he might instead bring fast-moving atoms into a region where strong fields existed naturally at the atomic scale. By allowing canal rays to pass close to the surfaces of electrodes, or through narrow gaps between charged plates, the ions would experience the intense electric fields that exist in the immediate vicinity of conducting surfaces. The effective field strengths that could be achieved through this method were far greater than anything that could be produced using simple parallel plate arrangements with reasonable voltages. Stark worked to generate fields approaching 100,000 volts per centimeter, a tremendous intensity that required careful engineering of his apparatus and considerable attention to problems of electrical breakdown and insulation. The experiments required patience and precision, as the effects Stark was seeking would be subtle shifts and splittings of spectral lines that could easily be obscured by other phenomena such as Doppler broadening from the thermal motion of the ions, or instrumental effects from the spectrograph itself. Stark used photographic plates to record his spectra, building up exposures over time to capture the faint details of the line structures. He worked with hydrogen and with helium, focusing particularly on the Balmer series lines of hydrogen that had been so thoroughly studied by earlier spectroscopists and that would later prove so central to Bohr's theoretical treatment. In the autumn of 1913, Stark obtained results that clearly showed the splitting of hydrogen spectral lines in the presence of strong electric fields. The effect was unmistakable, with lines that had previously appeared single now resolved into multiple components when the atoms were subjected to the intense fields near his electrodes. The pattern of splitting was complex, more complicated than the relatively simple triplet structure of the normal Zeeman effect, but it was reproducible and systematic. Stark announced his discovery in a paper published in November 1913, just a few months after Bohr had published the final installment of his trilogy of papers on the hydrogen atom in the Philosophical magazine. The timing could hardly have been more propitious for the quantum theory, as Stark's observations provided exactly the sort of independent experimental confirmation that a new theoretical framework requires if it is to gain acceptance among the scientific community. The significance of the Stark effect for quantum theory lay in the details of the splitting patterns that Stark observed. The spectral lines did not simply broaden or shift slightly in the electric field, but rather they separated into distinct components with specific separations that could be measured and compared with theoretical predictions. For this comparison to be made, however, theoretical work was needed to calculate what the quantum theory would predict for the behavior of atomic energy levels in the presence of an electric field. This theoretical challenge was taken up almost immediately by two physicists working independently, Paul Epstein in Munich and Karl Schwarzschild in Potsdam, both of whom published analyses of the Stark effect based on the quantum conditions that Bohr and Sommerfeld had developed. Paul Epstein was a young theoretical physicist who had been born in Warsaw in 1883 and had studied under Arnold Sommerfeld in Munich. He was well versed in the mathematical techniques of classical mechanics and their application to atomic problems through the quantum conditions that selected which classical orbits were actually permitted in the atomic realm. Epstein applied the methods of action angle variables and perturbation theory to the problem of a hydrogen atom in an external electric field, treating the field as a small disturbance to the Coulomb potential of the nucleus. His calculations showed that the electric field would cause the originally degenerate energy levels of hydrogen to split into multiple sublevels, with the pattern of splitting depending on the quantum numbers characterizing each state. The predictions matched Stark's observations remarkably well, providing quantitative confirmation that the quantum theoretical approach was capturing something essential about the behavior of atoms. Karl Schwarzschild, working independently in Potsdam, arrived at essentially the same theoretical results using similar methods. Schwarzschild was already a distinguished astronomer and physicist who had made important contributions to astrophysics and to the theory of stellar atmospheres. He would later become famous for his solution of Einstein's field equations of general relativity, published in 1916 while he was serving in the German army during the First World War. His analysis of the Stark effect demonstrated that the problem could be solved exactly using the technique of separation of variables in parabolic coordinates, a mathematical approach that exploited the particular symmetry of the combined Coulomb and uniform electric field potentials. The fact that two independent theorists had reached the same conclusions by somewhat different routes strengthened confidence in the reliability of the theoretical treatment. The agreement between theory and experiment in the case of the Stark effect was not merely qualitative but quantitative, with the predicted magnitudes of the line splittings matching the measured values to within the experimental uncertainties. This was precisely the kind of evidence that could convince skeptical physicists that the quantum theory was more than a fortunate numerological coincidence. The Zeeman effect had already shown that external fields could influence atomic spectra, and the Stark effect now demonstrated that electric fields had their own characteristic influence, one that could be understood and predicted on the basis of the quantum conditions governing electron orbits. Together, these phenomena provided powerful tools for investigating the internal structure of atoms and for testing the increasingly sophisticated theoretical models that were being developed to describe them. The Nobel Committee recognized the importance of Stark's discovery by awarding him the Nobel Prize in Physics in 1919, citing his discovery of the Doppler effect in canal rays and of the splitting of spectral lines in electric fields. This recognition placed Stark among the most honored physicists of his generation and confirmed the significance of his experimental contributions to the understanding of atomic structure. He was 45 years old at the time of the award, at the height of his scientific career, and his work had played an important role in establishing the quantum theory on a firm experimental foundation. Yet the story of Johannes Stark takes a deeply troubling turn in the years that followed, a turn that stands as a cautionary reminder of the capacity for human failing even among those who have made genuine contributions to the advancement of knowledge. During the 1920s and increasingly through the 1930s, Stark became associated with nationalist and anti-Semitic movements in Germany, eventually aligning himself closely with the Nazi regime after Adolf Hitler came to power in 1933. Stark became a vocal proponent of what was termed Deutsche Physik, or German physics, an ideological movement that sought to discredit the work of Jewish physicists and to promote what its adherents claimed was a distinctively Aryan approach to natural science. The irony of this position was profound, for the quantum mechanics that Stark now attacked as Jewish physics was the very theoretical framework that had explained and validated his own experimental discoveries. The Stark effect had been understood and calculated using the methods developed by physicists whom Stark and his allies now vilified, and the broader structure of quantum theory to which his work had contributed drew upon the insights of Einstein, Born, and many others whom the Deutsche Physik movement wished to discredit. Stark used his Nobel Prize credentials and his administrative positions within German scientific institutions to attack colleagues whose work had built upon and extended his own, representing one of the more disturbing examples of how scientific achievement offers no protection against ideological corruption. Stark's attacks were directed at many of the most distinguished physicists of the age, including Werner Heisenberg, whom he accused of representing the spirit of Einstein within German physics. These attacks caused real harm to individuals and to the German scientific establishment as a whole, contributing to the exodus of talented researchers who fled the increasingly hostile environment of Nazi Germany. After the war, Stark was tried and convicted by a denazification court and sentenced to 4 years of labor, though his advanced age prevented the sentence from being fully carried out. He died in 1957, his scientific legacy permanently shadowed by his political choices. But we must return now to the physics itself, which retains its value and its place in the history of atomic spectroscopy regardless of the moral failings of one of its contributors. The Stark effect, along with the Zeeman effect, became a standard tool for atomic physicists seeking to understand the detailed structure of energy levels in atoms and molecules. The splitting of lines in electric fields provided information about the symmetry and configuration of electron orbitals, complementing the information available from magnetic studies. The techniques developed by Stark for generating strong electric fields and observing their effects on spectra were refined and extended by subsequent researchers, leading to increasingly precise measurements and deeper theoretical understanding. The theoretical treatments by Epstein and Schwarzschild also had lasting significance, for they demonstrated the power of the quantum conditions in addressing problems that went beyond the simple hydrogen atom in isolation. The ability to calculate the effects of external perturbations on atomic energy levels was essential for understanding the behavior of atoms in practical situations, where they are rarely completely isolated from their environment. The methods developed for treating the Stark effect became prototypes for more general perturbation theories that would be applied to a wide range of problems in atomic and molecular physics. The period from 1913 to 1925 saw a remarkable flowering of atomic spectroscopy, with experimentalists and theorists working in close coordination to unravel the mysteries of atomic light emission. Each new discovery, whether the fine structure of spectral lines, the effects of external fields, or the patterns of line intensities, provided both challenges and confirmation for the developing quantum theory. The Stark effect represented one important thread in this larger tapestry, demonstrating that the quantum conditions were not merely ad hoc rules invented to explain the Balmer formula, but rather reflected something deep about the nature of atomic systems and their response to external influences. And so we may let our thoughts rest here for a moment, considering how the gentle splitting of spectral lines in an electric field could carry such profound implications for our understanding of the atomic world. The light from those canal rays in Stark's laboratory in Aachen, refracted through his spectrograph and recorded on photographic plates, held within its subtle structure confirmation of ideas that were reshaping physics itself. The atoms continued their quiet dance, emitting their characteristic colors, while the physicists worked to decode the messages hidden in those patterns of light and shadow. The story would continue, as it always does, with new questions arising from each answer, new puzzles emerging from each solution, in the endless patient work of understanding the natural world. In the years immediately following Niels Bohr's remarkable proposal of quantized electron orbits, the scientific community found itself in possession of a theory that worked surprisingly well for the simplest of atoms, yet left many observations only partially explained. The hydrogen spectrum, with its elegant series of lines, had yielded beautifully to Bohr's circular orbits, and this was no small achievement. But when physicists looked more closely at these spectral lines, using instruments of greater precision, they discovered that what had appeared to be single lines were in fact clusters of very closely spaced lines, separated by the tiniest of intervals. This fine structure, as it came to be called, suggested that the atomic world harbored subtleties that Bohr's original model, elegant as it was, could not yet accommodate. It was into this landscape of partial understanding and lingering mystery that Arnold Sommerfeld stepped, bringing with him the mathematical sophistication that would extend Bohr's ideas into something considerably more complete, and in doing so, he would uncover one of the most fundamental constants in all of physics. Arnold Johannes Wilhelm Sommerfeld was a German theoretical physicist working at the University of Munich, where he had established himself as both a profound thinker and an exceptional teacher of physics. Born in 1868 in Königsberg, he had trained originally as a mathematician before turning his attention to theoretical physics, and this mathematical background would prove essential to the work that lay ahead. By 1915, when he began his serious investigations into atomic structure, Sommerfeld had already made significant contributions to various areas of physics, but it was his extensions of Bohr's atomic model that would cement his place in the history of quantum theory. He was a man of considerable patience and precision, qualities well suited to the painstaking work of reconciling theory with the ever more detailed observations emerging from spectroscopic laboratories across Europe. The essential limitation of Bohr's original model lay in its restriction to circular orbits. While circles possess a certain mathematical simplicity that made them a natural starting point, there was no compelling physical reason to believe that electrons must travel in circles rather than in ellipses, which are, after all, the more general form of closed orbital motion. Johannes Kepler had shown centuries earlier that planets travel around the Sun in elliptical paths, and the mathematics of classical mechanics had long established that ellipses arise naturally from inverse square force laws, precisely the kind of force that exists between an electron and a nucleus. Sommerfeld recognized that by allowing elliptical orbits, he could introduce additional degrees of freedom into the atomic model, and these additional degrees of freedom would require additional quantum numbers to describe them fully. In 1915 and continuing through 1916, Sommerfeld developed his generalization of Bohr's model, working carefully through the mathematical details at his offices in Munich. Where Bohr had needed only a single quantum number, which we now call the principal quantum number and denote by the letter n, Sommerfeld found that a complete description of elliptical orbits required a second quantum number as well. This additional quantum number, which Sommerfeld called the azimuthal quantum number, described the shape of the ellipse, specifically the ratio of its minor axis to its major axis. An orbit characterized by a particular principal quantum number n could have any one of several different shapes, ranging from nearly circular to highly elongated, and each distinct shape corresponded to a different value of the azimuthal quantum number. Sommerfeld originally denoted this second quantum number by the letter k, and it could take integer values from 1 up to the value of the principal quantum number n. The physical meaning of this second quantum number was connected to the angular momentum of the electron in its orbit. A circular orbit of a given size possesses the maximum possible angular momentum for that size, while an elongated elliptical orbit possesses less angular momentum even though the electron may travel to the same maximum distance from the nucleus. By quantizing not only the total energy of the orbit, as Bohr had done, but also the angular momentum, Sommerfeld created a richer mathematical structure that could accommodate a wider variety of orbital motions. An atom characterized by a principal quantum number of 2, for instance, could have the electron traveling in a circular orbit with azimuthal quantum number 2, or in an elliptical orbit with azimuthal quantum number 1. These different orbital shapes would, in most circumstances, have very slightly different energies, and it was this energy difference that Sommerfeld proposed as the explanation for the fine structure of spectral lines. But the introduction of elliptical orbits alone was not quite sufficient to explain the observed fine structure. In a purely classical treatment, or even in a simple quantum treatment that ignored relativistic effects, an elliptical orbit and a circular orbit with the same principal quantum number would have exactly the same energy. This is a consequence of the inverse square nature of the electric force and is entirely analogous to the situation in planetary mechanics, where the energy of an orbit depends only on the length of the major axis and not on the eccentricity. Something more was needed to lift this degeneracy, as physicists say, and make orbits of different shapes have different energies. It was here that Sommerfeld made his most penetrating contribution, recognizing that the effects of Einstein's special theory of relativity, though exceedingly small, were precisely what was required. In an elliptical orbit, an electron does not travel at constant speed. It moves fastest when closest to the nucleus, at the point called perihelion by analogy with planetary orbits, and slowest when farthest from the nucleus, at the aphelion. In highly elliptical orbits, the electron approaches the nucleus quite closely and accelerates to considerable velocities at which the effects predicted by special relativity begin to manifest themselves. According to relativity, the mass of an object increases as its velocity increases, and this relativistic increase in mass affects the motion of the electron in a subtle but measurable way. The orbit no longer closes perfectly upon itself but instead precesses slowly, the major axis of the ellipse rotating gradually with each revolution of the electron. This relativistic precession introduces a small correction to the energy of the orbit, a correction that depends on the shape of the orbit and therefore on the azimuthal quantum number. Sommerfeld worked through the relativistic mechanics with characteristic thoroughness, applying the formalism of analytical mechanics to the electron's motion and quantizing the resulting expressions according to rules that generalized Bohr's original prescription. The calculation was mathematically demanding, requiring careful attention to the way momentum and energy transform under relativistic conditions. But Sommerfeld possessed exactly the mathematical preparation necessary to carry it through successfully. When he completed his analysis, He found that the energy of an electron in an orbit characterized by quantum numbers n and k could be expressed as a series of terms, the leading term being exactly the expression Bohr had derived, and the next term being a small correction proportional to the fourth power of the nuclear charge and inversely proportional to various powers of the quantum numbers. The coefficient that appeared in this relativistic correction term was particularly significant. It was a dimensionless number, formed from the fundamental constants of nature, specifically the charge of the electron, the speed of light, and Planck's constant, combined in such a way that all units cancelled out, leaving a pure number. This number, which Sommerfeld denoted by the Greek letter alpha, had a value of approximately 1 divided by 137, or more precisely, approximately 0.007297. Sommerfeld recognized immediately that this fine structure constant, as he called it, was something quite remarkable, a pure number that appeared to be built into the very fabric of the universe, characterizing the strength of the electromagnetic interaction between charged particles. He described it as one of the most fundamental pure numbers in physics, and so it has remained to this day, appearing in calculations throughout quantum electrodynamics and particle physics, its value known now to extraordinary precision, yet its origin still not fully understood. The fine structure constant determines, among other things, the ratio of the speed of an electron in the first Bohr orbit to the speed of light. Because this ratio is small, roughly 1/137, relativistic effects in atoms are correspondingly small, which is why Bohr's non-relativistic model worked as well as it did. But small does not mean negligible, and spectroscopes of sufficient resolution could detect the splitting of spectral lines that arose from these relativistic corrections. Sommerfeld's extended model, with its elliptical orbits and relativistic energy corrections, predicted exactly the pattern of fine structure that experimentalists observed in the hydrogen spectrum and in the spectra of other simple atoms. This was a triumph of theoretical physics, the kind of close agreement between calculation and measurement that gives physicists confidence they are on the right track. Beyond the fine structure of energy levels, Sommerfeld also contributed importantly to understanding which transitions between energy levels were actually observed as spectral lines and which were not. Not every possible transition occurs in nature, and the rules governing which transitions are allowed and which are forbidden came to be called selection rules. Sommerfeld and others worked out these selection rules in terms of the quantum numbers characterizing the initial and final states of the atom. The azimuthal quantum number, for instance, was found to change by exactly 1 unit in allowed transitions, never by 0 or by 2 or by larger amounts. These selection rules could be understood in terms of the conservation of angular momentum during the emission or absorption of light, since a photon carries 1 unit of angular momentum, and this angular momentum must come from or go into the orbital motion of the electron. The selection rules helped explain why atomic spectra showed the particular patterns they did, with some expected lines present and others mysteriously absent. They also provided important guidance for experimentalists trying to identify and catalogue the ever-growing collection of spectral lines being observed in laboratories. As spectroscopic techniques continued to improve, revealing finer and finer details of atomic spectra, the theoretical framework developed by Sommerfeld and his contemporaries proved increasingly valuable in making sense of what was being seen. In 1919, Sommerfeld gathered his work on atomic structure into a comprehensive textbook titled Atombau und Spektrallinien, which translates from the German as Atomic Structure and Spectral Lines. This book became the definitive reference work on atomic spectroscopy for an entire generation of physicists, running through multiple editions as the field continued to develop. Written with clarity and thoroughness, it presented both the theoretical foundations and the experimental evidence in a style accessible to students while maintaining full mathematical rigor. Physicists sometimes referred to it simply as the Bible of atomic physics, and it played an essential role in educating the young researchers who would go on to develop quantum mechanics into its mature form during the 1920s and beyond. The influence of Sommerfeld extended well beyond his published work, significant as that was. As a teacher and mentor at the University of Munich, he guided an extraordinary number of students who went on to make fundamental contributions to physics, many of them receiving the Nobel Prize for their work. Werner Heisenberg, who would formulate the matrix mechanics version of quantum theory and discover the uncertainty principle, studied under Sommerfeld. Wolfgang Pauli, who would propose the exclusion principle that bears his name and make crucial contributions to quantum field theory, was another of his students. Peter Debye, who received the Nobel Prize in Chemistry for his work on molecular structure, and Hans Bethe, who explained the nuclear reactions that power the stars, both passed through Sommerfeld's research group in Munich. It is sometimes observed that while Sommerfeld himself never received the Nobel Prize, despite being nominated more than 80 times, he trained more Nobel laureates than any other physicist in history, a testament to his abilities as a teacher and his judgment in recognizing talented young researchers. Despite its many successes, Sommerfeld's extended model of the atom could not explain everything that spectroscopists observed. One particularly troublesome phenomenon was the so-called anomalous Zeeman effect. The normal Zeeman effect, discovered by Peter Zeeman in 1896, involved the splitting of spectral lines when an atom was placed in a magnetic field. This splitting could be understood in terms of the interaction between the magnetic field and the orbital motion of the electron, which acts as a tiny current loop and therefore possesses a magnetic moment. The theory predicted that each spectral line should split into 3 components in the presence of a magnetic field, and for some lines, this is exactly what was observed. But for many other spectral lines, the observed splitting was more complicated, involving more than 3 components with spacing that did not fit the simple theoretical predictions. This anomalous Zeeman effect, as it was called to distinguish it from the normal behavior, resisted explanation within Sommerfeld's framework, even with all its refinements and extensions. Various attempts were made to account for it, including the introduction of half-integer quantum numbers, but none of these modifications was fully satisfactory. The anomalous Zeeman effect would remain a puzzle until the mid-1920s, when the discovery of electron spin by George Uhlenbeck and Samuel Goudsmit provided the missing piece of the puzzle, revealing that the electron possesses an intrinsic angular momentum quite apart from any orbital motion. Looking back at Sommerfeld's contributions, we can see them as representing a crucial intermediate stage in the development of quantum theory. His model, sometimes called the Bohr-Sommerfeld model, extended the original ideas of Bohr in ways that brought theory into closer agreement with experiment and introduced mathematical techniques that would prove valuable in later developments. The quantization conditions he employed, which specified how the action variables of classical mechanics should be restricted to integer multiples of Planck's constant, provided a bridge between classical and quantum descriptions of motion. These methods, while ultimately superseded by the more complete formalism of wave mechanics and matrix mechanics, served admirably in the years when a fully satisfactory quantum theory had not yet been developed. The fine structure constant that emerged from Sommerfeld's work has taken on a life of its own in the century since its introduction. It appears throughout modern physics, characterizing the strength of electromagnetic interactions, appearing in calculations of atomic energy levels, governing the scattering of light by electrons, and playing a role in the unification of electromagnetic and weak nuclear forces. Its value, measured to ever greater precision by successive generations of physicists, provides one of the most stringent tests of quantum electrodynamics, the quantum field theory of electromagnetic interactions. That such a fundamental constant should emerge from the study of fine structure in atomic spectra is a reminder of how the careful examination of natural phenomena, even seemingly small effects like the splitting of spectral lines, can lead to insights of the deepest importance. In his quiet way, in his offices at the University of Munich, surrounded by books and papers and the promising young students who would one day reshape physics, Arnold Sommerfeld refined our understanding of the atomic world, adding ellipses to circles, bringing relativity into quantum theory, and uncovering a number that seems to encode something essential about how our universe is constructed. His textbook taught a generation, his students changed the world, and his fine structure constant remains, to this day, a pure number of profound significance, still not fully explained, still holding its secrets, approximately 1 divided by 137. And so we come now to one of the quieter revolutions within the revolution, a principle that Niels Bohr developed over many years, beginning shortly after his initial work on the hydrogen atom and continuing through the early 1920s, a guiding idea that served as a kind of bridge between the familiar world of classical physics and the strange new territory of quantum phenomena. This was the correspondence principle, and while it may sound rather abstract at first, it proved to be one of the most useful tools in the early development of quantum theory, allowing physicists to make predictions and discoveries that would otherwise have remained quite out of reach. So let us settle in and trace the gentle arc of this idea, from its first stirrings in Bohr's papers of 1913 through to its mature form in the years that followed, and we shall see how it helped to illuminate the behavior of atoms in ways that Bohr's original model, elegant as it was, could not have managed on its own. When Bohr first proposed his model of the hydrogen atom in 1913, he had achieved something remarkable in explaining the wavelengths of light that hydrogen emits, the precise colors that had puzzled scientists for decades. His model, with its stationary states and quantum jumps, gave the right numbers for where the spectral lines should appear, and this was a tremendous success. But there was a difficulty, a gap in the theory that became apparent quite early on. The model could tell you which wavelengths were possible, but it could not tell you how bright each spectral line should be. When you look at the spectrum of hydrogen through a spectroscope, you see that some lines are quite prominent while others are faint, barely visible against the background. The Bohr model, in its original form, offered no explanation for these differences in intensity. It was rather like having a map that showed you the locations of all the towns but gave you no indication of how large each town might be. This was not a small matter, because the intensities of spectral lines carry important information about the atom, about how readily it undergoes one type of transition compared to another. Classical physics, the older electromagnetic theory developed by Maxwell and others, had clear methods for calculating how brightly a vibrating charge should radiate, based on the amplitude and frequency of its oscillation. But in Bohr's quantum world, electrons did not radiate while orbiting, they only emitted light when jumping between states, and there was no obvious way to apply the classical formulas. The question of intensities remained open, a puzzle waiting for some new insight. It was in grappling with this problem that Bohr began to develop what would become the correspondence principle. The essential idea, which emerged gradually through his thinking in the years following 1913, was that quantum mechanics and classical physics should not be entirely separate domains. Rather, there should be a smooth transition between them, a region where the predictions of quantum theory blend into the predictions of classical physics. Specifically, Bohr proposed that when you consider atoms in states with very large quantum numbers, states where the electron is far from the nucleus and moving in a very large orbit, the behavior predicted by quantum mechanics should approach the behavior predicted by classical electromagnetic theory. The two descriptions should correspond, should give the same answers, in this limiting case of large quantum numbers. This might seem like a rather technical point, but its implications were profound. If quantum predictions must match classical predictions for large quantum numbers, then you could use classical physics as a guide to discover features of quantum theory that might otherwise be hidden. The classical formulas, which physicists understood quite well, could serve as a kind of scaffolding, helping to construct the quantum theory in regions where direct experimental guidance was scarce. Bohr saw that this requirement of correspondence was not merely a convenience but something deeper, a constraint that any correct quantum theory must satisfy. In the years between 1913 and 1918, Bohr refined these ideas, working through calculations and considering how the principle might be applied in practice. The mature statement of his approach came in a long and detailed paper published in 1918, titled On the Quantum Theory of Line Spectra. This paper, which appeared in 3 parts in the Proceedings of the Royal Danish Academy, represented Bohr's most systematic treatment of spectral theory up to that time. It was dense with mathematics and careful reasoning, the sort of paper that one might read slowly over many evenings, pausing frequently to consider the arguments. In this work, Bohr laid out methods for using the correspondence principle to extract information about atomic behavior that his original model could not provide. The key insight was this. In classical physics, when a charged particle moves in an orbit, it radiates electromagnetic waves at frequencies related to its orbital motion. For a simple circular orbit, the particle radiates at the fundamental frequency of its orbit, but for more complicated motions, such as elliptical orbits or orbits that precess, the motion can be broken down into harmonic components, a fundamental frequency plus overtones, rather like the harmonics of a vibrating string. Each harmonic component contributes to the radiation, and the intensity of each component depends on its amplitude in the overall motion. This technique of breaking down complex motions into harmonic components was well established in classical physics, part of the standard mathematical toolkit known as Fourier analysis. Bohr reasoned that in the quantum theory, when an electron makes a transition from one stationary state to another, the frequency of the emitted light corresponds, for large quantum numbers, to one of these classical harmonic frequencies. More importantly, the intensity of the emitted light, the brightness of the spectral line, should correspond to the amplitude of that harmonic component in the classical motion. So by analyzing the classical orbital motion and determining the amplitudes of its various harmonics, one could make predictions about the relative intensities of the corresponding quantum transitions. This was a remarkable bridge between two worlds. On one side stood the classical physics of continuous motion and continuous radiation, described by differential equations and Fourier series. On the other side stood the quantum physics of discrete energy levels and sudden jumps, where electrons leapt from one state to another without passing through intermediate positions. The correspondence principle connected these two descriptions, asserting that they must agree in the appropriate limit and using that agreement to transfer knowledge from the classical domain into the quantum one. In his 1918 paper, Bohr applied these methods systematically, working through the mathematics of elliptical orbits and demonstrating how the correspondence principle could be used to predict not just which transitions would occur but how strong they would be relative to one another. The calculations were intricate, involving the precise shapes of electron orbits and the way those shapes changed with energy, but the underlying logic was clear. Classical physics, despite its limitations, still held useful truths that quantum physics must honor. Among those who took up these methods and developed them further, one of the most important was Hendrik Kramers, a young Dutch physicist who came to Copenhagen to work with Bohr. Kramers arrived in 1916, while the war was still raging in Europe, and he became Bohr's closest collaborator during this fertile period. He had a gift for mathematics and a patient temperament well suited to the detailed calculations that the correspondence principle required. In the years that followed, Kramers made significant contributions to the quantum theory of spectra, using the correspondence methods to calculate transition probabilities for various atomic systems. Transition probabilities are the quantities that determine how likely an atom is to make a particular quantum jump, and they are directly related to the intensities of spectral lines. If one transition has a high probability and another has a low probability, then the spectral line associated with the first will be brighter than the line associated with the second. Kramers developed techniques for computing these probabilities using the correspondence principle, and his work helped to establish Copenhagen as the leading center for quantum research in those years. He later summarized some of this work in papers and in a book that became a standard reference for physicists working in the field. The calculations were not always straightforward. The correspondence principle provided guidance and constraints, but it did not give a complete algorithmic procedure that could be mechanically applied. There was an element of physical intuition involved, a sense of which classical features would carry over into the quantum domain and which would not. Sometimes the principle pointed clearly in one direction, and sometimes it required considerable thought to see how it should be applied. But despite these ambiguities, or perhaps because of them, the correspondence principle proved enormously productive. It allowed physicists to make progress on problems that would otherwise have been intractable, to calculate quantities that the bare Bohr model could not provide. One particularly important application was in the development of selection rules, the rules that specify which quantum transitions are allowed and which are forbidden. When you look at the spectrum of an atom, you see certain lines but not others, and this suggests that not all transitions between energy levels actually occur. Some transitions seem to be prohibited by nature, or at least suppressed so strongly that they produce no observable light. The selection rules codify these prohibitions, stating, for example, that certain changes in quantum numbers are allowed while others are not. Using the correspondence principle, physicists could derive these selection rules by examining the classical motion and asking which harmonic components were present. If a particular harmonic was absent from the classical motion, having zero amplitude, then the corresponding quantum transition would be forbidden, or at least highly suppressed. This provided a systematic way to determine which lines should appear in a spectrum and which should be missing, predictions that could be checked against observation. The agreement between the predicted selection rules and the observed spectra was a significant confirmation of the correspondence approach. It is worth pausing here to consider the philosophical status of the correspondence principle, for it occupied an unusual position in the development of quantum theory. On one hand, it was a tremendously useful tool, a practical guide that led to correct predictions and fruitful discoveries. On the other hand, its logical foundations were somewhat uncertain. Bohr was not claiming that quantum mechanics was merely classical physics in disguise, or that the quantum jumps were somehow really continuous processes. The two descriptions remained fundamentally different, and the correspondence was a limiting relationship, not an identity. The principle asserted that quantum mechanics must reduce to classical physics in the appropriate limit, but it did not explain why this should be so or provide a rigorous derivation from first principles. Some physicists were troubled by this lack of rigorous justification. Paul Ehrenfest, the Austrian-Dutch physicist who held the chair at Leiden, was among those who expressed reservations about the correspondence principle. Ehrenfest was a careful thinker with high standards of logical clarity, and he was uncomfortable with arguments that seemed to rely on intuition and analogy rather than strict deduction. He worried that the correspondence principle, despite its successes, was not a solid foundation for physics, that it was a heuristic rather than a theorem. In correspondence with Bohr and in discussions at conferences, Ehrenfest raised these concerns, pushing for greater clarity about what exactly the principle meant and how it could be justified. Bohr, for his part, acknowledged that the correspondence principle was not a finished theory but rather a guiding idea, a principle that pointed toward the correct theory without fully specifying it. He saw it as a constraint that any complete quantum mechanics would need to satisfy, a test that proposed theories would need to pass. In this sense, the principle was programmatic, indicating what kind of theory was needed rather than providing the theory itself. This attitude frustrated some physicists who wanted more definite answers, but it was characteristic of Bohr's approach to physics, which emphasized provisional understanding and gradual refinement over premature systematization. The remarkable thing is that despite the lack of rigorous justification, the correspondence principle worked. It guided physicists to correct results, helped them discover selection rules and calculate intensities, and shaped the development of quantum theory through the early 1920s. When Werner Heisenberg created his matrix mechanics in 1925, and when Erwin Schrödinger developed wave mechanics shortly thereafter, both approaches satisfied the correspondence principle, reducing to classical physics in the appropriate limits. The principle that Bohr had developed through physical intuition and careful reasoning turned out to be a genuine feature of nature, built into the mathematical structure of quantum mechanics. This success was not accidental. The correspondence principle captured something true about the relationship between the microscopic and macroscopic worlds, about the way that quantum phenomena blend into classical phenomena when quantum numbers become large. It reflected the underlying unity of physics, the fact that the laws governing atoms must somehow connect to the laws governing planets and pendulums. By insisting on this connection, Bohr was able to extract useful information from classical physics and apply it in the quantum domain, bridging a gap that might otherwise have seemed unbridgeable. At the Institute for Theoretical Physics in Copenhagen, which Bohr founded in 1921, the correspondence principle remained central to the research program throughout the early 20s. Young physicists came from across Europe and beyond to work with Bohr and Kramers, absorbing the Copenhagen approach and contributing their own insights. The atmosphere was collaborative and intense, with long discussions in Bohr's office and walks through the city streets, conversations that ranged over the foundations of physics and the meaning of the quantum theory. The correspondence principle was not just a technical tool in these discussions but a philosophical touchstone, a reminder that the new physics must connect to the old. As the 1920s progressed, the limitations of the old quantum theory, including Bohr's atomic model and the correspondence methods, became increasingly apparent. There were spectra that the theory could not fully explain, phenomena that resisted the available techniques. The theory was a patchwork, combining classical and quantum elements in ways that were productive but not entirely coherent. Something more was needed, a new theoretical framework that would put quantum mechanics on a firmer foundation. That framework would come in the middle of the decade, with the work of Heisenberg, Schrödinger, Born, and others. But when it came, it did not abandon the correspondence principle. Rather, the new quantum mechanics incorporated the principle naturally, satisfying the requirement that quantum predictions match classical predictions for large quantum numbers. Looking back, we can see the correspondence principle as a kind of heuristic ladder, a tool that Bohr and his colleagues used to climb toward the complete theory of quantum mechanics. Once the complete theory was in hand, the ladder could be set aside, for the new framework provided its own justification for the correspondence between quantum and classical physics. But during the years when the complete theory was not yet available, the ladder was indispensable. It allowed physicists to make progress, to discover new results, and to build confidence that a coherent quantum mechanics was possible. In the history of physics, there are many examples of provisional principles and heuristic methods that guided discovery before being superseded by more complete theories. The correspondence principle stands as one of the most successful of these guiding ideas, a bridge between two worlds that remained sturdy and reliable until the complete bridge could be built. Its story is a gentle reminder that scientific progress does not always proceed by strict deduction and rigorous proof. Sometimes, a good intuition and a willingness to follow where the physics leads, even without complete justification, can carry you a very long way indeed. And so the work continued in Copenhagen and elsewhere, as physicists used the correspondence principle to explore the quantum world, to calculate the intensities of spectral lines, to derive selection rules, and to inch ever closer to a complete theory of atomic structure. The skepticism of careful thinkers like Ehrenfest was not misplaced, for rigor matters in science, but neither was the pragmatic confidence of Bohr and his school, for sometimes you must follow a path before you can fully map it. In the quiet hours of the early 1920s, as young researchers sat with pencil and paper working through the harmonics of classical orbits and translating them into quantum predictions, the correspondence principle was their constant companion, a gentle guide through unfamiliar territory. And if the foundation was not as solid as some would have liked, the structure it supported proved sound enough to stand until stronger foundations could be laid. This is, in its own way, a reassuring aspect of the history, the knowledge that useful work can proceed even amid uncertainty, that progress does not require omniscience, and that the careful, patient application of good ideas can yield understanding even when the full picture remains out of view. When observers in the late 19th century turned their spectroscopes toward helium, that lightest of noble gases first glimpsed in the chromosphere of the Sun before it was ever isolated on Earth, they encountered something rather peculiar, something that would resist satisfactory explanation for more than 3 decades. The spectrum of helium, unlike the elegant simplicity of hydrogen with its orderly series of lines, presented itself as though it were the combined output of two entirely different substances, two distinct sets of spectral lines that seemed to follow their own separate rules and refused, despite considerable effort, to intermingle or transition one into the other. This was the puzzle of ortho-helium and perhelium, names that suggested two forms of the same element. And for many years the question of why helium should behave as though it possessed this dual nature remained one of the quieter mysteries of atomic physics, a loose thread in the otherwise tidy fabric of spectroscopic knowledge. The story begins, as so many spectroscopic stories do, with patient observers seated at their instruments in the closing years of the 19th century, cataloguing line after line, measuring wavelengths with increasing precision, and gradually noticing patterns that did not quite conform to expectation. Helium had been discovered spectroscopically in 1868, when astronomers observed an unfamiliar yellow line in the solar spectrum during an eclipse, a line that matched no known terrestrial element. It would be nearly 3 decades before William Ramsay isolated helium gas on Earth in 1895, and once the element became available for laboratory study, spectroscopists set about their methodical work of mapping its emission lines. What they found was somewhat bewildering. The helium spectrum contained numerous lines, as expected, but these lines fell into two apparently independent series, two families of wavelengths that never seemed to share transitions between them. One set of lines was designated perhelium, the term suggesting a parallel or companion form of helium, and these lines were characterized as singlet lines, appearing singly without close companions. The other set was called ortho-helium, from the Greek for straight or correct helium, though the name carried no implication that one form was more genuine than the other, and these lines appeared as triplets, clusters of 3 closely spaced wavelengths. The peculiarity was not merely that 2 series existed, but that atoms emitting lines from one series never seemed to jump to states belonging to the other series. It was as though helium atoms came in 2 varieties, each stubbornly maintaining its own spectral identity, and while an atom might readily transition between various states within the ortho-helium system, or between states within the perhelium system, the barrier between the two seemed impermeable. The most natural hypothesis, given the understanding of the time, was that these 2 spectral systems represented 2 isotopes of helium, 2 forms of the element with different atomic masses but identical chemical properties. This interpretation had a certain elegance to it, suggesting that the spectroscope was revealing a subtlety of elemental composition that chemistry alone could not detect. If helium consisted of a mixture of 2 isotopes, each would produce its own characteristic spectrum, and the apparently separate line series would be explained. This isotope hypothesis persisted for some years, and one can imagine the quiet satisfaction it might have provided, a tidy resolution to an otherwise puzzling observation. But as measurements grew more precise and theoretical understanding deepened, difficulties emerged, and the isotope explanation began to seem less convincing. At the University of Tübingen in Germany, Friedrich Parchen devoted himself to the careful measurement of spectral lines with an exactitude that bordered on the obsessive, in the most commendable sense of that word. Parchen, who had already made his name through the discovery of the infrared series of hydrogen that bears his name, brought to helium spectroscopy a patience and precision that few could match. Working in the years around the turn of the century and into the 1910s, Parchen accumulated extensive data on helium lines, measuring their wavelengths, their relative intensities, and the fine details of their structure. His measurements would prove invaluable to theorists attempting to understand what helium was revealing about atomic structure, even when those theorists found themselves thoroughly confounded by the results. When Niels Bohr introduced his atomic model in 1913, with its quantized electron orbits and its stunning success in explaining the hydrogen spectrum, there was natural hope that helium would yield to similar analysis. Hydrogen, with its single electron orbiting a single proton, was the simplest atom imaginable, and Bohr's theory, however radical its assumptions about quantized angular momentum might seem, produced spectral predictions that matched observation with remarkable accuracy. Helium, possessing just one additional electron, seemed a modest step up in complexity, surely within reach of the new quantum theory. But helium proved far more resistant than anyone anticipated, and Bohr's attempts to extend his model to this two-electron system met with frustration at every turn. The fundamental difficulty was the interaction between the two electrons. In hydrogen, the single electron experiences only the attraction of the nucleus, a problem that, while requiring novel quantum assumptions, could still be solved with mathematical clarity. In helium, each electron feels not only the pull of the nucleus but also the repulsion of the other electron, a three-body problem that refuses analytical solution even in classical mechanics. Bohr and others attempted various approximations, imagining the two electrons orbiting in symmetric configurations, perhaps on opposite sides of the nucleus, or in concentric orbits, but none of these models produced spectral predictions that matched Paschen's careful measurements. The ortho-helium and perhelium systems remained unexplained, their separation mysterious, and the quantitative details of the spectrum stubbornly refused to emerge from any straightforward extension of the hydrogen theory. This failure was not a minor embarrassment to be swept aside, but rather a persistent reminder that the Bohr model, for all its successes, remained incomplete. Throughout the years following 1913, as Arnold Sommerfeld extended the theory with elliptical orbits and relativistic corrections, producing ever more sophisticated versions of what became known as the Bohr-Sommerfeld theory, helium remained beyond reach. The spectrum that should have been almost as simple as hydrogen's revealed depths of complexity that the old quantum theory could not plumb, and those two mysterious spectral systems, ortho-helium and perhelium, stood as silent testimony to whatever physics was still missing from the picture. Among those attempting to bridge the gap was Alfred Land, a German physicist who worked at Tübingen and Frankfurt during the early 1920s, grappling with the anomalies of atomic spectra that the Bohr-Sommerfeld theory could not explain. Land developed what he called the core model, an attempt to account for the behavior of atoms with multiple electrons by imagining that the outer electron moved in the field not simply of the nucleus but of the nucleus combined with the inner electrons, the whole constituting a kind of core with its own effective properties. This approach achieved some empirical success, particularly in explaining certain spectral patterns and the anomalous Zeeman effect, the strange splitting of spectral lines in magnetic fields that refused to follow the simple rules predicted by classical theory. Land introduced quantum numbers to characterize this core and its interaction with the outer electron, and while his model was more prescription than explanation, more a cataloguing of observed regularities than a derivation from first principles, it served as a stepping stone toward deeper understanding. The core model, like many interim theoretical structures, contained within it hints of the truth even as it fell short of capturing it. Land found himself introducing half-integer quantum numbers, quantities like 1/2 that had no place in the original Bohr-Sommerfeld scheme but seemed necessary to match observation. These half-integers were deeply puzzling, for what could it mean for angular momentum to be quantized in half units when the theory demanded whole numbers? The discomfort with such ad hoc additions was widespread, and theorists recognized that they were patching rather than solving, applying fixes to a framework that was showing its limitations. The resolution of the ortho-helium-par-helium mystery came in 1925, as part of the revolutionary year that transformed atomic physics entirely. Two young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, working under Paul Ehrenfest at Leiden, proposed that the electron possessed an intrinsic angular momentum entirely separate from any motion through space, a built-in spin as though the electron were a tiny rotating sphere. This electron spin, they suggested, could take one of two values, often described as spin-up or spin-down, and it carried with it an associated magnetic moment. The idea seemed peculiar, even to its originators, and when they first considered the implications, including that the surface of a spinning electron of classical dimensions would have to move faster than light, they nearly abandoned the proposal. But Ehrenfest encouraged them to publish, noting that they were young enough to afford a mistake, and the concept of electron spin quickly proved its worth. At almost exactly the same time, Wolfgang Pauli in Hamburg articulated what became known as the exclusion principle, a rule stating that no two electrons in an atom could occupy exactly the same quantum state. Each electron must be distinguished by at least one quantum number, and with the introduction of spin, electrons now possessed an additional quantum number that could take two values. The exclusion principle, combined with electron spin, suddenly made sense of vast swathes of spectroscopic data, from the structure of the periodic table to the complex patterns of atomic spectra. For helium, these two developments together provided the long-sought explanation. The two electrons in a helium atom, each possessing spin, could combine their spins in two distinct ways. They might align their spins parallel to each other, both spinning in the same sense, or they might align them antiparallel, spinning in opposite senses. These two configurations proved to have profoundly different consequences for the allowed quantum states and the resulting spectra. When the spins were antiparallel, they cancelled out, producing a total spin of zero, and the resulting states were called singlet states, corresponding to perhelium with its single spectral lines. When the spins were parallel, they combined to give a total spin of 1, and the resulting states were called triplet states, corresponding to ortho-helium with its clusters of 3 closely spaced lines. The reason these two systems remained distinct, the reason atoms did not readily transition between ortho-helium and perhelium states, lay in the selection rules governing such transitions. For an atom to emit or absorb light and change its state, certain conditions must be satisfied involving the quantum numbers before and after the transition. Transitions that change the total spin were strongly disfavored, occurring rarely if at all under ordinary conditions, and so an atom in a triplet ortho-helium state would cascade down through other triplet states rather than jump to a singlet perhelium state. The two spectral systems were not two isotopes, not two substances, but two spin configurations of the same helium atoms, distinguished by the relative orientations of their two electrons. The singlet-triplet distinction that emerged from spin and the exclusion principle proved to be far more than a peculiarity of helium. It represented a general feature of all two-electron systems and indeed of quantum mechanics itself, reflecting the deep connection between spin and the symmetry properties of quantum states. The mathematical formalism revealed that the wave function describing two electrons must change sign when the electrons are exchanged, a property called antisymmetry, and this requirement linked the spatial part of the wave function to the spin part in a precise way. Singlet states, with their antisymmetric spin configuration, required symmetric spatial wave functions, while triplet states, with their symmetric spin configuration, required antisymmetric spatial wave functions. These different spatial distributions affected the energy of the states and produced the characteristic differences in the ortho-helium and perhelium spectra. Friedrich Paschen's years of careful measurement at Tübingen now found their theoretical home. The line positions he had catalogued with such precision could be understood, at least in principle, as consequences of the quantum mechanical two-electron problem with all its attendant complications of electron correlation and exchange. The full calculation remained challenging, requiring approximation methods and careful treatment of the electron-electron interaction, but the conceptual framework was now secure. Helium was not anomalous or pathological but exemplary, a case study in the physics of multi-electron atoms that revealed principles applicable throughout the periodic table. The history of the ortho-helium-perhelium mystery thus traces an arc familiar in the development of quantum theory. An empirical puzzle, noticed by careful observers in the 1890s, resists explanation for 3 decades, outlasting the Bohr model and the Bohr-Sommerfeld refinements that built upon it. Interim hypotheses, like the isotope interpretation, are proposed and eventually discarded. Theorists like Land construct partial models that capture some patterns while acknowledging their incompleteness. And then, in a concentrated burst of insight, new principles emerge that resolve not only the original puzzle but connect it to a vast web of related phenomena, revealing the deeper structure that underlies atomic behavior. The helium spectrum, precisely because it refused to yield to the old quantum theory, served as one of the crucial proving grounds where the inadequacies of that theory became unmistakable. Its resistance was not a failure of spectroscopy or measurement but a gift to physics, a clear signal that something fundamental was missing. When spin and the exclusion principle arrived, helium was waiting to confirm their power. Its ortho and para forms finally united in a single coherent picture. The two spectral systems that had puzzled observers for so long were revealed as two manifestations of one element, distinguished only by the subtle orientation of invisible spins, a distinction that makes all the difference in the quantum world. And so the mystery that began with patient work at spectroscopes in German university laboratories, with wavelength measurements recorded in notebooks and spectral atlases compiled over decades, found its resolution in the reimagining of the electron itself, no longer a featureless point charge but an entity with intrinsic spin, obeying exclusion principles that organize the structure of all matter. The story of ortho-helium and perhelium, once a puzzle to keep spectroscopists puzzling, became a chapter in the larger story of quantum mechanics, one thread among many in the fabric woven through those transformative years of the 1920s. But that larger story belongs to other sections, and for now it is enough to rest with the helium atom, its 2 electrons spinning in their quiet configurations, its spectral lines catalogued and explained, its long-held secrets gently released into understanding. In the quiet decades that bridged the 19th and 20th centuries, the study of light found its homes in scattered institutions across Europe and America, each developing its own particular character, its own rhythms of work, its own contributions to the growing understanding of how matter and radiation intertwine. These laboratories and observatories became, in their own unhurried way, the places where spectroscopy matured from a promising technique into a foundational science, and the cultures that grew within their walls shaped not only the discoveries that emerged but also the very manner in which those discoveries were made and shared. To understand how our knowledge of atomic spectra developed, one must spend some time, as we shall now, wandering through these institutions in the mind, noting their particular atmospheres and the quiet dedication of those who worked within them. In Berlin, the Physikalisch-Technische Reichsanstalt stood as a monument to the German conviction that precision itself was a worthy pursuit, that the careful establishment of standards and the meticulous measurement of physical quantities formed the necessary foundation upon which all other scientific work must rest. Founded in 1887 through the efforts of Hermann von Helmholtz and the industrialist Werner von Siemens, the Reichsanstalt was intended to serve both pure science and the practical needs of German industry, and in its gleaming laboratories equipped with the finest instruments available, researchers pursued measurements of unprecedented accuracy. Friedrich Parchen, who came to lead the spectroscopic work at the Reichsanstalt, embodied this culture of precision in his patient investigations of spectral series, particularly in the infrared region where new lines awaited discovery by those willing to develop the specialized techniques required. The infrared presented particular challenges, as the human eye could offer no assistance and the detection methods available were considerably less sensitive than those used for visible light. Yet Parchen and his colleagues developed bolometric and thermoelectric methods that allowed them to map spectral lines far beyond the red end of the visible spectrum. The series of hydrogen lines that Parchen discovered in 1908, lying in the infrared and corresponding to transitions ending at the third energy level in the terminology that would later emerge, bore his name ever after as testimony to this careful work. At the Reichsanstalt, the maintenance of wavelength standards became an institutional responsibility of considerable importance, for spectroscopists everywhere required reliable reference points against which to measure the wavelengths they observed, and the Berlin institution provided these standards with a precision that commanded international respect. The Cavendish Laboratory at Cambridge presented a rather different atmosphere, one shaped by the particular character of British physics and by the remarkable succession of leaders who guided its work. When Joseph John Thomson assumed the Cavendish professorship in 1884, he brought to the position a theoretical bent combined with considerable experimental skill, and under his direction the laboratory became a center for the investigation of electrical discharges in gases, a line of research that would eventually lead to the discovery of the electron in 1897. The spectroscopic work at the Cavendish during Thomson's tenure focused considerably on the light emitted by discharge tubes, those slender glass vessels containing rarefied gases through which electrical currents could be passed to produce glowing columns of colored light. The spectra of these discharges revealed much about the processes occurring within them, and Thomson's students and colleagues measured and catalogued these emissions with care. When Ernest Rutherford arrived at the Cavendish in 1919, having already conducted his famous scattering experiments at Manchester that revealed the atomic nucleus, the laboratory's focus shifted increasingly toward radioactivity and nuclear physics. Yet spectroscopic methods remained essential tools for investigating atomic structure. The Cavendish culture emphasized a certain practical ingenuity, a willingness to construct apparatus from whatever materials came to hand, and this resourcefulness proved valuable in a field where new phenomena often demanded new instruments for their proper study. The afternoon tea that Thomson instituted became a legendary feature of Cavendish life, providing daily opportunities for researchers to discuss their work in an informal setting, and many ideas were born or refined during these quiet gatherings over cups of tea and biscuits. At Uppsala University in Sweden, spectroscopy had found an early and devoted home through the work of Anders Jonas Angstrom, whose measurements of solar spectral lines in the 1860s established standards of precision that inspired emulation throughout the scientific world. The unit of length that bears his name, equal to 1/10,000,000th of a meter and convenient for expressing the wavelengths of visible light, remains in use among spectroscopists to this day, a quiet tribute to his foundational contributions. Uppsala's tradition of careful spectroscopic measurement continued through the later decades of the 19th century, creating an environment in which Johannes Robert Rydberg could pursue his theoretical investigations of spectral regularities. Rydberg, working largely alone and with limited experimental resources, examined the accumulated measurements of his predecessors with a mathematician's eye for pattern and order, seeking the underlying formulae that might connect the seemingly disparate wavelengths observed in the spectra of different elements. His discovery in 1890 of a general formula for spectral series, incorporating a constant that likewise came to bear his name, represented a triumph of theoretical analysis applied to experimental data, and the Rydberg constant became one of the fundamental quantities characterizing the atomic world. The Swedish tradition combined Scandinavian thoroughness with a certain independence from the larger continental centers, and this combination allowed researchers like Rydberg to pursue unfashionable lines of investigation that might have found less support elsewhere. The long northern winters, with their extended darkness, perhaps encouraged the contemplative work of spectral analysis, though one should not place too much weight on such romantic speculation. Across the Atlantic, the Harvard College Observatory presented yet another model for spectroscopic research, one that combined astronomical observation with an innovative approach to the organization of scientific labor. Under the direction of Edward Charles Pickering, who assumed the directorship in 1877 and held the position for over 4 decades until his death in 1919, the observatory embarked upon an ambitious program of classifying the spectra of stars, seeking to catalogue and understand the bewildering variety of spectral appearances that different stars presented. This enormous task, involving the examination and classification of hundreds of thousands of stellar spectra recorded on photographic plates, required a workforce far larger than the handful of astronomers traditionally employed at such institutions, and Pickering's solution was both pragmatic and, for its time, somewhat unconventional. He employed a staff of women, initially paid at modest rates comparable to those of domestic servants, to carry out the painstaking work of examining plates, measuring spectral features, and recording data. These women, sometimes referred to as computers in the terminology of the era that applied this term to human calculators rather than electronic machines, proved remarkably capable, and several among them made contributions that extended far beyond the routine tasks originally envisioned for them. Williamina Patten Stevens Fleming, who had emigrated from Scotland and initially worked as a maid in Pickering's household before joining the observatory staff, developed a classification scheme for stellar spectra based on the strength of their hydrogen lines, and this system, later refined and extended by her colleagues, formed the basis of the stellar classifications still used today. Fleming's work required not merely diligence but genuine scientific insight, for she recognized patterns and anomalies that led to significant discoveries, including her identification of white dwarf stars and her cataloguing of stellar novae. Annie Jump Cannon, who joined the observatory in 1896, further refined the classification system into the sequence of spectral types designated by the letters O, B, A, F, G, K, and M, a progression that later came to be understood as reflecting differences in stellar surface temperature. Cecilia Helena Payne, arriving at Harvard somewhat later in the 1920s, would use this accumulated spectroscopic data to demonstrate that stars are composed primarily of hydrogen and helium, a conclusion initially met with skepticism but eventually recognized as fundamentally correct. The Harvard Observatory thus demonstrated how spectroscopic research could be organized on an almost industrial scale while still producing discoveries of the first importance, though the contributions of its women researchers were often acknowledged less fully than they deserved during their own lifetimes. In Copenhagen, a new center for theoretical physics emerged in 1921 when Niels Henrik David Bohr established the Institute for Theoretical Physics, supported by the Danish government, by the Carlsberg Foundation, and by international funding that recognized the importance of Bohr's contributions to atomic theory. The Institute, which would later be renamed in honor of its founder, quickly became the world's preeminent center for the development of quantum mechanics, attracting young physicists from across Europe and beyond who sought to work in an environment where the fundamental questions of atomic structure were being actively pursued. The culture that Bohr cultivated at his institute was distinctive, emphasizing open discussion, collaborative work, and a willingness to entertain radical ideas if they showed promise of explaining experimental observations. Spectroscopic data remained central to the theoretical work conducted there, for every new quantum mechanical formalism had to be tested against the accumulated measurements of spectral wavelengths, intensities, and regularities that decades of careful observation had provided. The Institute's atmosphere was informal by the standards of the time, with Bohr himself participating in discussions as a colleague rather than distant authority, and the ping-pong table installed in the building became almost as famous as the blackboards on which quantum mechanical equations were developed. Young physicists such as Werner Heisenberg, Wolfgang Pauli, and Paul Dirac passed through Copenhagen during the 1920s, absorbing and contributing to a theoretical understanding that built directly upon the spectroscopic foundations laid in the preceding decades. The Institute also maintained close connections with experimental spectroscopists, for Bohr understood that theory untested against measurement was merely mathematical speculation, however elegant it might appear. The mathematical physics tradition at Göttingen University in Germany provided yet another essential element in the development of spectroscopic theory, for the increasingly sophisticated analysis of spectral regularities required mathematical tools that only institutions with strong traditions in pure and applied mathematics could readily provide. Göttingen had been a center of mathematical excellence since the time of Carl Friedrich Gauss, and this tradition continued through the 19th and early 20th centuries under mathematicians such as Felix Klein and David Hilbert, who encouraged the application of advanced mathematics to physical problems. The theoretical physicists at Göttingen, including Max Born and his students and colleagues, developed the matrix mechanical formulation of quantum theory in the mid-1920s, providing mathematical frameworks that could predict spectral frequencies and intensities with unprecedented precision. The culture at Göttingen emphasized mathematical rigor in a way that complemented the more physically intuitive approach characteristic of Copenhagen, and the creative tension between these two centers proved remarkably productive. Born's seminars brought together mathematicians and physicists in discussions that crossed disciplinary boundaries, and the spectroscopic data that experimentalists had accumulated over decades provided crucial tests for the mathematical theories that emerged from these collaborations. The instruments that made all this research possible came largely from specialized manufacturers who developed their craft over generations, accumulating expertise that no individual researcher could hope to match. Among these instrument makers, the firm of Adam Hilger Limited in London occupied a particularly prominent position, supplying spectroscopes, spectrographs, and related apparatus to laboratories throughout the world. Founded in the late 19th century, the Hilger Company developed techniques for ruling diffraction gratings, for polishing optical surfaces, and for constructing the precisely adjustable mounting mechanisms that allowed spectroscopic instruments to achieve their full resolving power. The relationship between instrument makers and research scientists was one of mutual dependence and mutual education, for the researchers communicated their needs and the makers devised means of meeting them, while the capabilities of available instruments shaped the questions that researchers could practically address. A Hilger spectrograph represented not merely a collection of lenses, prisms, and metal parts, but an accumulation of optical knowledge and manufacturing skill that enabled measurements impossible with less refined apparatus. Other firms in Germany, France, and America contributed their own specializations to the growing arsenal of spectroscopic equipment, and the international trade in scientific instruments helped to standardize techniques and disseminate capabilities across national boundaries. The community of spectroscopists that formed across these dispersed institutions maintained its coherence through correspondence, through publications, and through the occasional gatherings that brought researchers face to face. Letters passed between laboratories carrying news of discoveries, requests for confirmation, and discussions of theoretical interpretations, creating networks of communication that preceded and in some ways anticipated the more formal structures of international scientific collaboration that would develop later. Scientific journals, particularly those devoted to physics and astronomy, provided venues for the publication of spectroscopic measurements and their analysis, and researchers followed these publications carefully to keep abreast of developments in their field. The Solvay Conferences, inaugurated in 1911 and funded by the Belgian industrialist Ernest Solvay, brought together small groups of leading physicists to discuss specific topics in intensive sessions, and spectroscopic questions figured prominently in several of these gatherings. The first Solvay Conference on Physics, held in Brussels, addressed the theory of radiation and quanta, topics intimately connected to the spectroscopic observations that had prompted Planck's quantum hypothesis and that continued to challenge theoretical understanding. Later conferences provided opportunities for researchers who knew each other primarily through correspondence and publication to establish personal connections that facilitated subsequent collaboration. National styles and institutional cultures inevitably shaped the spectroscopic research conducted within different settings, yet the international character of the scientific enterprise ensured that ideas and techniques flowed across boundaries with relative freedom, at least during peacetime. German thoroughness, British empiricism, Swedish precision, American organizational innovation, and Danish theoretical audacity each contributed distinctive elements to the collective understanding of atomic spectra, and the synthesis that emerged in the quantum mechanical revolution of the 1920s drew upon all these traditions. The laboratories and observatories where this work was conducted have changed greatly in the century since. Some expanded, some closed, some transformed beyond recognition. Yet the contributions they made during the formative years of spectroscopic science remain embedded in our understanding of atoms and light. The researchers who staffed these institutions, whether famous professors or anonymous assistants, whether acclaimed directors or overlooked women computers, built collectively a body of knowledge that continues to inform how we comprehend the physical world. As you consider these scattered centers of spectroscopic research, These varied cultures of scientific work. You might imagine the quiet dedication that characterized daily life within them. The long hours spent adjusting instruments and recording measurements. The patient correspondence that connected isolated researchers with distant colleagues. The gradual accumulation of understanding that came not through sudden revelation but through steady effort extended over careers and even generations. Such work proceeds most often in unhurried fashion, with small advances adding incrementally to what was known before. And though history remembers the dramatic breakthroughs and famous names, the foundation upon which those breakthroughs rested was laid by many hands working steadily in many places over many years. This thought, perhaps, can accompany you now as you rest. This sense of quiet progress, of patient labor rewarded gradually but certainly, of understanding growing slowly in the gentle light of spectral lines examined one by one across the peaceful years. By the year 1925, the science of atomic spectroscopy had reached a peculiar and rather uncomfortable position, one that might best be described as a kind of productive exhaustion, where the old methods and the old pictures had been stretched and modified and patched so many times that they had begun to resemble a well-worn map covered in penciled corrections, still useful for some journeys but increasingly unreliable for others. And the travelers who depended upon it could sense that something more fundamental would soon be required. The Bohr model, which had seemed so triumphant in 1913 when it explained the hydrogen spectrum with such elegant precision, had by this time accumulated so many additional assumptions and modifications that it had become, in the words of some physicists, a kind of theoretical scaffolding held together more by ingenuity than by any clear underlying principle. And while it continued to guide research and to suggest fruitful directions for investigation, there was a growing awareness that the scaffolding could not support much more weight without collapsing entirely. The successes of the preceding decade had been genuine and substantial, and one should not underestimate how much had been accomplished by the patient work of spectroscopists in laboratories across Europe and America, measuring wavelengths with ever-increasing precision, cataloguing the subtle patterns of spectral lines, and providing the empirical foundation upon which all theoretical advances ultimately depended. Arnold Sommerfeld's extensions to the Bohr theory, incorporating elliptical orbits and relativistic corrections, had explained the fine structure of hydrogen and the behavior of certain spectral lines in ways that seemed almost miraculous in their accuracy, and the general framework of quantized orbits and selection rules had proven remarkably successful at organizing the bewildering complexity of atomic spectra into comprehensible patterns. Yet for all these achievements, there remained a collection of puzzles that resisted every attempt at explanation within the existing theoretical framework, and these puzzles were not minor curiosities at the margins of the field, but rather fundamental difficulties that struck at the very heart of atomic theory. Perhaps the most troublesome of these difficulties was what had come to be known as the anomalous Zeeman effect, a phenomenon that had been causing headaches for physicists ever since Peter Zeeman's original discovery in 1896 that spectral lines could be split by magnetic fields. The normal Zeeman effect, in which spectral lines split into three components when atoms were placed in a magnetic field, could be explained reasonably well by classical electromagnetic theory and fitted comfortably within the Bohr-Sommerfeld framework. But the anomalous Zeeman effect, in which lines split into 4 or 5 or 6 or even more components with apparently irregular spacings, defied all attempts at theoretical explanation. Various physicists had proposed increasingly elaborate modifications to the theory, introducing half-integer quantum numbers and complex coupling schemes. But these modifications often seemed arbitrary and ad hoc, lacking any deeper justification, and the patterns of splitting varied from element to element and from spectral series to spectral series in ways that suggested some fundamental aspect of atomic structure was being overlooked. Equally troublesome was the question of intensity rules, which concerned not the positions of spectral lines but rather their relative brightness, a matter that had practical importance for spectroscopic analysis and theoretical significance for understanding the quantum mechanical transitions between atomic states. The Bohr theory and its extensions could predict, with varying degrees of success, which wavelengths of light an atom might emit or absorb, but it offered no systematic way of calculating how likely each transition might be, and therefore how bright each spectral line would appear relative to its neighbors. Various empirical rules had been developed, often through the patient accumulation of observational data, but these rules remained disconnected from the underlying theory, and physicists were increasingly aware that a complete understanding of atomic spectra would require not only knowing which frequencies were possible but also understanding why some transitions occurred readily while others were rare or forbidden entirely. The atoms with more than one electron presented difficulties of an even more fundamental nature, for while the Bohr theory could handle hydrogen with remarkable success, and while various approximation schemes had been developed for helium and the heavier elements, there was no systematic method for predicting the spectra of many electron atoms from first principles. The interactions between multiple electrons introduced mathematical complications that seemed to multiply without limit, and the rules that worked for one element often failed for another, suggesting that some essential piece of the puzzle was still missing. The periodic table itself, that magnificent organization of the chemical elements into families and groups with similar properties, remained something of a mystery at the atomic level, for while it was clear that the periodicity must somehow reflect the arrangement of electrons within atoms, the precise rules governing that arrangement had not yet been satisfactorily established. It was into this situation of productive confusion that Wolfgang Pauli introduced, in January of 1925, what would come to be known as the exclusion principle, a rule of startling simplicity that would prove to have profound consequences for the understanding of atomic structure and indeed for the whole of chemistry and solid-state physics. Pauli, who was then a young man of only 24 years but already recognized as one of the most brilliant theoretical minds of his generation, had been struggling with the problem of the anomalous Zeeman effect and had become convinced that the existing quantum numbers were insufficient to describe the states of electrons in atoms. He proposed that each electron in an atom must be characterized by 4 quantum numbers rather than 3, the additional quantum number being capable of taking only 2 values, and he further proposed that no 2 electrons in an atom could possess identical sets of all 4 quantum numbers. This exclusion principle, as Pauli termed it, provided an immediate explanation for the structure of the periodic table, for it meant that the electrons in an atom could not all crowd into the lowest energy state but were instead forced to occupy higher and higher energy levels as their numbers increased, much as guests arriving at a hotel must take progressively less desirable rooms as the better accommodations fill up. The closing of electron shells, which gave rise to the chemical inertness of the noble gases and the periodicity of chemical properties, followed naturally from this principle, and for the first time the arrangement of electrons in complex atoms could be understood in terms of a clear underlying rule rather than a collection of empirical observations. Yet Pauli himself acknowledged that the 4th quantum number he had introduced was something of a mystery, a mathematical necessity that had no obvious physical interpretation within the existing framework, and he suggested that it must correspond to some property of the electron that had not yet been properly understood. The resolution of this mystery came later that same year, in the autumn of 1925, from two young Dutch physicists working at the University of Leiden, Samuel Goudsmit and George Uhlenbeck, who were then both in their 20s and still at relatively early stages in their scientific careers. They proposed that the electron possessed an intrinsic angular momentum, a kind of internal rotation that was not associated with any orbital motion around the nucleus but rather belonged to the electron itself, as if it were a tiny spinning top. And they further proposed that this intrinsic angular momentum, which they called spin, could take only two possible orientations relative to any external magnetic field. This spin angular momentum was precisely the physical property that corresponded to Pauli's mysterious fourth quantum number, and it provided a natural explanation for the anomalous Zeeman effect. For the interaction between the electron spin and external magnetic fields would cause the additional splittings that had puzzled physicists for so long. The idea of electron spin was initially met with some skepticism, and there were legitimate concerns about whether a classical picture of a spinning particle could be reconciled with what was known about the electron's size and charge. But the explanatory power of the concept was so great that it was rapidly accepted into the mainstream of atomic physics, and it would prove essential for the full development of quantum mechanics in the years that followed. The spectroscopic anomalies that had seemed so intractable suddenly became comprehensible, and the complex patterns of the anomalous Zeeman effect could be calculated with precision once the spin of the electron was properly taken into account. Yet even as these successes accumulated, there remained a sense that something more fundamental was required, that the patchwork of rules and modifications that constituted the old quantum theory could not serve as the final framework for understanding atomic phenomena. The decisive break came in June of 1925, when Werner Heisenberg, then just 23 years old and working as an assistant to Max Born at the University of Göttingen, completed a paper that would mark the beginning of modern quantum mechanics. Heisenberg had been struggling with the problem of atomic spectra and had become convinced that the traditional picture of electrons moving in definite orbits around the nucleus was fundamentally misconceived, not merely in need of modification but actually incorrect at its foundations. He noted that no experiment had ever directly observed the orbit of an electron within an atom, that the orbital picture was a theoretical construction that had been introduced by analogy with planetary motion, and that this construction had been the source of endless difficulties and contradictions when pushed beyond the simplest cases. What experiments actually revealed, Heisenberg argued, were the frequencies and intensities of spectral lines, the observable quantities that spectroscopists measured with their gratings and prisms and photographic plates, and any successful theory should be built upon these observable quantities rather than upon hypothetical mechanical pictures that could never be directly verified. This approach, which Heisenberg described as considering only relations between observable quantities, led him to develop a new mathematical framework in which the familiar notion of position and velocity were replaced by abstract mathematical objects that obeyed unfamiliar rules of combination, rules in which the order of multiplication mattered so that the product of two quantities could differ depending on which was placed first. This strange mathematics, which Born would soon recognize as the algebra of matrices, seemed obscure and counterintuitive, but it proved capable of reproducing the known results of atomic spectroscopy while avoiding the conceptual difficulties that had plagued the orbital picture. The development of matrix mechanics, as Heisenberg's approach came to be called, proceeded rapidly through the latter half of 1925 and into 1926, with major contributions from Born, Pascual Jordan, and Paul Dirac, and it quickly became apparent that the new framework could handle problems that had been intractable within the old quantum theory. The intensity rules for spectral lines, which had previously been merely empirical, could now be derived from the theory itself, and the selection rules that governed which transitions were allowed and which were forbidden emerged naturally from the mathematical formalism rather than being imposed as additional assumptions. The anomalous Zeeman effect, that long-standing embarrassment of atomic physics, yielded to analysis within the new framework once electron spin was properly incorporated, and the complex multiplet structures of heavy atoms became, if not simple, at least comprehensible in principle. Yet matrix mechanics was not to remain the only form of the new quantum theory, for in the early months of 1926, Erwin Schrödinger, an Austrian physicist then working in Zurich, developed an alternative approach that seemed at first to be entirely different in character but would prove to be mathematically equivalent. Where Heisenberg had abandoned the picture of waves and orbits entirely, Schrödinger returned to it in a transformed way, proposing that the behavior of electrons in atoms could be described by a wave equation, similar in form to the classical equations that govern the propagation of sound or light, but with a profoundly different physical interpretation. The solutions to Schrödinger's equation were wave functions, mathematical expressions that spread through space and varied with time, and these wave functions somehow encoded all the information that could be known about the quantum state of a system. Schrödinger's wave mechanics proved immediately applicable to spectroscopic problems, and one of its first triumphs was a derivation of the hydrogen spectrum that was even more elegant and direct than Bohr's original treatment, requiring no arbitrary assumptions about quantization, but rather deriving the discrete energy levels from the mathematical requirement that the wave function remain finite and well-behaved throughout space. The extension to more complex atoms, while still mathematically challenging, could proceed in a systematic way, and the wave functions provided a natural framework for calculating the intensities of spectral lines through their overlap integrals, those quantities that measured how strongly different atomic states were connected by the interaction with light. The wave picture also provided an intuitive understanding of why certain transitions were forbidden. For transitions between states whose wave functions had certain symmetry properties would have vanishing overlap integrals and would therefore not occur. The transformation from the old quantum theory to the new quantum mechanics, which occurred with remarkable speed between 1925 and 1927, represented not merely a technical improvement but a fundamental reconception of the physical world at the atomic scale. The comfortable mechanical pictures that had served so well in describing the motion of planets and projectiles could no longer be applied to electrons and atoms, and the familiar concepts of position, velocity, and trajectory required fundamental revision or abandonment when applied to the quantum realm. This transformation had been driven, from beginning to end, by the demands of spectroscopy, by the need to explain the precise patterns of light that atoms emitted and absorbed, and spectroscopy continued to serve as the primary testing ground for the new theoretical ideas, confirming their predictions with the precision that only spectroscopic measurements could provide. Looking back from the vantage point of later years, one can see how the period from 1859 to 1925 formed a coherent arc of scientific development, beginning with Bunsen and Kirchhoff's recognition that each element possessed a characteristic spectrum, passing through the steady accumulation of spectroscopic data and the development of empirical regularities, reaching a crucial turning point with Bohr's quantum theory of the atom, and culminating in the revolutionary developments of 1925 that established the foundations of modern quantum mechanics. Throughout this entire period, spectroscopy served as both the source of empirical knowledge and the arbiter of theoretical truth, providing the data that theories had to explain and the tests that theories had to pass. The colors of flames, which had seemed so simple and familiar when Bunsen first gazed at them through his spectroscope in the dimly lit laboratory at Heidelberg, had proven to be windows into the deep structure of matter, revealing a quantum world that operated according to laws quite different from those of everyday experience. The patient work of measuring wavelengths, of tabulating spectral series, of searching for mathematical regularities among seemingly random numbers, had ultimately forced physicists to reconsider their most basic assumptions about the nature of physical reality. And the spectroscope, that modest assemblage of prisms and slits and scales, had proven to be one of the most powerful instruments of scientific discovery ever devised. As you settle more deeply into rest now, perhaps with your eyes already closed or closing gently, you might reflect on how the story of atomic spectroscopy demonstrates the unexpected connections between simple observations and profound theoretical understanding, how the colors of light can encode information about the innermost structure of atoms, and how the patient accumulation of careful measurements over many decades can ultimately transform our understanding of the physical world. The scientists who contributed to this story were human beings with their own personalities and prejudices and moments of confusion and insight, working in laboratories and studies and lecture halls across Europe and America, building upon the work of their predecessors and leaving foundations for those who would follow. The spectroscope continues to serve as a tool of scientific investigation today, its basic principles unchanged since the time of Bunsen and Kirchhoff, though its applications have expanded to include everything from the analysis of distant stars to the detection of environmental pollutants to the study of quantum phenomena that those 19th-century pioneers could never have imagined. The colors of light, whether emitted by a candle flame or a distant galaxy, still carry information about the atoms and molecules that produced them, and the methods developed in those early decades of spectroscopic research remain fundamental to the practice of physics and chemistry and astronomy. And now, as you drift toward sleep, you can let these thoughts settle quietly, knowing that the universe continues its intricate dance of light and matter whether we observe it or not, that atoms emit their characteristic colors in stellar atmospheres and laboratory flames and everywhere that matter exists, and that the understanding of these processes, hard-won over decades of careful work, represents one of the great achievements of human curiosity and persistence. The patterns of spectral lines, those regular sequences of wavelengths that encode the quantum structure of atoms, will wait patiently for another day, and for now there is only rest, and quiet, and the gentle fading of conscious thought into the peaceful darkness of sleep.